Okay, attendees are starting to arrive. We'll wait a few more seconds to give them time to join. Okay, so welcome everybody to this session of NeuroMatch 3.0. I'm Alberto Antonietti from Blue Brain Project, Geneva, Switzerland. And I'm glad to be here today to host this wonderful session. And my backend is Sophia, so she will help us with the chat and everything. And we will have a very nice session with three traditional talks that will be about different aspects of human cognition, intelligence, and memory. So it will be very, very, very interesting. And if you have questions, please use the Q&A box, and I will read them to our speakers. So I encourage you to send your questions a bit before the end of their talk, so I can ask them on time. And so I would like to introduce our first speaker. She's Maren Wirheim. She's a master student at the Goethe University in Frankfurt, and she will talk about the prediction of human intelligence. So Maren, the floor is yours.
Yeah, thank you. So I'm just sharing my screen. Okay. So hi everyone, and thank you for tuning into my presentation. I'm Maren, and I'm really happy to present to you the work that I've been doing over the past year with all of these great collaborators. So we try to predict human intelligence from time-resolved brain connectivity. So broadly speaking, we analyze variations in the dynamic connection of different brain regions and how they relate to differences in human intelligence. And when using an average of the complete time series, we can predict intelligence with a correlation of 0.37 between the observed and predicted intelligence score. And now recent advances by the lab of Olaf Sporns have identified time points where the whole brain is highly connected. And these so-called event time points correspond to 5% of the complete time series and also capture the majority of the time average data and are also individually specific, like a fingerprint. And therefore, we hypothesized that these events might also carry the intelligence relevant information. However, as you can see, those events are rather achieve a mediocre result when predicting intelligence. And therefore, we went one step further and asked, are there other 5% of time points in this connectivity strength data that are predictive for intelligence? And as you can see, the local extreme points in this connectivity strength are predictive for intelligence. And I'll go into detail about them a little bit later. So as a quick overview, intelligence is correlated with a lot of important life events, such as your socioeconomic status, health, or academic achievement. And in this study, we used the so-called VASI test, which is a measure for general intelligence and consists of 4 subtests, so a block design test, a similarity test, a vocabulary test, and a matrix reasoning test. And as neural data, we used functional MRI data. So people were scanned in an MRI scanner while at rest. So they were just looking at a fixation cross. And this data approximates the neural activity over time. And we can now parcellate the brain into 114 different brain regions, which correspond to 7 different functional brain networks. And here on the right, you can see the neural activity of 2 exemplary nodes. Whereas when we now calculate the correlation over all of the possible node combinations in the brain, we can calculate the static functional connectivity. So however, as the static connectivity is a time average, we hypothesized that calculating this might lose a lot of intelligent relevant information. And therefore, we use a new approach to calculate the dynamic functional connectivity. And to do so, We use an approach which was recently published by Esfalani et al. So it's also in the Olaf Sporn's lab, which is quite simple but highly effective. So you can again think of two neural activity time series of 2 exemplary nodes, which are z-scored. And we can now calculate the frame-wise co-fluctuation by just simply multiplying these z-scored time series frame-wise. And when we do this for all possible node combinations, we can calculate the dynamic functional connectivity. So from this dynamic connectivity matrix, we can then calculate the whole brain connectivity strength by calculating the root sum of squares over all of the possible node combinations. And as I mentioned before, we observe that there are time points where the whole brain is highly connected. And these event time points are defined as the highest 5% of this RSS time series. And then using either those 5% or the remaining 95%, we can reconstruct functional connectivity matrices from the selected time points. And then we can take these matrices to predict intelligence. And to do so, we use a new approach, which we term the Cmap approach, and I'll quickly walk you through it. So just think of the functional connectivity matrix, and we can now calculate the variance of this matrix into any direction using an arbitrary vector. And maybe think of this vector as, for example, the first principal component. And if we now keep this vector the same for all participants, we can calculate variance features for all of the participants. And maybe we find that, for example, for the first principal component, we do not observe a strong linear relationship to intelligence. However, if we now, for example, choose the second principal component, we might observe a strong linear relationship. But we don't want to just random guess which vectors might share a strong linear relationship, and therefore we optimize for this effect. So we generate features that share strong covariance between intelligence and those generated variance features, and then use these features to predict intelligence. And this is our Cmap approach. So the complete build-up is we use a leave-one-out cross-validation. So we have our training data and one left-out test sample. And we can now weight each participant's functional connectivity matrix with a mean adjusted intelligence score. And when summing over all of participants, we generate this matrix Q, which enhances differences in intelligence. And if we now calculate the eigendecomposition of this matrix, we generate vectors, which can then be used to calculate variance features, which share decreasing covariance to intelligence. So these have the highest covariance, whereas these ones have the lowest covariance. And as you can see, the vectors that generate the features with the highest covariance are also highly structured into the 7 brain networks, whereas the lower ones are rather random. Now, if we use those generated features, we can fit our prediction model, which is an elastic net. So it's basically a linear regression with L1 and L2 regularization. And now that we have our model, we can finally use our vectors to also calculate the variance features of the left-out test sample. And these features can then be inputted into our prediction model to predict the intelligence score of the left-out sample. So here, just quickly again, the 2 steps of our Cmap approach. So first, the feature generation, where we maximize the covariance, and then the elastic net prediction model to actually predict intelligence. And as already said, we only achieve mediocre results when predicting intelligence from the high amplitude time points. However, when predicting from the low amplitude time points, we can predict intelligence almost as good or as good as with the complete time series. And this is kind of like a sanity check. Then when removing those events, we do not remove the intelligent relevant information. However, we tested the events and their relation to intelligence a little bit further. So at first, we replicated the findings by Esfalani et al. That the high amplitude events reconstruct the static functional connectivity a lot better than the low amplitude time points. And also, and then we went further and showed that there's only a weak relationship between intelligence and the number of events necessary to reconstruct the static functional connectivity with a similarity of 0.8, so these points here. And then we showed also that if the events are not related to high in-scanner head motion, and that their temporal distribution is also unrelated to intelligence. So as an intermediate conclusion, we don't observe any predictive ability of the number of events, their temporal distribution, and when reconstructing functional connectivity from only these event time points. And this is surprising because the events capture the individual identifying information in the human functional connectivity. So as these 5% of events are seem not to be predictive for intelligence, we then ask the questions if we can identify other 5% of this time series which are predictive. And therefore, we looked at the extreme points in this connectivity strength time series. So on the left, you see the maxima in yellow and the minima in green. And everything above this red dotted line belongs to the event. So these would be event time points, but now we choose only those dots. And as the events correspond to 5%, we also want to select 5% of time points, which are predictive for intelligence. And therefore we choose the same number of maxima as minima. And we do not do this randomly, but we choose the lowest maxima and the same number of highest minima. And overall, this will give us 5% of time points that we will use to reconstruct functional connectivity and to predict intelligence. So here again, just several selected time points, and we use those time points in the neural activity time series to then correlate over these selected time points and to reconstruct functional connectivity. And as I said, we can predict intelligence with a correlation of 0.3 using those time points. So as a conclusion, the events are not predictive for intelligence. However, we find that the local extreme points of whole brain connectivity strength are predictive for intelligence. And thereby, we showed that actually in only 5% of the time series, there's enough information contained to predict intelligence. And all of our results also generalize to a new data set and also when controlling intelligence for age. So as our next steps, we want to further analyze those time points and their neural mechanisms and how they relate to cognition and intelligence, and also if there's any effect of global signal regression on our results. So thank you for watching, and also to all of our great collaborators here.
Thank you very much, Maren, for your talk. Very interesting. And in the meantime, while we wait for possible question from the audience, I have one from my own. You are considering, let's say here, intelligence as just the IQ, right? So I think an easy critique could be that maybe intelligence cannot be measured by a single number.
Yes, so that's absolutely right. And in this case, we have an intelligence test that is often tested. So it's kind of a stable measure for this, but obviously it's a lot of noise contained in that one. However, we also use in this other data set, in the bigger one, we use different tests that are kind of combined to one measure in the end to predict them. So it also contains several different tests. But you might be right that it might be an additional approach to kind of maybe predict several measures, and some of them might be more predictive than just a single measure of intelligence. So, yeah. Thank you.
Thank you very much. Then we have one question from Bastian. Can you speculate on what is the meaning of these local extrema that are predictive for IQ?
Yeah, so this is the point that we're just analyzing. So we have different underlying effects in those local extreme points. So either the whole brain is a little bit active. So some of these time points that we observe, there's just a little, like a low connectivity between all of those, between the whole brain. Or we have the other effect where several brain networks are highly connected, whereas others are only weakly connected. And now the next step would be to analyze which of those processes are actually the ones that drive the prediction. So separate these events and maybe like find all these patterns happening in those local extreme points, and separate those and their ability to predict intelligence. No.
Okay, thank you very much again for your talk and for answering our questions. So I will move to our second speaker today. She's Chiara Caldinelli, and she's a PhD student at the CUSA Club at Trinity College Dublin in Ireland. She received her bachelor's in cognitive science and master's in neuroscience from the University of Padua, Italy. And she's interested in how higher cognitive function develop and how early experience can shape the way we look at the world. So please, Chiara, the floor is yours.
Thank you, Alberto. The talk today is the frontoparietal network is not a flexible hub during natural risk recognition. So the frontoparietal network that you can see in yellow in this figure is traditionally associated to higher cognition, so executive functions or fluid intelligence, or anything really that we use when we need to complete a complex task. So opposite to unimodal, to other brain networks that are unimodal, like the visual network, for example, that is mostly active when we look at something, or the motor network that is mostly active when we move parts of our body. The frontoparietal network is actually active during a great variety of tasks. So for instance, is mostly active when we implement, when we learn something new. And this is partially because it's very highly structurally connected to the rest of the brain. But also because it's functionally connected to the rest of the brain in a higher measure if compared to the other networks. And it's actually been proposed that the frontoparietal network is actually a hub, flexible in the sense that it's able to change the connectivity to the rest of the brain, highly. And how, because it's sort of managing the rest of the network. So sometimes it would be very highly connected to something, sort of recruiting another brain network that is needed to complete the task. And sometimes it's sort of shutting down. So someone will be able to quantify the flexibility of the frontoparietal network. And this comes from a group led by Michael Cole. So they showed it first in 2013. So in this graph, you can see the frontoparietal network in yellow, and the higher the bar, the more flexible one brain network is, and all the brain networks are lined out here. So you can clearly see that the frontoparietal is the one that is most flexible. It really stands out with compared to all the others. So they first published that in 2013 with around 15 people, and it was replicated in 2020 with 100 people. So in both these studies, they used the same task that I will try to explain now. So the participants would see first the screen on the left. So they would see three things, same, sweet, and left index. And then they know that they will see two things later. So they have to answer the question, are they both the things that you are going to see sweet? And if yes, then press the button on your left index finger. So then they see grape and apple, and are they both sweet? Yes, they are. So they have to press the button of the under the left index. Okay. And this goes on, and so they see second loud in the middle, and they would be like, is the second element loud? And if yes, then press the button under your right middle finger. And then they see leaf and dynamite, and yes, it's loud. So the answer is still yes, and they have to press the button under the right finger. And this goes on for 64 times. So you can understand that this task is very complex. It's very complicated to explain. It's actually not complicated, but it's also complicated to perform. I still thought that this idea of flexible was very interesting, but it's sort of limited if we only can show it doing this task. So then we thought that if this characteristic of the frontoparietal network is something that is very intrinsic to the network itself, then it would show in everyday life. So now, because we are constrained to have people lying into the scanner and doing something, looking at something on the screen, we cannot really measure in everyday life, but we thought that something that would resemble an naturalistic stimulus would be watching a movie. So then we took in consideration this one, watching a movie, and we tried to answer this question, which is the frontoparietal network a flexible hub during naturalistic cognition? So we decided to use an open access dataset from the Study Forest project, the German project, taking showing a full movie, Forrest Gump, of around 2 hours to 15 participants. They were young adults. So we use the pre-processed data from this project, and we used a similar pipeline to the ones used in the studies that I showed earlier. So in particular, we took the movie and then we chopped it into small windows. So the choice of the length for the window is very arbitrary in functional connectivity. It somehow varies from 30 seconds to 180 seconds. And we chose to use 30 seconds because that was very similar to what they used in the previous studies that I showed you earlier. So we then estimated a functional connectivity for each of these windows, and that was estimated for every network, and then we averaged, and we took the standard deviation. So the standard deviation was a measure of how much the connectivity was varying for each network. And then we used 2 measures of flexibility, the global variability coefficient and the between network variability coefficient. So they seem very complicated by the name, but it's actually a very simple concept, and I will tell you about it. So the first one, the global variability coefficient, is just how much one network was connecting to any other network, including itself. So it's just a simple measure of connectivity. While the between network variability coefficient is how much one network was connected to all the other networks, but not itself. So only looking at other networks then. So here are the results. So the frontoparietal network will be in yellow at the extreme left. So you can see that it really doesn't stand out as the highest among all the networks. It's still high, but there are other networks that are higher, like the auditory network and the motor network. So this is for the global connectivity, and it's sort of the same for the connectivity that does not include the connectivity to itself. And then so this is not the result we were expecting. And just to make sure that the choice of window length was not making things looking weird, then we tested it with different window lengths, and you can see that the results really don't change much. And this is also for the between network variability coefficient. So this is not really the results that we expected. And then we thought that, however, we tried to use very similar, a very similar pipeline to Michael's calls. Perhaps our study had some limitations that caused the results look like that. So, for instance, we only had 15 people, and we used a movie that although it's very engaging, we are not sure it really engages the frontoparietal network. So we decided to run the second study. And this time we took into consideration another open access dataset from the Cmap project. So in this dataset, the participants are around 600 with a wider age range. So they were including young adults, but also older adults. And they were all watching a short clip. So instead of a long movie, then this time they only had 8 minutes. It's a very specific clip that we know that engages the frontoparietal network because that was shown in a previous study. It's from Hitchcock, and it's the story of a child who finds a gun, and he thinks it's a toy gun, but it's actually a real gun with a bullet. And he goes around and plays with mom and points into a friend, and he goes into a shop. So it's very suspenseful. Again, we use preprocessed data from the project. We use a similar pipeline, took micro calls. We use chunks of 30 seconds, and we estimated the same measures. So here are the results. So again, in yellow, the frontoparietal network, and again, you can see that is not the one that is standing out as the highest. So the results here seem to look quite different from the previous experiment. However, statistically, they're like very similar. They all differ from each other. They're different from the whole brain connectivity. The motor and auditory networks are still higher than the other networks. And this is true also looking at the other measure, and this is true also looking at other window lengths. So what we can conclude is that, so we wanted to answer this question. We wanted to ask ourselves this question with this movie: is the frontoparietal network a flexible hub during naturalistic cognition? So what we see from the result is that the frontoparietal network does not act as a flexible hub any more than other networks in the brain. So this would suggest that it's not a trait of the frontoparietal network, but rather a state during sets of different tasks. And this is it, I think.
Thank you very much, Chiara, for your nice talk. So again, while the attendees can send a question, I have some myself. The first one is that I noticed that in the CamCam dataset that you analyzed, there was less variability between the different networks, so they are kind of looked equally distributed, while in the Forrest Gump experiment there was much more variability. Do you have an explanation for this? Yeah. Maybe the duration of the movie? Or...
I would say actually the opposite. So there is more variability here. Okay. And the graph itself looks more flat. Yeah, we are still investigating that. So I'm presenting now perimeter results. That's extremely interesting, but also it's just very difficult to explain. So this could just be because we have 600 participants here and the age range is so wide, while there we only have 15 and they're all young and healthy. So here we just have, I don't know what the range of connectivity. So this is my feeling, but for sure, this is something interesting that we would like to investigate more. Thank you for the question.
No problem. And also another interesting thing that I noticed, but maybe that was just by chance. So in the Forrest Gump protocol, in slide 12, I think, the network, the motor network was kind of very high. I think that's the second highest in for the GVC index for Forrest Gump. So cool. Is it, let's say, could it be that it's related to the fact that in Forrest Gump you see a lot of running, or could be due to some other factors?
Yeah, Absolutely could be, but I mean, it's also a long movie, and the scenes in which Forrest Gump, although it's running, he is really running a lot in the movie. I'm not sure that he's running so much, and also, so this, like, it's true that these graphs look very different, but the overall shape is the same. So it would be very similar in the other short clip, but also, I mean, we are looking at someone that is moving on the screen, so that could absolutely be, and people are just hearing people talking, so the auditory network, that absolutely can be like, but I feel like this is only speculation.
Okay.
Yeah.
That was just out of curiosity. Okay, thank you very much, Chiara. Very, very nice work. And so I will move on to our last speaker for this session. We will still see some prediction, but not of attention as in the first case, but of attentional engagement. And our last speaker is Ha-Young Song, and she is a doctoral student in integrative neuroscience at the University of Chicago. So it must be quite early for her. So thank you for being here, and please, the floor is yours.
Thank you so much for the introduction. I'm actually right now in Korea, so my time is okay. Yes, thank you everyone for coming in. Today I'm going to present the work titled Predicting Attentional Engagement During Narratives and Its Consequences for Event Memory. Okay, so this work is inspired by the phenomenon that every day we experience dynamically changing attentional engagement. So for example, imagine a situation when you're watching a movie, listening to a podcast, or having a conversation with your friends. Though these narratives are highly engaging, our attentional state is never constant, but it's dynamically changing across time like this. So previous theories have defined this narrative engagement as an experience of being deeply immersed in a story with heightened emotional arousal and attentional focus. And quoting directly from 2012 paper, this engagement, which we use so often in our daily lives, is a cognitive state that lacks a rigorous definition in the neuroscientific field. So in order to push forward with this research, we first needed to empirically define what narrative engagement is. Then eventually, we were curious to know whether there exist neural signatures that reflect time-varying engagement. And also, we wanted to characterize engagement in relation to the psychological notions that are better understood in the field, sustained attention and episodic memory. Okay, so for the experimental procedure, basically what we did was we analyzed 2 open source fMRI studies, and then we collected 2 independent behavioral data sets. So the first fMRI data set that we used was collected by Finn and colleagues, where 22 participants listened to a 20-minute audio narrative story inside the scanner, and this is called Paranoia Story. And then as the post-hoc behavioral session, participants did a spoken recall in which they were instructed to retell the story in as much detail as they can. And another data set that we analyzed was by Chen and colleagues, where 70 participants, again, inside the scanner, they watched the television episode of Sherlock for 15 minutes. And then again, these participants did a spoken recall as a post-hoc behavioral session. However, the problem with these data sets was that we did not know how attentive or engaged these participants were during the study. So we wanted to conduct behavioral studies using the same narrative stimuli to measure people's dynamically changing subjective engagement. So we tried the most intuitive way that we could think of. We simply asked participants to self-report their dynamically changing engagement. So this was the instruction screen that participants were viewing. So during the task, you will listen to a story. While listening to the story, you will continuously rate how engaging you find the story. So the scale bar was always up on the screen, and participants will press right if they're feeling more and more engaged. They're going to press left if they're getting less engaged. So participants had was able to continuously adjust the scale bar as they listened to the story or watched a television episode. And this was the definition of engagement that people saw before starting the experiment. So the definition of engaging was when they're curious and excited to know what's coming up next, when they're immersed in the story, when their attention is focused to the story, and when they found the events interesting. Okay, so I'm going to show you the results for both Paranoia and Sherlock. The x-axis is time duration, and y-axis is all the participants. And these are the results. You can see that for every participant, their behavior ratings are normalized across time. And what you can see is that during these moments of time, participants were reporting that they were highly engaged. And you can see that these are quite synchronous across people. So we averaged every participant's behavior responses like this. And what we saw was that given that these gray areas are 95% confidence interval, participants' behavioral ratings were highly synchronous, and it was very dynamic across time. So we were curious when participants were reporting to be highly engaged versus less engaged. So for example, we saw that this very less engaging moment was when Dr. Watson was casually strolling in the park without any suspenseful event going on. Whereas this moment of time was when Sherlock was examining the dead body and trying to find the clues to this mysterious incident. And we also found statistically that engagement is increasing when participants were viewing emotional moments of the narratives. Okay, so from this behavioral study, we observed that engagement is fluctuating across time dynamically. It is synchronized across individuals. And because of this synchrony, we were able to apply this group average engagement to infer engagement of independent functional MRI participants. Okay, so next, our question was whether there is this neural signatures that reflect this time-varying engagement. So we wanted to use this prediction approach to ask whether just from observing this functional brain dynamics, can we predict people's time-varying engagement? So we adopted a method of connectome-based predictive models where the goal was to predict this time-varying engagement. So basically what we did was we extracted this time-varying functional connectivity applying sliding window approach for all participants. And then we trained the model like this to understand the relationship between time-varying functional connectivity and then time-varying group average engagement that were defined from independent behavioral studies. And then we applied the model to unheld out participants to see if whether the model, after seeing the unseen participants' time-varying functional connectivity, whether this could predict this group average engagement. And then the prediction accuracy was calculated like this by taking the correlation between the predicted and observed engagement time courses. Okay. And to test for the generalizability of the results and to overcome any potential confounds, we made use of the fact that we had this independent data set. And then we trained the model from all participants in one sample and then tested in an unseen participant at an independent data set. And we turned this across data set prediction. And again, the prediction accuracy was calculated like this. Okay, so this is the prediction results. Again, we predicted time-varying engagement from time-varying functional connectivity. And first, I'm going to show you the results for within dataset prediction. These are the null distribution for Paranoia and Sherlock respectively. And these are the actual prediction results for all cross-validations. And what I have here is the average of these prediction results. And you can see that for both Paranoia and Sherlock, it was significant above chance. However, most importantly, what we observed is that in an across dataset prediction, both these data sets were significant above chance. And what these results implies is that the time-varying functional connectivity-based models is able to predict engagement across participants and even across independent data sets that contain different narratives, different sensory modalities, and different pre-processing or analysis pipelines. Okay, and we were curious to know which of the functional connections were important in this prediction. And we observed that not only does engagement network is significantly overlapping between paranoia and Sherlock datasets, but that the functional connections within and between the regions of the default mode network and frontoparietal networks were predicting this time-varying engagement. So next, we wanted to understand the relationship between engagement and sustained attention. And from behavioral studies, we saw that narrative engagement can be understood as stimulus-driven attention. However, what we noticed is that most of the psychological literature studied these fluctuations in sustained attention within the context of these controlled psychological tasks. So here, participants were asked to make continuous button presses to streams of visually presented images like this. And the researchers tried to characterize distinct moments of attentional state using people's response time variabilities. And previous literature showed that from patterns of functional brain connectivity, they can predict this participants' individual's attention task performance. And we use this patterns of functional connectivity, which we would call sustained attention network. And then we try to understand whether this sustained attention network defined during controlled experimental task was able to explain this stimulus-driven narrative engagement. So again, here, we are going to predict people's narrative engagement using see that sustained attention network was unable to predict people's engagement as people were listening to an audio narrative story. However, interestingly, the sustained attention network was able to predict people's engagement as people were watching a television episode, which suggests that sustained attention network, which was defined during controlled visual task, was able to predict engagement during movie watching, but not story listening. Okay, lastly, we were curious to understand the relationship between engagement and episodic memory. So recalling back to our experimental procedure, we had all participants do a spoken recall. So our hypothesis was that given that people's engagement is fluctuating over time, whether people would remember highly engaging events compared to less engaging events. So in order to do this analysis, we extracted every individual's recall fidelity time course that indicates which of the events that people were more likely to remember versus did not remember. Okay, so here, what we did, important points to note is that we predicted individual specific recall fidelity for every fMRI participants from their individual specific engagement network. And also these characterization of event recalls and engagement dynamics were done separately. Okay, so first for the within dataset prediction, here what we see is that people's engagement network was able to predict people's subsequent event recall above chance for both paranoia and Sherlock datasets. However, we did not find significant results for a cross dataset prediction. So what this implies is that individual specific recalls are predicted from story specific engagement network, suggesting that engagement impacts subsequent event memory. And to put it again, so that we remember events that are more engaging. So to conclude this talk, I'd like to emphasize that this continuous behavior rating is actually a good way of measuring group average engagement. We saw that time-varying functional connectivity predicts engagement. And then we also observed that neural signatures of sustained attention defined during controlled tasks partially reflects engagement to narratives. And lastly, we see that neural signatures of engagement reflects memory encoding of the events. And with that, I'd like to thank everyone for listening. I'd like to acknowledge my co-authors and people who open source the data set and code, and Neuromatch organizers and my lab members. Thank you so much.
Thank you. Thank you very much for this last wonderful talk. So we have one question from Marco. He compliments you for the nice talk, and I join him in this. And he asked, can you speculate on the finding that the sustained attention network obtained from the visual task is predicted by the movie, but not the auditory task?
Yes, so this was actually a very interesting finding. So again, this sustained attention network was characterized during controlled visual task, and the functional connectivity that were specifically standing out to be predictive of sustained attention was a lot of the networks were coming from the visual sensory networks, and also dorsal attention network, which is known to be predictive of like visual attention. And we think because these sensory modalities coming from visual, it is specific to predicting engagement as people watch movies, but not so much as when people are listening to stories.
Okay, thank you very much. That was a question that I also wanted to ask you. So thank you, Marco, for your question. And then okay, there is a question in the chat from Thomas. Since participants had to report their engagement, their response is correlated to their engagement. How this report could impact the neural signatures of engagement?
Oh, yes. So there was actually no problem of confounding from people's like behavior responses, because this behavior response was collected in an independent behavioral studies. So for the fMRI participants, what they did was they just lied inside a scanner and watching the television show, but this behavioral engagement was collected as a separate data set from independent participant group. Does that answer the question?
I think, yeah, I said thanks that I missed that part. Okay, so I think one last comment that I can make if no more questions arrive is that it's really nice to see in all your works the use of open fMRI datasets, and the fact that there is, well, especially in neuroimaging, there is this movement to have more open data and share data among groups, even if especially because it's kind of time consuming and resource consuming to have those data, and also the numbers of participants has to be, let's say, as high as possible to have some robust data. So I really like to see that you could build your part of your work on already collected data that have been shared to the world. So that was just nice to see. And thank you again to everybody, to Chiara, to Hayong, to Maren for their wonderful talks, and to all the attendees, and also to Sophia, our backend today. So I will close the sessions, and I would just say to enjoy the rest of the conference. Thank you very much, everybody. See you soon.
Thank you.
Okay, so attendees are starting to join. I will wait a few more seconds to give them time to arrive. Okay, I think we can start. So, hello everyone. Welcome to this session of NeuroMatch 3.0. I'm Alberto Antonietti from Blue Brain Project Geneva in Switzerland. And today we will have two great talks. Just two. The third one unfortunately has been cancelled, but we are glad to hear from our two speakers, and we will have a bit more time for question and answers in the case. So the common theme of this session is related to movement and energy and vigor of movement. So I am very happy to welcome our first speaker. He's Thomas Morvan. He graduated in cognitive neuroscience at the University of Strasbourg in 2018. And since last year, he's a PhD student in neuroscience and physics in Marseille University. And he's working in the Institute of Neurobiology of the Mediterranean and in the Institute of Research for Out of Equilibrium Phenomena. So very nice names for an institute. And his research project revolves around the development of an automated behavioral task in order to study motor control in rodents, and then a mathematical modelization of a virtual agent's behavior in the same task. So both experiments and modeling, that's really cool. So welcome, Thomas, and the floor is yours.
Yeah, thank you, Alberto, for this nice presentation. So as you said, I'm studying movement vigor in rats. So basically, how rats decide how much energy they will use when they do their movements. So let's plan the setting. So imagine that you are at a piñata party and the piñata just broke and all the candies are on the floor. If you are a kid, you want to get as much candy as you want. To get this candy, you have to do an effort, you have to do a movement, and you can do like this boy, you can do a really fast movement that is going to have a high cost in energy. But you can also do like this girl, who is going to be a bit slower, and that is going to consume less biomechanical energy. So if that was the only parameter, the ideal strategy would be to use the less energy possible, so move slowly. Problem is, if you do that, you are very late and there might be no candy left. So this introduces a cost of time. So basically this has two components. First component called the reaction time. So the time that you spend before deciding to commit into the action. And then you have a cost of time that is linked to the duration of the action that you do. So yeah, if you go there really fast like the boy, you're going to have a really low cost of time. And if you take your time, you're going to have a high cost of time. So if you sum these two costs, you have the sum of the two costs. And the idea is that you want to minimize the cost of the action that you want to do. So you want to minimize and you want to trade between the cost of time and the cost of movement. So in this case, it might be interesting to spend a little bit more energy moving in order to decrease the cost of time, like the boy did. So with that, we can get a utility function, so a perceived value of an action that you can do, which is comprised of the reward that you can get, minus the two costs, so the cost of movement and the cost of time that you can get per unit of time. So we know from various experiments in humans and non-human primates that movement vigor is a good proxy for utility. So vigor is usually described as the movement speed of the movement that you do and the reaction time for this movement. And if you have a high vigor, you have a higher movement speed and a lower reaction time. I can't see below your faces. So yeah, what I wanted to say, I don't see it. Maybe I can. Yeah, so an increase of vigor would be would reflect, in fact, the utility of your action. So what we want to do is to develop an nosological experimental paradigm to manipulate these different parameters of the utility of rats, so the reward, the cost, and the two costs in rats. And the question is, can we see a trade-off between the cost of time and the cost of movement is in this setup? And we want to be as naturalistic as possible, because what has been done in previous experiments is that basically you get some virtual rewards, like virtual money in humans, and you do non-natural movements like fixed arm movement or lever presses in rats. And our long-term goals are how can we explain the behavioral variability between, for example, the slow and the fast kids that we saw before. And finally, how it's computed in the brain. So our task is really simple. Basically, we are training 8 rats to run back and forth an enclosure that is 90 centimeters long. So in the beginning, the rats can go to one reward pod that has water. Yeah, the rats are water restricted, so they want to get the reward when they can. So they get to the reward pod, they can drink the reward, and they can wait if they want. Then to get the next reward, they have to run to the other side, and so on for 30 minutes. Basically, yeah, this is a 30-minute session. So what we see is that they're going back and forth on the enclosure. So if we zoom in on a few runs, basically we have the position at the start, when it's the middle of the enclosure, and when it's at the end. We also have the leak data, basically when the animal leaks or not. So with this data, what we can do is extract when the animal runs to the left and to the right. So we define the start of a run and the end of a run, and we compute the speed at which he runs. We are also interested in the waiting time. So basically, we define the waiting time as the last moment that he was leaking and the moment that he starts running. So we do that for the run to the left and to the right, and we do that for the waiting time in the left and in the right. So first, we need a control condition in which basically the utility of running to one side is the same as running to the other side, because we have the same reward and he has to run the same length in both cases, so 90 centimeters. In this case, here I plot you the speed of the animal. So each dot is a single run, and you get the speed. So the higher it is, it means that the animal was fast, and when it's lower, it means that it was slower. And we got that when it runs to the left and when it runs to the right, and we can already see in this distribution that basically it's the same. They have the same speed overall to both sides. If I plot you cumulative histograms of these run speeds, basically we see no clear difference. So they run as fast to one side and to the other. Then it's the same principle for the waiting time. So basically, yeah, again, each dot is a waiting time in left and in right, and we see no clear difference, and the same on the cumulative histogram. So yeah, if we have the same reward on each side, basically we don't expect a change in utility, so no change in vigor. If we look at the population-wide for 8 rats, so basically every rat is doing the same behavior and does not really run faster toward one side and the other, and does not wait faster in one side and the other. You can also see that some rats are on overall running faster than others and waiting less or more. So this will be interesting later. Now, if we want to play around with it, we can modify the size of the reward. So we can put a small reward on one side, and we can put a big reward on the other side and just see what happens with the movement vigor. So yeah, what we expect is if the reward is bigger, the utility of the run should be bigger, and so they should run a bit faster toward this side. And this is what we see. So again, same data representation. We see the runs, the speed of the runs toward the small rewards and toward the big rewards. And basically we see that towards the big reward, they tend to run a bit faster, which is also what we can see on the cumulative histogram. So yeah, in the thick line is toward the big reward, and the thin line is toward the small reward, and basically we have more runs toward that are faster toward the big reward. This is the same for the waiting time. Basically, they wait more when they are in the big reward zone than when they are in the small reward zone. This is also something that you can see on the population level. So basically, most rats are doing the same strategy, meaning that they run faster towards the big reward and they wait more in the big reward zone. Now, if you want to modify the cost, one thing that we can do is modify the length of that they have to run. If we increase the size that they have to run, so if you go from 90 centimeters to 120 centimeters, basically we increase the movement cost, but also the cost of time, because a longer time elapses before they get to the reward. And if we decrease the size that they have to run, basically it's the opposite. So the question is, are they going to run faster in this condition to trade off the cost of time? And yes, this is what we can see. Basically, if we have our control condition at 90 centimeters, we see that when they have a shorter distance to run, they tend to run a bit slower. And when they have to run a bit longer, they tend to run faster. For the waiting time, we see no clear difference between the three conditions. So our goal was to first develop an altruistic automated task to test the rats. And we modified the reward size and the distance to run. And we saw that it modified the movement speed and the waiting time in a way that is congruent with the vigor theory and utility. We will in the future, instead, for instance, of modifying the reward size, we can modify the probability of the reward. Instead of modifying the length in order to modify the cost of time, we can add a delay before they get the reward. And to modify the cost of movement, we can take advantage that, in fact, the floor of the apparatus is a treadmill, and we can make it turn toward one side, which will strongly decrease the cost of movement toward one side and increase the cost of the movement towards the other side. One of our goals is also to explain the behavioral variability. So yeah, this will be the mathematical work that we will have to do that I've not really delved into now. But we can see that we can get some behavioral variability in our population, but we need a lot more data. We also don't really like that the rats are water restricted and they can only do the task once per day. So we want to make them able to be tested continuously. So every day, all day long, every day of the week. So our idea is to make an automated sorter to allow the rats to cross and go to the task apparatus when they want to perform the task. So yeah, another long-term perspective is how is it computed and implemented in the brain. So basically, we think that it's happening in the basal ganglia, in which we have a direct pathway that is excitatory is going to facilitate the action, and an indirect pathway that is inhibitory is going to inhibit the action. And we think that is going to have an impact on the computation of utility and thus on movement vigor. So I'd like to thank my team and all the people that work on it. So David, Christophe, which are my PIs, Stefania and Ocean, who worked on the computational part that I couldn't present to you today. And I'd like to thank you for your attention.
Thank you very much, Thomas. Very nice talk. Congratulations for your first talk. And we already have one question from the audience, so I'm going to read it to you. So Ellie asks, how does the behavior observed change or vary throughout the duration of these trials?
Yeah, okay, so that is quite interesting because basically what we can see is that at the beginning, I looked at the evolution of like the running speed and the number of crossings that they do throughout the session by 5-minute sub-sessions. So what we can see is that in the beginning, they are a bit slow because like they have to wake up or activate themselves to get ready to really run. Then they have a peak during the 5 to 15 minutes. And then I get that they get tired or they have drank enough. So in the last 10 minutes, the speed and the number of crossing decreases a bit.
Okay, thank you very much. And then I have a question myself. So in this protocol that you used, the reward is always the same, right? So if the mouse run faster or slower, that doesn't change the amount of reward.
It's always the same reward size throughout the same session. So obviously, yeah, I showed you an example in which we had a big reward on the right side. And we also tested if we had the same reward on the other side and the small reward on the right, for example. And we got the same curve basically. But yes, we're the same session, the reward is constant and doesn't move.
Yeah, that's. I think. Well, maybe you will do it in the next months and years. But it will be interesting, I think, to see if the let's say if the mouse moves slower, then the reward will be kind of affected. So less reward or. But I think it's on your roadmap.
It's in the pipes. Yeah, but yeah.
Thank you. That's very interesting. So thank you again, Thomas, for your talk. And I would then proceed with our second and last talk for this session. Our next speaker is Mostafa Safai, and he will. He's recently finished his PhD. So congratulations. In David Robb's lab in Marseille, so next to Thomas. And during his PhD, Mostafa studied embodied strategies for timing and the contribution of the dorsal striatum to those strategies. And his presentation is the second part of his PhD work. And very soon he will join Juan Gallego's lab at Imperial College in London as a postdoc to study motor skills and the role of cortical striatal pathway. So good luck with the postdoc and good luck with the talk. So the floor is yours.
All right. Thank you, Alberto. Can you hear me?
Yes.
Thank you. Thank you for the introduction. Today I will present part of my PhD work about the dorsal striatum's role in energizing motor routines. But before getting to it, maybe first it's better to review the current hypotheses in the field about the role of the dorsal striatum. Generally, there are two hypotheses. One is action selection, proposing that the direct pathway promotes an appropriate action, while the indirect pathway of the basal ganglia suppresses competing ones. For instance, in this example, we can see that both direct and indirect pathway activity increases right before a motor sequence. An alternative idea is that direct and indirect pathways bidirectionally control the speed of movement. For instance, in this example, on the left panel, we can see that direct pathway stimulation increases locomotion, while indirect pathway stimulation decreases motor activity. But testing this hypothesis is a bit complicated because using neural manipulation techniques usually leads to what is called performance confound, meaning that if we see a performance loss, it could be either due to an impaired memory or selection mechanism with an intact execution ability, or it could be due to impaired execution ability with an intact memory or selection. And it's difficult to tell these two apart. So to do just that, we used several behavioral tasks that I'm going to explain. Here is a trained animal on a motorized treadmill. And the task is just to wait for 7 seconds before approaching the reward. If the animal approaches the reward too early, there's going to be a penalty and no reward. If too late, there's going to be a smaller reward. And what majority of animals develop is what we call this wait and run routine, which includes starting from the front, waiting more or less immobile until the treadmill carries them to the back, as we just saw, and then accelerating forward and crossing the treadmill to get the reward. So this is like the typical trajectory that we see in each trial, starting from the front, waiting while the treadmill carries them, and then running forward and outrunning the treadmill. So now the question is what is the contribution of the striatum to this particular routine, what we call the wait and run routine? And those two hypotheses predict different phenomena. If it's about speed control, we would expect different speeds in the acceleration phase of the routine. And if it's about action selection, we expect a kind of a different sequence of actions during the task. So our experimental setup, our experimental design is here. So we trained animals for at least 30 days, making sure that their performance is stable, and then we lesion different parts of the dorsal striatum, dorsolateral striatum, dorsomedial striatum, and eventually the entire dorsal striatum. We waited 2 weeks for the recovery, and then we retrained the animals, and finally we perform histology to verify the location of the lesion, and also we quantified the volumetric size of the lesion. Here's an example session. On the left, we see the session right before lesion, and the blue traces show routine trials, and we see that the animal mostly uses the routine. Immediately after the lesion in the middle, we see that the animal is more or less trying to do the same, but sometimes it starts running maybe too early, but after a couple of more sessions, the animal continues doing basically the same strategy and solving the task similarly. And this is in an animal with a huge complete striatal lesion. At the group level, with the large number of animals in each group, we can see that in terms of entrance time at the top and percentage of routine on the bottom, both DLS and DMS animals are basically unaffected. So after the lesion, they perform the task similarly. However, in the group with largest lesions, the DS group, we see a transient effect immediately after the lesion, but animals tend to recover after a few more sessions. However, if you look at the speed, and by speed, I mean the speed with which the animals outrun the treadmill, we see a big, robust, and irreversible effect in all the groups. And interestingly, this effect, the reduction in the speed, correlates very well with the size of the lesion. So, so far I showed you that after striatal lesion, overall performance in the task is spared. However, speed was irreversibly reduced. But there was also a peculiar transient effect in the DS group. Now, one might argue that this could be due to a loss of routine, which is followed by relearning the routine using a striatal independent system. So to test just that, we used the modified version of the task, identical to the original task. The only difference is that the treadmill moves toward the reward instead of away from it. So what this means is that all the animal needs to do is just to go to the back of the treadmill and sit while the treadmill transports it to the reward. So it could be performed basically with a very compromised motor system as well. And that's the behavior that we see animal develop. So during the inter-trial, they go to the back of the treadmill and they just sit while the treadmill transports them to the front. So in this video, the animal is taking the reward from the previous trial. And then when the reward is finished, he moves slowly to the back of the treadmill and just sits there while the treadmill carries him to the reward. So again, this new routine, which is very similar to the original routine, what is run and wait, and here indicated in blue. Before the lesion, most of the trials animal is using this routine. And interestingly, even after the striatal lesion, the animal is still capable of performing this routine, even in the very first session. And at the group level, in 9 animals, they still perform the same routine after striatal lesion. So this, the first argument does not seem to be the case. So another alternative is that maybe this is also due to the speed deficit that we saw, meaning that in the first sessions after the lesion, animals had a bigger speed deficit that recovered a little bit afterwards, not completely. So to understand better the origin of this speed deficit, we consider different possibilities. It could be due to a reward-seeking deficit or a basic locomotion problem, or maybe animals just cannot run at fast speeds, or maybe they cannot control their locomotion speed, or for the sake of argument, it could be due to the two-week break after the lesion surgery. Today, I don't have time to present the last two, but let's quickly look at the first 3 possibilities. We recorded the licking behavior of animals before lesion and after lesion, and we can see that it's more or less similar. The number of licks and also the frequency of licks is not affected after the lesion. So reward seeking seems to be intact. Also, if you put the animal in a novel environment and record their locomotion, both control and lesion animals seem to have similar similar amount of exploration, which suggests the basic locomotor activity is also unaffected. And if you force the animals without any reward or anything, just we force them to run on the treadmill with increasing speeds, lesion animals can keep up, although maybe they tend to be a little bit slower, but they can keep up with much faster speeds. So none of these explanations seems to be the case. So we think that the most parsimonious explanation of our data is that animals actually preferred running at a slower speed. And this is in line with this great paper in Parkinsonian patients, where authors show that movements with a lower energy expenditure are favored, although a repertoire of normal movements is available. So Stefania, who is a computational neuroscientist in the lab, we use optimal control theory to find the optimal strategy in our task. I don't have time to go through the modeling part, but basically she showed that increasing the effort sensitivity in the motor, or the sensitivity to energy expenditure, causes the animals to start running earlier. So the red trajectories in this plot. So they wait less and have a reduced maximum position. And this was something that we had noticed in our data. Here, if you compare before and after lesion, just the median trajectories, we can see that not only animals after lesion are slower, indicated by the slope of the trajectory, but also they start running earlier. So we looked for this in our database, and indeed we found that post-lesion animals tend to have a shorter maximum positions, meaning that they start running earlier. And this is also an effect that is not reversible. No matter how much we train them after lesion, they still tend to do this. And also, this effect correlates very well with the size of their lesion. And although this effect is small, but if we just look at the absolute value of maximum position in all of our database, so in more than 100 lesioned animals, we can see that this effect is still significant. So in conclusion, I hope I showed convincing evidence that the striatal lesions did not prevent execution of a learned motor routine. However, they increased the sensitivity to energy expenditure or effort, while preserving locomotion speed modulation, preserving locomotion speed range, and reward-seeking behavior. And if you're interested in this work, I just summarized this paper that was recently published, and you can have a look to see more analysis and more data. And I'd like to also thank all the members of the team, David, my supervisor, and especially Teresa and Estefania, my two co-first authors in that paper. Thank you.
Thank you very much, Mostafa, for your nice presentation. And I see some similar background in this last group picture and the one from Thomas, and also some common topics, of course, in your presentation. So we have already two questions. The first one is from Josefa. Nice talk. Could you give me more experimental details on how to measure the volume of the lesion?
Mm-hmm. Yeah, so we do immunohistochemistry on coronal sections, and then in each section we outline manually the striatum and also the lesion, and considering the rostrocaudal distance of those sections, we can estimate the size of the lesion and size of the striatum by approximating it basically by having imagining a truncated cone basically between each two consecutive sections. And the values that I showed you is just the ratio of lesion size versus over striatum size.
Okay, thank you. Then we have another question from Faiz. I might miss part of your talk. Is the treadmill run at a constant speed across trials or at different speed?
Yeah, it's always constant at 10 centimeters per second. But in this presentation, everything that I talked about, the speed of the treadmill is constant and it's 10 centimeters per second.
I see. I think having a variable speed could have been another confounding factor that could make things more difficult than they already are.
Well, we have also data on that, and it's on the other part of the work that is more concerned about timing mechanisms. And in that part, it's also published if you're interested. We do play with the speed, and we vary speed between trials to see how animals can adapt their timing performance. But here, that would be a confounding factor. So it's always the same.
Thank you very much. And then I see that among our attendees, we have Manuel who raised his hand, but I don't see a question from him. Okay. Okay, so I think that I would suggest to reach out to our speakers if you have further question or if you want to continue the discussion. And I really want to thank you, Mostafa and Thomas, for their wonderful talk. and all the attendees that have been present here today, and also Sophia, that has been our backend host for this session. So thank you again for being here, and enjoy the rest of NeuroMatch 3.0. Bye, everyone.
Yeah, thank you. Bye.
For the viewers to populate, so you can see a bunch of people have entered in now, and Christos is in the audience, Ali, so you can pull Christos in as a panelist, and I don't see Ben. Hello, Christos.
Hello, nice to see you all.
Yeah, nice to see you. Are you calling in from Crete?
Yes, from Greece. Actually, now I'm in Athens, but I started.
Okay. Nice, great. So the room is populating. While it's populating, I'm just going to introduce myself in the session, and then we'll get started. So hey everyone, I'm Adam Steele. I'm a postdoc at Dartmouth College in Hanover, New Hampshire, USA. I'm going to give a few more moments for people to trickle in. So I'll use that time to tell everyone in the United States to make a plan to vote. If you've already got a plan to vote or you've already voted, please call a friend and make sure they have a plan. And if you're not in the US or you can't vote in the US elections, why don't you call one of your US colleagues and make sure that they have a plan, because it's a super important moment for us. So today in this session, we've got a great lineup of speakers who are going to be presenting three interesting talks on the intersection of neuroscience and philosophy, and perhaps what philosophy can, how philosophy can inform theoretical and experimental work. So this is an interactive talk session. So our speakers are going to give a 5-minute presentation to get the conversation going, and then leave 10 minutes for audience discussions and questions. You can post in the chat or in the Q&A if you'd like to come on stage, or if you don't, just put attach to your comment a comment about whether you'd like to come on or not, and we'll make sure you get up if you would like to. Make sure if you post in the chat that you have your chats set to panelists and attendees, so that way everyone knows what you're saying. Because this is an interactive session, it'd be great if everyone can introduce themselves, so that way you know who's in the room. So why don't you just chat, hey, what your name is and where you're calling in from, so that way everyone can know who's here. You can post questions at any time, upvote your favorites, and for those of you who are on Twitter, please tweet about this session using the hashtag NMC3. So our first talk is going to be given by Aman Patel, an undergraduate at the University of Southern California. I'm really excited for his talk. It's got a very provocative title, A New Computational Theory of Intelligence. So Aman, you can start sharing your screen and take it away.
Thanks. Let me figure out how to share the screen. All right, there we go. And then actually, while we go through this, I can actually, I'll put the questions for feedback at the end. So yeah, as Adam said, my name is Aman. I'm an undergraduate at USC. And yeah, I know that the title is a little bit gimmicky. Really what I'm trying to do is propose a slight modification to, our current understanding of how intelligence works at the computational level. So the main hypothesis or premise of this view is that most cognitive processes can be viewed as associating input patterns with output patterns, and that this associative process is equivalent to modeling unknown rules or relationships. And so a quick snapshot of the grounding for this premise, we can see here that there are some typical processes that are considered to be integral parts of cognition, like perception and reasoning, and that these can be viewed as simply connecting patterns of input to patterns of output. So for perception, for example, we're simply connecting input patterns from multiple senses to output patterns of other senses and internal models of the world. And for reasoning, we're simply associating input patterns of premises to output patterns of conclusions. And so what we're doing when we're learning these processes is modeling the relationship between those inputs and those outputs. And this might work for other cognitive processes too, like episodic memory or working memory, even though those might be more specific in the types of input patterns and output patterns that go into it. So we can take a brief example of how we learn addition. So when we first learned to add in kindergarten or earlier, we're shown methods for solving the problems, like counting on fingers. You know, if you're told to add 2 plus 1, you count on your fingers 2 and then 1. And so this is a motor method for solving this problem. What we're basically doing is learning that procedural process to do that modeling and to do that mapping. And then as we do this, we memorize a table of addition that 5 plus 7 equals 13, and or that 12, and things like that. And that constitutes, you know, a semantic memory table, basically, which we memorize through the same process of input and output, but it's more direct. And then as we go on, we can learn or invent more algorithms for using this memorized table for adding multiple more complicated numbers together. And these, again, are just memorizing the semantic or semantically memorizing the algorithms for that. And then the important part of all of this is that these are all modeling processes, linking those input patterns of the addends to the output pattern of the sum. And then so if we accept this, the basic process of intelligence would be a method of mapping those input patterns to those output patterns. And importantly, it would have to be tweakable for different purposes and functions, depending on which cognitive process it's part of. And so biological neurons do this in their own way. So every neuron, as you guys all know, it associates, you know, semi-specific patterns of its input firing with its own output. And you know, our understanding of how neurons work backs this up with Hebbian learning, spike timing-dependent plasticity, and didactic organization. And then, you know, evidence for neural backpropagation also might help these neurons associate their input firing patterns to patterns of their own outputs. And then if you have a microcolumn or an ensemble of these neurons that all share the same input, we can associate patterns of the input neurons to patterns of output neurons firing instead of just input neurons to one neuron. And then importantly, this isn't the only way to do this modeling from input to output. Associating this input to output is really just a matter of calculating probability, the probability of an output pattern occurring for each input pattern. So you can do this in a Bayesian method or a frequentist method. And it could also be in other schemes of computation that might not be observed biologically. Like, I'm not sure if you can see this diagram here, but the idea is that if you have your input neurons, but instead of directly exciting or inhibiting the neuron in question, what they're doing is, or what the neuron in question is doing is trying to mimic this other associate neuron here and model the rule or relationship between the input neurons and this associate neuron. And either way, what matters is that this method of calculating probability or of trying to associate those output patterns with the input patterns should be tunable for different situations. And so then how do we go back from this neural computation back to cognition? So we know that natural selection has tweaked the parameters and connectivity of neurons in different areas of the brain to carry out functions that are useful to survival in our natural environments. So we have some models that are pre-built, like fear responses. When we're born, we already know to associate, you know, certain dangerous patterns of markings on animals with a fear response. But a lot of these models we have to learn for ourselves, like object permanence. We learn as we become older. Same with fine motor control, and obviously our semantic knowledge. And what's important is that the parameters of the neurons in these specific areas and the connectivity between them are tuned for these specific functions. So basically, the moral of the story is that cognitive processes can be viewed as modeling processes, mapping input to output, and that collections of neurons can carry out this process through multiple different ways, including the way we see in biology. And to recreate this in machines, for example, we could let evolution take the wheel and create those models that way. And then, of course, evolutionary algorithms from the artificial intelligence side are often constrained by computation limits, and we might overcome these by breaking down cognition into components. So again, that was just a very, very brief overview of a very speculative and theoretical view, and it would be great to have questions and comments about this, and feedback on whether how you think this could be tested empirically or perhaps simulated.
Thanks, Aman. That was a really definitely an interesting theory. I'm really excited to discuss it with you. For everyone in the audience, please post any comments and questions in the chat or in the Q&A, and we'll bring you on stage. I wanted to go back to your slide where you list all of a number of different examples of cognitive processes. So I think it's really interesting that you've kind of discretized these different cognitive things. One thing that I have been thinking about is how difficult it is to really extract these as independent processes, and how episodic memory or semantic learning, for example, might be feeding back and influencing your perception, right? So with all these cognitive processes, you have these elements in what I would consider to be intelligent systems, elements of recursion among the processes, and also elements of recursion among the biological substrate. So with your example of addition, for instance, if we scale that up we can take a very one potential way of explaining how you go from the ability to do addition, which you can do on your fingers, to the ability to do calculus, for example, is having a system that has recursion to some extent that allows it to monitor the processes that are actually computing arcs and trajectories, which we have as like our reaching system. That's a system that's built to do this thing. And we have another system perhaps that's able to consciously monitor it and realize that it can pre-compute this trajectory, and now we can pre-compute other trajectories. So I'm wondering how you would build this type of recursion into your schema of intelligence, or whether it's already there.
Yeah, so like an important part to realize is that these different processes, their inputs and outputs feed into each other. So for example, your process of perception, whatever internal world model you have as a result of it, that can get fed into your process of reasoning as a premise, and then you can use that to infer conclusions. And so basically, I'm imagining that as we learn through experience, we're basically able to find patterns in what we already know and extend that to new knowledge. So basically, as you said, building up our understanding of calculus, right? Mm-hmm. We could do that by taking what we already know here and adding on top of it with either through learning from like symbolic language, being told what to do, and memorizing algorithms for doing that calculus, and also basically just from working with the problems ourselves and developing our own internal methods of solving those problems. Yeah,
I guess it'd be interesting to, if you go to your next diagram, where you begin to, your flow chart here, it'd be interesting to start building in some of these like feedback loops that you're talking about. I think as you expand what your theory of intelligence is, and one of your questions being how to actually implement this in a computer simulation or something like that, I think trying to build in more of this recursion might become key to understanding to building an actual model of what intelligence looks like. So we have Jules Brachard has posted a question. Jules, if you can post in the chat, if you'd like to come on stage, we can invite you. Or if you'd like to just talk and not actually come on stage with your video, that's also good. He's fine with text only. Okay, so in the Q&A tab, Jules has asked, you said that tuning could occur through natural selection. Can your theory also account for learning through the course of one's life? What would tune the network during learning across the lifespan of an organism or a computer? And then this question is going to be your last one, unfortunately, because we have to move on to the next talk.
Yeah, but yeah, that's a great question. So yeah, it can account for learning through the course of one's life. So basically, as we learn, what we're doing is building those models ourselves. And what natural selection is doing is just taking those parameters and tuning them so that we can optimally build those models in different spaces. So for example, let's say we're learning how to like run, for example, or walk. Obviously, this is not a built-in process. We have to learn it. But what natural selection has done, it has created in our brain a specific space and a region that is tuned for learning how to do this. So it already has the input and output connections from the relevant areas, our kinesthetic senses and your motor neurons. And from that, because that area is primed to do so, it will be able to learn that model as the human gets more experience. And then basically, so if we have natural selection, it's turning the levers for what kinds of cognitive processes each area of the brain can do and what they're related to. And as we learn, we're just filling those in with the actual data.
Cool, really interesting. So Jules has responded in the chat. Aman, you also have another Q&A question from Richard Lang in the Q&A tab. So we're going to move on to the next talk, but you can continue the conversation in those two places if you'd like.
All right, thank you.
Yeah, thank you. That was a really interesting talk. So our next speaker is Christos Sakaris. His talk, I apologize if I've said your name incorrectly. Christos, you can correct me.
No worries, no worries. It's Tsagaris, almost correct.
I'll take almost. His talk is titled Aristotle as a Neuroscientist, the Power of Habit and the Science of the Metron.
Metron, yes, another Greek word, which I will explain shortly. First of all, thank you for the floor, and thank you to Aman for this very interesting presentation. In this presentation, I will try to take you a bit back in time, and we will talk about Aristotle as a neuroscience, his contribution in neuroscience with a focus on habit. My name is Christos, as already mentioned, and I'm a medical student at the University of Crete in the Faculty of Medicine. First of all, we need to be at the same page, and to do that, we need to know how the world of Aristotle looked like. And it was a world with many disadvantages, like he wasn't able to perform anatomical studies on humans, only on animals. Of course, he didn't have plenty of equipment for experimentation, let alone imaging or microscopic techniques. And he was fenestrated by the so-called humoral theory, a theory in which blood biles, yellow and black bile and phlegm would dominate the human body, and their equilibrium would define health and any condition, any physical and any mental condition. However, there were some advantages in this situation, and it was that Aristotle was allowed to be at the same time at a diverse field of science. He could write and conduct research at the same time in medicine, in anatomy, and biology. And this is why he has some works called Perison Morion, which means about animals. It's a biological work. And at the same time, he could work on ethics. And this is why he has a work about ethikanikomachia. This means it is about virtue and about ethics in individual and civic level. And of course, he had plentiful resources of comparative anatomy because don't forget that he was the teacher of Alexander the Great. And while Alexander was conquering the world, he was sending to him any strange animal or plant he would find. So what we have in the world and in the perception of Aristotle, we have the so-called cardiocentric perception. So he believes that the brain is not the brain, but the heart. Indeed, the brain is something like a cooler, a thermoregulator. But he has something similar to the brain, which is located to the heart, and this is psych. Psych is the root of psychotherapy, psychiatry, and so on, and it's the soul. And he has a lot of works that focus on this from different aspects. What about the psyche, or the new brain, the heart in his perception? It is divided in three compartments: the vegetative, the sensitive, and the rational. The vegetative is only about sustaining ourselves. It's not significant. However, the rational and the sensitive is about thinking, becoming not only better people, but also better citizens, and this is very important. And this is why the overlap of rational and sensitive part of the soul makes the mind. And in the mind, we have the so-called ethical virtues, or what we know as ethics in Aristotle. How can somebody reach virtue? According to his definition, virtue is a settled disposition of the mind, determining the actions and emotions of a person and consisting essentially in the observance of the mean relative to us. The mean relative to us has been defined as the metron. This is the metron of the mediocrity or moderation. And it means that we need to be brave, but we need to be brave with moderation, otherwise we will be fooled. And this goes for any kind of virtue. So in Aristotle, we start from a reasonable perception of a virtue. I need to be brave because this is necessary for my city. I need to be knowledgeable because this is necessary for my self-development. And this reasonable concept leads to repetition, leading to pleasure or misery. The more virtuous we are in bravery, for example, the more courageous we are at war. Or the more virtuous we are in terms of knowledge, the more eager we are to learn. And this repeatability is called ethos and leads to ethos. Ethos is telos, and telos is the scope, the purpose of this habituation. And it is, of course, in accordance to moderation. And finally, it leads to eudaimonia. Eudaimonia means happiness. So somebody decides on a reasonable basis to be virtuous in order to be happiness at a personal and at a collective level. And what does this have to do with memory? In modern neuroscience, we have this division of declarative and non-declarative, conscious and unconscious memory. And when it comes to habit, because arete, virtue is habit, in modern neuroscience, it's something non-declarative, something unconscious, and belongs to procedural memory. And it is the striatum that has to do with this. But in Aristotle, we have a somehow different model in which we can involve the cortex because there is reasoning at the first step and conscious decisions. We can involve the cerebellum because we have repetition, so we have patterns called axes in Aristotle, and we also have the limbic system, which mediates the pleasure that we get from being virtuous. A very modern and popular science, even among management, about habit is the habit loop. In this sense, we have cues, positive, neutral, or negatives, that lead to action, to repetitive action, and this leads to the establishment of habit. However, these cues are more about sentiment and less about reasoning. And when it comes to the pathophysiology of obsession, we still have more areas of the prefrontal cortex of the limbic system being involved, but yet the reason that we have the pathophysiology in an Aristotelic point of view is that the mean is lost, and we have obsession instead of habit. What can Aristotle offer? His vision about virtue was civic virtue. It means that we cultivate arete, we cultivate virtues in the context of a city for our own sake and for the sake of the people who live at the same community. And this is something very important to Greece, where we had city-states that wanted to be self-sufficient. So everybody would have to be reasonable, and on a reasonable concept build on his own virtues in order to build a strong city. What can we understand from this today? That we have huge countries and the cities that are not self-sufficient. We have to collaborate from science to trade to everything. Aristotle is shifting the balance from implicit to explicit memory. So we need to investigate more the overlap between declarative and non-declarative processes in the acquisition of habit. The second is that there is an emphasis on social neuroscience. We study virtue because it is a component of the ideal life in the polis, in the society. And the third one is the multidisciplinary approach. We have at the same table ethics and neuroscience. This is something that can help us a lot. Especially today that we start from mice, we have studies on people. We try to have translational science and neuroscience, but we can take it at the level of the city, at the level of the society. And this is very interesting with regard to new prospects of research, such as the brain on a chip. And how can we simulate not only the neuronal circuits, but also the sense of being part of a society in this. In the antiquity, this discussion and your questions would take place at the first image. Unfortunately, this is what remains in Athens of the first image. However, we're all here, and this agorevin bulletin means who wants to speak, and I'm open to your questions. And of course, after this, I would also be happy to contact with you for more questions or collaboration or whatever. Thank you very much once more. And some references.
All right, Christos, thank you very much. That was a really great talk, especially for someone like myself who's not super hasn't been exposed much to Aristotelian philosophy. I think it was really a great primer. So we've got time for questions. So if you've got questions or comments, please post them in the chat or in the Q&A. I guess I was really interested in what you kind of ended on, which is the idea of how society is being, how this relates to society. I think it's very interesting, this idea about perhaps societal memory and societal habits. So kind of borrowing from the macroeconomics, where people say like, oh, at like an individual level, we can't really predict behavior very well, but like at the global level, we are able to predict the behavior very well. That almost seems like a cultural habit, if you will, if we are able to predict like in response to something, you know, this is how society will respond. Do you have any thoughts on that in this in your framework?
Yes. Actually, to be honest, the trigger of this presentation and of this discussion about Aristotle started in my first years when I had neurophysiology, and we had a lot of studying about experiments on mice or functional imaging, and everything was about nuclei that communicate with each other and establish connections with chemical or electrical transmission. However, in many cases, we really forget that all this happen in a society. Aristotle would say that people cannot live on their own. People are social beings. And I thought that we neglect in the way that we conduct research the fact that everything is a matter of social interaction. And I believe that modern neuroscience should take this into account, because most of the research I'm seeing is about this nucleus connecting to the other one and a protein or a neurotrophin supporting this, which is amazing, but we need to have the bigger picture at the back of our minds.
Cool. Ben has a question. So Ben, you can feel free to unmute.
Yeah, thanks, Christos, for the great talk on some Aristotle background, which is useful for me because I'm going to mention him anyway. I had a question about the levels of soul. So you mentioned you had that slide with the nutritive and the sensitive and the reasoning, two of which I think were related to ethos and in particular like human ethics, and so eudaimonia for us and human virtues. And in my memory of Aristotle, one thing that the reasoning element was what really distinguished in his view in De Anima humans from other animals. So I'm wondering how you see the virtue ethical component as tied up with the sensitive and kind of powers of locomotion and sensation vis-a-vis powers of reason. So do we get the ethical picture? Yeah, more generally about the relationship between virtue ethics for humans and then Aristotle's view of the psyche of animals.
Oh, wow. Thank you very much for this question. And it seems that you know very well the Aristotelian view of the soul. My reading and my view comes mostly from the Ethics Nikomachia, Ηθικά Nikomachia, where indeed he argues that logistikon, the reasoning part of the soul, is definitely the most important and the most superior. However, there is a distinction between virtue. We have ethical virtues which combine sensitive and reasoning in the sense that we will have to feel something about practicing these virtues, and we will also have a moral impulse to behave this way. And this is why we have ethos and ethos. And on the other hand, we have the so-called intellectual virtue, in which only the reasoning participates. So yes, actually, ethical virtue
great answer. Thanks.
here is not the top of virtue. The top of virtue is intellectual virtue, which is moderated only by the reasoning part of the psyche.
Great. So we have to move on. You did have another question pop up in the Q&A, Christos. So if you want to address that there, that would be great. It's from Douglas. So you'll see that when you open up the tab. So thank you again for that talk. Our last talk of this session is from Ben Baker, postdoc working with Conrad Courting at the University of Pennsylvania. When I asked Ben if there was anything he wanted me to mention, he said that he's a dancer and is interested in applying neuroscience tools to the study of dance. Today, he is going to give a talk about philosophy, though titled Neuroscience Needs Philosophy to Understand Representations. So thanks, Ben. You can take it away.
Thank you. All right, I will share my screen here. Let's see if this works. All right. So yeah, I slightly rejiggering of the title to make it a little bit less polemical here. I'm acting in my role as philosopher critic of neuro, but I guess keep in mind that I'm an aspiring neuroscientist myself, and I take you all to be philosophers yourselves as well. So yeah, and thanks again to another collaborator in Recording Lab, Ben Lansdell, who I'm working on this paper with, and Conrad, and my PhD supervisors. I just finished my PhD in philosophy, so they had a lot of influence on my views here. So just to set the stage a little bit, the point of this presentation is supposed to address what I take to be some messy semantics in neuroscience, basically a lack of kind of a clear theory governing the use of certain key terms. So I have here, maybe I can use my, laser pointer. So yeah, information, code, computation, representation. I'm especially going to be concerned with representation. You don't have to take my word for it on the messy semantics. I'm just going to hide behind Conrad and Brett, who kind of make a similar claim about we need to clean up these terms. So just a first pass, very broad look at how philosophers have thought about representation and representationalism. There's lots of disagreement, but what can encompass most of philosophers who talk about this is understanding representation as something that's defined to have intentional content. This is often glossed as aboutness or directedness. Representations come in different types or modes. And these often highlight these features of representation. So for instance, a map of pen represents pen as something to be navigated. So this is kind of a mode of representation, a map-like mode, you could say. Pen is the object that you're trying to represent. And then similarly for a painting of pen represents it differently, an utterance of pen represents it differently. Okay, and so the broad view that in some sense mind and mental processes are to be understood in terms of representation, I'm going to call representationalism, goes way back. So I'm just going to do a little bit of an overview. First, just to characterize the puzzle that's associated with this set of family of theories, we want to know what determines the content of a representation. If we say some mental process involves representing pen, what determines that it represents pen per se? This can be easier for other kinds of representations like language. We can rely on conventions. For art, maybe we can rely on the intentions of the artist or the consumers. But here we're trying to explain cognition itself. So what sets the content for cognitive or subcognitive states? Some closely related problem is the possibility of error. Essentially, if you're trying to determine the content, you're trying to determine when the content is right and when the content is wrong. In that states like beliefs, perceptions, plans, states that we think of as intentional states in philosophy, they can be false, they can be inaccurate, they can err. Representations more generally are like this. That's thus the explanatory value of appealing to representations is the sort of basic motivation. So just some quick historical highlights of representationalism showing up in philosophy. We have Aristotle. I mentioned De Anima. It was fresh on my mind. That's why I had that response to Christoph. So neat about Aristotle that is he has a pretty explicit example to point out what we would call an isomorphism. So the way the wax receives the form of a signet ring pressed into it is the way that the organ receives the form. That is, there are sensible forms out there in the world for Aristotle. They impinge upon the organs in this isomorphic way, and that's essential to his view of perception. Samkhya Yoga, I just want to note, is interesting because it's a physicalist approach to mind. So that is, it's got these three components that we can go into later if we want: manas, ahamkara, and buddhi. And they're all constituted by different kinds of vrittis, i.e. changes in prakriti, which is the material side of a material-immaterial distinction in Samkhya Yoga. Moving on to the medieval period, we have Avicenna and Averroes, two really influential philosophers from that period, influenced a lot of the early modern West. Notably, the Latin intentio is taken to be a translation from this Arabic term mana, which figures centrally in their theories. And they offer an immaterialist picture where you've got, almost a grammar of mana states that relate in some way that they try to explain to a material outer world. Going forward to the early modern West, you have more precise versions of a similar idea, especially Descartes, who had very precise kind of anatomical diagrams of the eye and the optic system, and offered theories about these mediating states between the material world and what is ultimately a immaterial internal kind of power of reason. But we've got a lot of this kind of isomorphism within mechanisms in the nervous system for Descartes. And he has this analogy of wind through the pipes that mediate between an organist's fingers and the sound. Quick, just make sure we're on the right page here, restate some basic points. We can sideline the overall metaphysical pictures that these different representationalist views fit into. Aristotle has this soul body composite view. Samkhya, as I mentioned, is a physicalist view. The Arabic and European views are non-physicalist views of mind. What these all have in common is this idea of states that are directed at or about things. And in some sense, those are going to be used to explain things like seeing something that isn't there or having a misperception. And overall point here is that it's going to take more than measured correlations between neural activity and more than information per se to determine representation in this philosophical sense of representation. So as versions of representationalism today in philosophy generally appeal to some notion of function. And I'll highlight the main one, but there's a couple of versions of this. Just to get the intuition going, the thought is the heart has the function to circulate blood and it malfunctions when it fails to do this. So you've got this distinction between the proper case and the inappropriate case. And if we, along similar lines, analyze neuronal activity as having a particular function, let's say to carry information about some stimulus, call that a representation, then we can derive from a notion of malfunction cases of misrepresentation. This is importantly going to rule out a lot of things that activity carries information about. Not all of that information content is representational content, would be one way to put it, in the same way that not all of the causal properties of a heart are its proper function. Just highlighting the first of these, so there's some disagreement about what sort of function you could use to specify representation. One prominent is teleological views. So here we have the telos from ancient Greek, actually, meaning purpose or goal. Here's some citations for this view, but essentially what you're trying to answer is what a component is supposed to do. Like, let's say some population of neurons that can fire at rate n or rate m. You're saying it's supposed to fire at one of those, and you're going to appeal to evolution or learning or some goal-oriented structure in order to specify how to decompose functions. And then here's some other approaches we can talk about if we want. Within teleological views, there are two main approaches: a backwards-looking ideological theory. What is the history of some part that has a function? We're going to answer what is that thing's function by appeal to what it was selected for, in a notion of selection that means natural selection over evolution, or we have a nice paper by Garson recently talking about selection in terms of the retention of synapses in populations of neurons. So selection at the scale of an individual learner. There's some challenges for this approach. We can talk about those. The alternative forward-looking teleological notion of function relies basically on a non-reductive characterization of goal-oriented systems to start, something that you know when you see it. People will disagree about the hard boundary cases. You can formalize what it is to be a goal-oriented system in dynamical systems terms. People have tried to do that. Of course, there's disagreement about whether it can handle all kinds of these hard cases. But anyway, both of these give you the payoff, which is that you can use this philosophical framework about function to get functions to carry information or functions to represent, in short, and thus relying on this function malfunction distinction to actually have a view of misrepresentation, which is philosophers have thought is really important to a view of representation. If you can't explain misrepresentation, then something is missing. And then in future work, we want to kind of nail this down by giving a teleological interpretation of some recent research that uses whole brain recordings in C. elegans and also apply it to the deep neural net framework of modeling intelligent behavior, which very explicitly relies on learning goals and tries to focus less on representations. So that's another thing we're thinking about. So yeah, with that, I guess I will open it up for questions.
Great, that was a great talk. We've got two questions that I want to get to. Actually, a few more coming in. So Richard Lang.
Stop sharing. How do I do that? There, I got it. Sorry.
You got it. Okay, I'll read the questions anyway because we want them on the recording. So Richard Lang has asked, what is the link between intentionality as aboutness and being as for something? Can a representation about X be without, can a representation be about X without being for a particular action?
So on the teleological approaches to function, no. It doesn't have to be for carrying information about X per se, although I think that's the most popular way to gloss this in philosophy. But my understanding is that a representation, that's kind of what we're looking for, is suppose we think intuitively that this state in the brain is a representation of X because we found some correlation. Needing some more theoretical background to say what makes the content X rather than any number of other things it's also correlated with, you can appeal to ? I'm inserting here the teleological approach. So appeal to some notion of goal-orientedness or selection. The alternative notions of function that I didn't really get into, maybe I'll just do this quickly. Are we on time? Okay, we're okay. Well, actually, no, let me not do that. Sorry. The alternative notion of function, the main alternative notion of function in philosophy that's popular right now is people are called the new mechanists. It's a mechanistic approach to function where the interest of the investigator sets what we take to be a mechanism that we're interested in. So you might be interested, for instance, in the heart as a mechanism for producing a sound. Forget the fact that it circulates blood. We're just interested in its capacity to produce a certain sound, in which case you can decompose it into parts insofar as they contribute to that sound making. And so in that case, you're still going to have a for, but that is, the part is still going to be for something related to sound making, but that is set by us as investigators rather than by some notion of the goal-orientedness of the organism or what it's learning towards or how it's been selected. Yeah.
Cool. We've got another question here that's gotten a few upvotes from Sander Van Bray. If all these philosophical accounts have in common is that representations are about something, and that's essentially how neuroscience uses it, neural activity X is about Y, is there really an issue?
So the issue as I see it is understanding what makes X about Y. So neuroscientists might disagree. They might offer alternative models about, that part X that's carrying information about Y, and it's actually carrying even more information about Z, but we think Y is functionally relevant and Z isn't. And so we hypothesize that it's about Y. Just because we think so, great. I mean, fine, you can operate on the basis of reasonable, educated guesses, but if you want a more fleshed out theoretical framework, teleological notion of function is supposed to do that for you.
Yeah, I think that's a great answer. I've seen some interesting data recently about how motion information is available throughout the visual system. And yet we have specific areas that we think are functionally relevant for motion. So how do you say that although there's information there, what are these regions actually for? So I think that's posing the problem really well. We have time for one more. We have time for one more quick answer. Ava is asking, could you go further into the application in deep neural networks?
Sure, I'll try to do this quickly. I'm thinking of a couple papers, one by Richards et al. That Blake Richards that says our framework should operate, rather than focusing on representations, we should focus on learning goals, learning architecture, I'm actually going to forget the third one, but what's important is that learning goals are a part of the framework, and that's kind of the locus of this teleological theory. So that's kind of a point at which you could say, okay, does the investigator just get to say what the learning goal of a system is, or do we need some more systematic way of saying what kinds of artificial systems, actual systems are goal-oriented, and if so, what determines the goal such that we can then look into the components and say, okay, because the goal is self-maintenance and getting food, then we can interpret this as a food detector. If instead we don't think that that's what the artificial network is doing, that it's learning on something else, then that's going to change our representational hypotheses. So we're keeping representation in the picture, but making it derivative on this kind of goal-oriented structure that I think is sympathetic with the DNN-based approach.
Cool. So we had another question come in from Julian Colomb, but unfortunately, we need to adjourn. So I want to thank again all three speakers for fantastic talks. It was definitely really interesting stuff. And I would encourage everyone to find them on Twitter if you want to keep the conversation going. So thank you again all for coming. And we hope. Okay, let me get my windows configured here. All right, so I'm going to get started. So hey everyone, I'm Adam Steele, a postdoc at Dartmouth College in Hanover, New Hampshire, USA. I've been told that we have a few moments to allow people to trickle in, so I'll use that time to say for everyone in the US, have a plan to vote. If you have a plan already, call somebody else to make sure they have a plan. And if you're not in the US or you can't vote in the US elections, why don't you go ahead and call one of your US colleagues and make sure that they have a plan to vote, because it's extremely important. So we've got 3 great talks in this session about motor behavior and motor control. And I'm really looking forward to hearing all of them. I think it's going to be a great session. As a reminder, we have the chat where you can post messages and clarification questions. Just make sure that you have your messages set to go to panelists and attendees, so that way we can all hear and see what you are saying. If you'd like to introduce yourself in the chat, now is a great time to do that. Just post your name and where you're from, so that way we can see who's here. We also have the Q&A tab for questions. You can post questions at any time during the talks and upvote your favorites, and we'll ask them live. For those on Twitter, please tweet about this session using the hashtag NMC3. So for our first talk, we have Amit Yaron, a postdoc at the National Center of Neurology and Physiology in Tokyo, Japan. And he's going to give a talk with the provocative title, Are Primates Just Big Frogs? Forelimb force direction and amplitudes are independently controlled by spinal motor modules. So Amit, you can take it away.
Okay, so in this work, me and my colleague in Kazuhiko Seki's lab wanted to find out whether the motor control in primates is modular in a similar way as in the bullfrogs. So motor control is a complicated task. So how the central nervous system overcomes the complexity of multi-joint and multi-muscle control is a fundamental and open question in neuroscience. And one of the ways that people thought about how it can be solved is by modular organization. So a limited number of output modules in the spinal cord would control different but overlapping sets of muscles and joints. This will decrease the number of variables directly controlled by the cerebral cortex. And by recruiting different modules and simultaneously but independently, the CNS can achieve flexibility of behaviors at a lower computational cost. So in this famous paper from Nilo Bitti's lab from 1994, they try to check this hypothesis using bullfrogs. So they put microelectrodes in the spinal cord of the bullfrog and recorded the force transduced from the hind limb. So they put the frog's leg in 9 different positions. In each position, they recorded the forces when stimulating different areas of the spinal cord. And these are the forces that were recorded in this example, in these 9 different spots. And they interpolated the entire force between these points. So this is the force field for this experiment. So here's an example of a force field that was measured after stimulating in point A. And this is a force field that was measured when stimulated in another point. So you can see that the direction of the forces is quite different between these 2 points. And now what they did is stimulate in both points in the same time. And what they got was very similar to what you would expect from a linear combination of the response to electrode A alone and electrode B alone. So here, the similarity between the expected and the co-stimulation is very high, 0.967. And here's another example where the similarity was lower. So here, the similarity between the observed and the expected was only 0.77. And actually, the observed was more similar to just point D. So this is a case of winner takes all. But the most common case in 87.8% of the cases was a high similarity between observed and expected, close above 0.9 similarity. This is confirming to the hypothesis of modularity, where two modules can be combined in a linear method, in a linear way. So here the similarity is both in direction and also in strength of the response. What we wanted to see if similar things happen in the macaque. So we implanted the electrodes in the spinal cord of the macaque and did a similar experiment where we placed the hand in 7 different locations, recording the force output of X and Y in each location. We also recorded EMG of different masses, but I don't have time to talk about these results. And what we saw was quite similar to the results in the frog. So here is the one example of stimulation in one location. Stimulation in the second location. And what we expect from a linear combination of the two. And the actual observed. So what we can see here is very high similarity between what we expect from a linear combination of the responses to A and to B and the co-stimulation result. And here the similarity is 0.91, which is higher than similarity to any of the others, of each one individually. And in the whole population, we see similarity of 0.1%, and 77% of the cases, we have a higher similarity than 0.1. So these results are quite similar to what we see in the frog, meaning linearity in the direction of the response. But this is only in direction. What we see when we look at the how strong is the response, the magnitude of the response. So this is one example where here is the response to A, here is the response to B, and this is the expected result. But the observed result that we see is actually this. So the direction is what we would expect, but the magnitude is much larger. And in the overall population, we see about 4.7 times the magnitude of what we would expect by linear sum. When we looked at the individual masses, we saw a bit more complex story, but for this I don't have time to explain. But in general, the more proximal masses show closer to a linear response. So the take-home messages are a confirmation of the modular output in non-human primates, similar to what was found in the frogs. However, unlike the frog and rodent, the magnitude of force vectors was greater than a simple sum, supralinear. So while the force direction in primates is controlled by the linear sum of modular output, force amplitude might be adjusted by additional sources shared by those models. So if you want to know more, our paper is just out in PNAS. So please ask questions. Thank you.
All right, thank you. Thank you, Amit. That was a very, very interesting talk, really comprehensive work, I think. So we have plenty of time for questions if people have. We've got one coming in the chat from Brian Corneal. Great talk, Amit. Can you speak briefly to where you think your stimulating electrodes were in the spinal cord? For example, did you target the ventral horn?
Yes, so we use the stimulation in different locations in the spinal cord in different depths, and we saw different results in different depths. So there was closer to the ventral horn, we saw more linear magnitudes also. So, we talk about it more in the paper.
So I think you've got a little bit of time to explain my question, which was what you make of this proximal versus distal modulation by force, because that seemed like a really interesting result. Was that something that was similar to what was seen in the frog, or is this?
In the frog, in general, they just saw a linearity, so they didn't really measure the different masses, or they did, but they didn't talk about it in the paper. So the explanation, I'm really not entirely sure what it is. And I don't have a good explanation.
Okay, interesting. Do you have any, I guess, any speculation? It seems like one of the main differences between primates and frogs is going to be the dexterity and cortical control of the wrists and fingers. So maybe that has something to do with it. I don't know much about spinal cord physiology myself, but so I'd be happy to hear your any explanation you might have.
Yeah, it might have to do with the dexterity, but yeah, I'm not really sure.
Too early to say.
Yeah, I'm sorry.
No, it's no problem. Again, it's really interesting work. We'll give another moment for just for any questions to come in. If you have any for Amit, you can also post in the chat. He'll be able to monitor the chat if you have any comments coming up. In the meantime, we can prepare our second speaker. So our second talk is by Sarah Kearsley. She's a master's student at Western University. She can be found on Twitter at Kearsley Sarah. And her talk is titled Bilateral Stimulus Locked Responses in Upper Forelimb Muscles During Visually Guided Reaches. So thank you, Sarah, and we're really looking forward to this talk.
There we go. Okay, so am I good to go now?
Yep, you're good to go.
Okay, awesome. Thank you. Good morning or afternoon, depending on where you are. Thank you for coming to my talk. I'm Sarah. I'm a first-year master's student, and today I'm going to be presenting the work from my undergraduate thesis project about rapid visual motor responses in the upper limb muscles during a bilateral choice reaching task. We make visually guided reaches every day, such as when reaching to pick up a TV remote. It takes time to integrate the information about the visual stimulus, such as its size and location, to initiate a contextually appropriate motor response. It takes approximately 250 to 400 milliseconds to initiate one of these responses, which is fast, but I'm interested in situations where we might not have that much time. In these situations, like the one the picture was just in, we can get visual information to the muscle very quickly, at times that are approaching the minimal afferent and efferent conduction delays. I'm interested in what pathways underlie these rapid visual motor transformations. This question is complex given the pathways involved in visual and motor control. So here we're looking at some of the pathways involved in processing the visual image, reaching control, and eye movement control. Interestingly, there's this common node, the superior colliculus, in both of these pathways, and I'll actually be telling you how it's implicated in reaching too. The superior colliculus is a phylogenetically old midbrain structure involved in orienting movements and rapid eye movements, otherwise known as saccades. It's been studied extensively in regards to saccades, and I'm going to talk a bit more about its activity because it becomes relevant for reaching. So if we record from the intermediate layers of the superior colliculus during a task where a saccade is required to a newly appearing visual stimulus, we see three distinct types of neurons. There are neurons which show a purely visual response, time-locked to the onset of the visual target. There are neurons which show a motor burst, that is neural activity associated with the saccadic eye movement. And then there are these visual motor neurons. These neurons show both the visual burst and the motor burst of neural activity. If we look at the activity of these neurons across many trials, we can clearly see the time-locked bursts of the visual activity occurring around 100 milliseconds, followed by the saccade-related bursts. As the saccadic reaction times become shorter, these bursts become closer together. This gives rise to bimodal peaking, the first peak associated with the visual response, and second with the motor. When these peaks merge into one, we get what are called express saccades. Express saccades are visually guided saccades occurring around 100 milliseconds towards the visual target. The superior colliculus's ability to mediate these rapid visually guided saccades make us think it may be involved in other rapid visual motor responses. The superior colliculus sends both the visual and motor information down to areas in the reticular formation for eye movements. More than just this, it sends to areas involved in head movements and arm movements. And from here, the information goes bilaterally. In line with this, if we stimulate the colliculus, we actually get contralateral and ipsilateral arm movements. But what happens to the visual information at these other premotor centers? This brings me to the stimulus-locked response. If we record from the pectoralis major, a muscle involved in cross-body reaches, we can look at how the muscle is responding across time during reaches to a newly appearing visual stimulus. Lower muscle activity is indicated by blue, with higher indicated by yellow. And we can see that the first wave of muscle recruitment actually occurs around 100 milliseconds. This is the stimulus-locked response. If we look across many reaches to a newly appearing visual stimulus, we can see that although the reach reaction time varies, shown by the black dots, this first wave of muscle recruitment consistently occurs around 100 milliseconds. Properties of the stimulus-locked response have been shown through other studies to actually be very similar to properties of the visual response within the superior colliculus. So there's an accumulation of evidence suggesting that this response is mediated by the superior colliculus via the tectoreticulospinal tract. For my project, I wanted to further investigate the actual involvement of the reticulospinal tract. Stimulation studies and anatomical studies have shown that a key feature of the reticulospinal tract is that it projects bilaterally to the upper limb muscles. So I predicted that in a task where either arm could reach to intercept the visual target, the response would appear bilaterally regardless of which arm was chosen. To test this, we collected data from 15 healthy participants. Participants were seated in the KinArm endpoint robot, holding onto 2 robotic manipulandums. The task was displayed on a screen horizontal to their chest level, with their precise hand locations displayed on the screen. Throughout the reaching task, we recorded muscle activity bilaterally from the pectoralis major, the muscle involved in the crossbody reaches. Participants completed a bilateral hand choice emerging target paradigm. The emerging target paradigm has previously been used in a unilateral reaching task to reliably elicit the stimulus-locked response. We modified this paradigm to allow for reaches from either hand. Participants were instructed to initiate each trial by moving their hands into the white dots on the screen and looking at the notch in the barrier. Once their hands were in the dots, a target would appear at the top and move down to behind the barrier. It then re-emerged below at one of 7 possible locations. Participants were instructed to wait until it re-emerged and then reach as fast as they could with either hand to intercept the target. We collected 200 reaches to each target location, resulting in 1,400 reaches for each participant. Here, we're looking at the percent of right hand reaches as a function of target location. Not surprisingly, for the targets furthest to the right, the participant always reached with their right hand. And for the targets furthest to the left, they always reached with their left hand. But for targets that were closer to center, there was actually a mix of which hand reached. We were able to use the proportion of right arm reaches to make a psychometric function and find the point where 50% of reaches would be made by each hand. From here, we found the actual location with approximately an even number of reaches. We did this for each participant. This location was really interesting to us because we could look at what was happening in the right pectoralis major when the right arm was chosen to reach, but also what was happening in that same muscle when the left arm was chosen to reach to the exact same visual target. We could also look between muscles what was happening with it throughout a given trial. So here we see that when the right arm performed the reach, and if we're looking at the right pectoralis major, although the reach reaction time varied, we still get this initial wave of muscle recruitment occurring around 100 milliseconds. So we see that this version of the emerging target paradigm still does evoke the stimulus-locked response in the reaching arm. But more than just that, we could look on these exact same trials what was happening in the left pectoralis major. And what we found was that we still get this initial wave of muscle recruitment occurring around 100 milliseconds. Thus, we see the stimulus-locked response in both the left and right pectoralis major, even though it was the right arm that was chosen to reach. Further, we could look at what was happening within a muscle based on which arm was reaching. So if we're looking at average muscle activity throughout time, we can see that for the left pectoralis major, when the left arm reached, we get this initial burst of muscle activity, followed by sustained increased activity. Further, when the right arm reached within this exact same muscle, we see a very similar initial burst, followed by minimal muscle activity. The same pattern is seen in the right pectoralis major, with the sustained activity for the right arm reaching. Thus, we can clearly see the stimulus-locked response appears bilaterally, regardless of which arm is reaching. We were further able to look at qualities of this response, such as its magnitude and latency, based on whether the arm was chosen or not chosen to reach. And so what we found was that the response was actually about 20% larger when the arm was chosen to reach. Here we're showing the within muscle values for when that arm was chosen to reach and not chosen. Using a paired t-test, we also found that the response occurred about 4 milliseconds earlier when the arm was chosen. But this is a bit more inconsistent across participants. So we found that the stimulus-locked response does present bilaterally regardless of arm choice, supporting reticulospinal tract involvement in the response. Further, on the chosen arm, the response was a bit larger and tended to occur a bit earlier. Most importantly, this first wave of muscle recruitment during these rapid reaches is bilateral during the stimulus-locked response interval, but then rapidly gives way to lateralized recruitment favoring the chosen arm. I think it'd be interesting in the future to look at the pathways underlying this initial burst of muscle activity in animal models and further in clinical populations. I would like to thank the various members of the Cornell Lab and the various funding sources for this project. Thank you.
All right, thank you, Sarah. That was a great talk and super, super clear. So I'm really, yeah, I think it's great work. So I had a few questions. We also have plenty of time if anyone else has questions. I'll defer to the audience first. Joran Smeets has said the effect of the chosen arm must be based on a prior. For instance, the choice in the previous trial. Did you check for that? So how much did one trial influence the subsequent trial?
I haven't looked at that yet, actually, but I did want to look at that because I do think like if you reach with the right arm 3 times in a row, that likely does influence the next one. But because for this outside trials, you always get the reaches with the closest hand, I do think that they are taking in the information from the trials, but that will be interesting to look at in the future.
Great. Yeah, that's an interesting point. So I am going to ask my question. If you can go back to the time course of activation, muscle activation for the 2 arms. What it looked like to me was that there, actually you can see it in both. There's the the peak at the stimulus locked response, and then there's a subsequent peak in that about 150 to 175 millisecond range.
Yeah.
Both in the arm that's reaching, more so in the left, there's kind of 3 peaks, but in the right, there's just like the second peak and rise. But there's also in the arm that's not reaching, you see 2 peaks. I was wondering if you could talk a little bit about what that might mean to you.
Yeah, so this actually follows with previous work that was done looking at the stimulus locked response. So there's a paper by Wood et al. 2015, and they found that there's an oscillatory behavior that's at about 15 hertz that actually falls in line with what you'd see from the reticulospinal tract. So we think that this has to do with that oscillatory activity. And yeah, so it's.
So just to follow up on that, is it then that when the reach is being made, is it necessary for both pectoralis muscles to contract to stabilize the trunk to make the reach? And that's why, like, at the initial point of the reach, you would have these, or is that not the case, that actually this is a product of the colliculus being only delivering bilateral responses, so it not being hemi-specific? Does that make sense?
Yeah, so I don't think this has to do with postural stability, because if you look, the response is like very large, like it's half of the size to almost the size of the actual voluntary activity. So I think that it's just basically like, because the colliculus does orienting and stuff like that, that you're just like, it's the first initial wave of preparatory activity for it, and then after that it gives way to the lateralized reach.
Great. So that's really, yeah, I think it's a great answer. We've got another question in the Q&A from Ivan, who says, "Hi, Sarah, super clear talk. Congrats. I was wondering whether the effect was due to some kind of motor overflow or because of a stabilization strategy caused by a slight torso rotation." So this is similar to my question. But also adds this concept of muscle overflow. Do you have any ideas about that?
I'm honestly not sure. I'm not sure about that one. Sorry, I'll have to think more about that.
That's no worries. And you can always pick it up in the chat with Ivan if you guys want to discuss further, because I think it's an interesting point. So I think that unless there's another quick question that somebody wants to ask, we can move on to our final talk of the session from Maria Jantz from the University of Pittsburgh. She is going to be presenting her talk titled "Optimizing Spinal Cord Stimulation for Bladder Control Using Evoked Nerve and Muscle Responses." So Maria, you can take it away.
Awesome, thanks. As he said, I'm Maria Jantz. I'm at the University of Pittsburgh with Dr. Robert Gaunt, and I study the effect of epidural spinal cord stimulation on the lower urinary tract. So bladder control may not be the focus of this particular conference, but I think it's important to understand the implications of losing it before we move on into this talk. Bladder control is something that has a huge impact on your lifestyle. You might not have to think about it every day, but the things that you don't think about are always the things that are hardest to lose. So if you think, for example, about like going on vacation and having to try to figure out where bathrooms are all the time, carrying sterile catheters anywhere you go, this is a real struggle. I'll use lower urinary tract dysfunction can come from a number of sources. One of them would be spinal cord injury. Restoration of bladder control is consistently ranked as the first or second priority by people with spinal cord injuries. There are also disorders like overactive bladder, which affects 1 in 8 people, so it's quite common, and can lead to things like poor sleep, as well as avoidance of activities and travel, because bathrooms are maybe not available. So completely restoring effective function requires 2 parts. You have to restore both continence and voiding in order to have complete functional bladder control. There are a couple of ways that people currently try to intervene for bladder control. Catheters are one of them, but maintaining sterility is really difficult in order to avoid infection. If you have compromised hand function, it's difficult to insert a catheter, and it's just not comfortable. If you think about trying to insert a catheter, say 6 to 8 times a day, that's not something you want to do. It leads to scarring. So current healthcare guidelines actually aim to minimize catheter use. And despite all of these problems with catheters, their clean intermittent catheterization is actually the gold standard in this area right now. So there's a lot of work to be done. There are also some pharmaceutical options, but those of course come with their own side effects. And there's a third option, which is what I'm interested in, and that's neuromodulation in order to interface with the neural control of the bladder. So in order to get at how we're going to interface here, I'm going to give you a quick background in the sensory motor control of the bladder, focusing here on the pelvic and pudendal nerves shown in this illustration, which are critical to bladder control. They're both innervated from the sacral spinal cord. I'm simplifying this diagram a bit. We're working in a cat model, and that's what's illustrated here. But you can think broadly of the pelvic nerve as supplying the bladder itself. So the efferents of the pelvic nerve contract the bladder, the afferents convey bladder sensation, while the pudendal nerve efferents contract the external urethral sphincter, and the afferents convey genital sensation. And pudendal nerve afferent activity, activating those afferents can also allow you to access reflex loops for both continence and voiding, those functions that we're looking for. So in order to produce activity in these nerves, we'd like to use epidural spinal cord stimulation, which is used widely for chronic back pain in something like 50,000 people per year. And more recently has been used in spinal cord injury patients for things like locomotion as well as bladder control. And so in order to access the nerves of the lower urinary tract that I showed you on the last slide, we're using these sacral spinal cord placements here. And we're also using high density arrays. So we just have a lot of potential locations where we can stimulate. There are two main effects of epidural spinal cord stimulation that we're looking at, and I'll show data for both of these in a moment. The first one is to see the nerve responses, so we can activate bladder afferent pathways. And the second one is looking for changes in function in both continence and voiding. So we're eliciting both of those bladder reflexes, and we're measuring those functional changes as bladder pressure. So our goal here is then to relate these two these two response types, this SCS evoked nerve responses to the function or bladder pressure changes that we're producing. We want to see, we're curious if we can predict functional outcomes from just the neural activity. Because we know that we can produce reflexes and nerve activation. We don't know the exact relationship between the two of those. There's a second reason that this is useful, which is that we're using these high density arrays, and that means that there are different possible responses at every electrode for 40 to 96 electrodes. And it's much faster to test neural activation than bladder pressure changes. So from a clinical perspective, this is a quick way to find a good stimulation location. So this is a rough outline of our instrumentation. We're doing, of course, epidural spinal cord stimulation on the sacral cord and cauda equina in anesthetized cats. And then we're recording on these lower urinary tract nerves, the pelvic nerve, the pudendal nerve and its branches, and the sciatic nerve to measure off-target effects, so like lower limb movement that we might be causing. Also EMGs to measure muscle activity in places like the external urethral sphincter. And we're recording bladder pressure with just a bladder catheter. So we're looking at this relationship between evoked nerve activity and lower urinary tract reflexes. So we're going to look first at an example of lower urinary tract afferent activity that we're able to evoke. So this is a stimulation triggered average of the nerve activity that we're evoking. In this gray bar is the stimulation window. And we're taking the window following stimulation of each of these stimulus pulses of a stimulus train applied at 3 to 33 hertz frequencies, and averaging all of these windows together. So in this example, pudendal nerve cuff activity, you can see this large initial response, as well as some of this later activity in this boxed area here. So we expect some simple predictors of bladder pressure. We expect the pudendal nerve afferents are involved in both voiding and continence reflexes, so we would expect that nerve to be active during any good functional response. The pelvic nerve is likely active if we're able to produce bladder contractions. And the external urethral sphincter EMG is likely, if it's actively contracting, it's likely associated with continence or a guarding reflex. So what do these functional responses that we're able to evoke actually look like? These are some bladder pressure recordings that we're looking at. We've got several trials overlaid for each of these, all from one cat. So the blue here indicates a voiding trial, and the green here indicates a continence trial throughout the talk. It's very typical in neuromodulation of the lower urinary tract to have a higher frequency evoke a voiding response and a lower frequency evoke a continence response, even on the same electrodes that you're stimulating. So note these background contractions ongoing. That's very typical in the bladder at rest. And then you can see this nice bladder contraction, this voiding response that we're able to evoke, as well as this cessation of background contractions, this continence-like reaction that we're able to evoke. So we're able to produce both of these components of bladder control with spinal cord stimulation. Just in case you're concerned that our lives are too easy, this also doesn't work sometimes. So these are some examples of poor function at either of these frequencies. So we've got some poor function examples where, again, we have the background contractions. Something happens here, but it's not either voiding or continence-like. And then we have examples where there was just no function evoked. So we're curious then if we can predict these types of functional outcomes from just the neural activity, both voiding versus continence, as well as good function versus poor function. We're going to look at this by extracting features from the muscle and nerve cuff recordings. And we'll use these features first independently to predict based on each feature individually, and then to combine them into a feature vector in order to predict based on all of the features of all the nerves and muscles. So a couple of the time and amplitude features that we extracted here are things like time of the maximum amplitude, peak to peak amplitude, and time of the response, those sorts of things, as well as mean absolute values of 2 millisecond windows, just to get a sense for the evolution of the response over time. So I've done this in several animals. Because we're short on time, I'm just going to have us looking at one here. Peak to peak amplitudes are a straightforward measure of just how much of a response you're getting. So in this example here, this is the pudendal nerve. I've plotted the amplitude of the peak to peak response on the pudendal nerve during trials classified as voiding in blue, continence in green, poor function and no function. And if you'll recall, we would have expected the pudendal nerve to be active during any good functional response. And you can see to a certain extent that that's true, that there's generally less pudendal nerve activation in the poor and no function examples and more in the continence and voiding examples. And you can also see in this example that we have higher pudendal nerve activation in continence than in voiding. So that seems like a promising indicator for our ability to separate these things out. However, this example by itself, this feature is not enough to fully predict the kinds of functions that we're getting. So let's look at the pelvic nerve and the external urethral sphincter. These are roughly sorted from most to least separable, but of course, even the most separable example is not enough to classify on its own. So in the pelvic nerve here, you would expect the pelvic nerve to be very active during voiding. This does sort of appear to be true, but you can see here that there's quite a lot of pelvic nerve activity in many of these other cases, certainly not enough to classify based on this feature alone. If you look at external urethral sphincter EMG, note that this one is in terms of max amplitude rather than peak to peak amplitude, just because the EMG signals are rectified here. So we would expect the external urethral sphincter to be very involved in continence. And this is honestly even less helpful of a feature to indicate what kind of trial we're getting. It's very hard to separate out any of these values. So there's a key takeaway here that all of our expected predictors by themselves don't appear to be enough to predict the kind of function that we're getting. These single features are not enough. So I've just shown these examples of 3 points out of 128 features total across 10 different channels that we're using to do this prediction. This is too many to deal with, and there is a likely relationship between many of these features. So since we expect some shared structure and we don't want to try to visualize in 128D, we have combined all of these features into one feature vector for each of the trials, and we're using dimensionality reduction to identify a common structure and look for some separation. So looking here, we have used a principal component analysis for dimensionality reduction to generate this space. You can see visually that there's some separation between the continence group, the voiding group, and the poor and no function groups. As it turns out, It's fairly easy to classify differences between this poor function and these good function examples. Those things separate fairly easily. Although you can see visually that these different types of function are separated from each other, those do turn out to be a bit more difficult to separate out, to classify. So, in conclusion here, we have been able to use epidural spinal cord stimulation to recruit our afferents of the lower urinary tract and produce all of the bladder functions necessary for effective bladder control. We also have found some simple features of neural activity, which have some ability in some cases to predict functional outcomes, but it's very limited. And none of those features are effective on their own. We can produce then our different we can predict our functional outcomes with these combined features of nerve and muscle activity. And we'd like to use those to determine the best locations for stimulation. A huge caveat here is that this example shows data that I've manually labeled and it's in a single animal. And so our next step here is to find out how much of this space is common between animals and pull out, try to highlight some of the examples of different features that are most effective for predicting these different responses. So this is work that a lot of people have been involved in. I would definitely not be here without them. I want to especially highlight Chaitanya, Ritesh, and Rob, who have been involved in overnight experiments and a lot of talking through ideas, and I'm really lucky to get to work with them, as well as our IT staff and our animal care staff, and of course our funding organizations. Thank you. Any questions?
All right, that was a great talk and a super important area of research. So you definitely don't need to convince me. I thought that was really, really great. So we do have plenty of time for questions if people want to post in the chat or in the Q&A. In the meantime, I'll just say that I was really glad that you looked at did a PCA or some kind of dimensionality reduction across all the features, because I was expecting that it would take a suite of features, especially based on Amit's talk with the spinal cord, where you saw that there were many muscles that are kind of working in coordination. So I was wondering if you could speak a little bit more about what the combination of features are that your PCA is picking up on, either for the classification of success versus not success, and then in that what you said was the trickier contrast between the two different successful trial types.
Yeah, absolutely. So there are some things, one thing that was surprising is that EMG activity is not very predictive. We have several different muscles that we're recording, and that turned out to be less predictive than some of our nerve responses, which is particularly surprising.
Sorry, I was just gonna ask, do you think that that's because there's more noise in the EMG, or is that for some?
That's entirely
plausible? And then I'll let you finish. I'm sorry, I didn't mean to cut you off, but I was very surprised that it was a little bit counterintuitive.
It's very counterintuitive. I attribute it partly to noise in the EMG. I mean, EMGs are just harder to keep in place consistently, so that certainly is relevant to that. But I would expect, especially the external urethral sphincter EMG, to be much more predictive than it is.
Yeah.
So that was definitely kind of a surprise. One of the interesting things about doing dimensionality reduction on this was pulling out some of the features that I didn't expect to be very predictive, and they turned out to be. There are also several time-related features. So I mentioned that I had those mean absolute value windows. And so if you look at about like 8 to 10 milliseconds into the response, a lot of like high activity there on a couple of the nerves turns out to be quite predictive as well. So that was very interesting.
That is interesting. So we have a question from Jean who says, thank you for your talk. Would EMG/nerve cuff be a viable option in a clinical setting?
Yeah, that's a fantastic question. So one of the reasons that we're trying to push, we've done a lot of work in the past focusing on nerve cuffs, but that's very, very difficult in a human clinical setting. And so one of the reasons that we're trying to push towards EMG, and one of the reasons I would love to see some features of EMG that are a bit more predictive, is that EMGs are much more effective in a clinical setting. Certainly not super comfortable, but much more plausible as a testing method.
Great. So that is all of the time that we have for this session. I want to thank our panelists again for 3 fascinating talks, all very clear and wonderful work. So round of applause from me. And I want to thank everyone for listening, and we hope that you tune into some more sessions from NeuroMatch 3. So thanks, everyone.
Ah, yes.
Yeah, it's
Two
slowly
more.
increasing.
Yeah.
Sorry. Paola, I would suggest we wait for 2 more minutes and then we will start, right?
Yes.
Because still the number is increasing so that not many people miss, but also to not lose too much time. I have 4:01 right now, so I think we could wait.
It's only 1 minute past 4, yes.
Yeah. Exactly. Okay. I would like to welcome you all on behalf of the organizers of NeuroMatch 3.0. I'm happy that you joined us for this keynote lecture from Paola Bezzi. You can see the title and the presentation already, but I would like to take a short opportunity to introduce her. Paola studied biology in Pavia in Italy and did her PhD in Milano in pharmacology at the University of Milan, and then went for a postdoc to Switzerland, to Lausanne, where she stayed further on, and she is still an affiliation to the University of Lausanne, as you can see, but she's now an associate professor also at Sapienza University in Rome. And as you can see, her major focus is on astrocytes, and she will talk on the relationship to mental disorders in this time. But I think you did much more on the role of astrocytes in different functionalities. Thank you, Paola, for accepting the invitation, and the floor is yours.
Okay, thank you. Thank you very much, Rute, for this nice presentation. So I would like to thank the organizers, in particular Tora, that invited me and giving me the opportunity to present this new data. Part are new, part are also published about the astrocytic, let's say, VMAT2 in pathological, let's say, condition. So let me see if it works. Okay. So this first slide is just to tell you that we will talk a lot about the self-grooming today. And actually the self-grooming, as you can see, is an innate behavior, as you can see, as you know, that is involved in hygiene maintenance and also in other physiological processes, such as, for example, social communication or the arousal. And actually, as you can see here, this spontaneous behavior that usually occurs in the transition between, let's say, the period of rest and the period of activity, it is represented across most animal species, including humans. And this is because the self-grooming is actually remarkably similar across species in several, let's say, taxa. And the self-grooming is one of the most frequently observed behavior in awake rodents. And as you can see here, as a pattern sequential organization with characteristic cephalocaudal progression, in the sense that they start, the mouse or the rodent start with the head, they groom at first, then it's followed by the body region, and then finally with the urogenital region and tail. And this behavior was really well characterized, and actually it seems, a lot of papers, let's say, suggest that the pattern regulating signals originating from the brain can organize this physical complex movement. And actually, there are a lot of brain areas that are involved, such as, for example, cortical region or brainstem, or also striatum. And let me add also that, let's say, rodent self-grooming is now actively recognized as sort of, let's say, suitable behavior in order to study the neuronal circuit that underline this complex behavior. And actually it can be also particularly important in some psychiatric disorders, especially the ones that are characterized with a lot of repetitive behavior. Actually, in the human, self-grooming can be also pathological. For example, during the stressful condition or in obsessive-compulsive disorder or in obsessive-compulsive spectrum disorder that are characterized with excessive grooming behavior. The OCD is highly heterogeneous as a pathology, and it occurs in about 2–3% of the population. And as you can see here, actually is associated with persistent obsessive thoughts, with repetitive behavior or repetitive ritual that we call as a compulsion, and also it is also associated with a lot of anxiety. And all of these symptoms can significantly impair the social activity. The heterogeneity of the obsessive compulsive disorder is related to various types of obsession or compulsion, or also various types of comorbid conditions associated with it. And actually, there are a lot of, let's say, as I already said, I already mentioned, the obsessive-compulsive spectrum disorders, such as Tourette syndrome or trichotillomania, some others, that can share many features of obsessive-compulsive disorder, particularly the acquisition of the association, let's say, with repetitive behavior. And the neurobiological basis of obsessive-compulsive disorder is still partially unclear in terms of neuronal circuits that are involved, or also in terms of neuromodulators that are involved in the OCD. Let's say, for the neuronal circuit, a lot of neuroimaging studies that have been performed in patients support this model. So they support the corticostriato-thalamo-cortical loop. In this model, we think that an abnormal loop between this area play a critical role in the onset of symptoms associated with obsessive compulsive disorder, and again, especially related to repetitive behavior. And actually, many papers have been, many studies have been done in, let's say, preclinical studies, so have been done in mice model, and actually they provide insights, important insights in the relationship between the striatum dysfunction and the abnormal OCD behavior. But actually, it is still unknown whether other, let's say, upstream cortical region can somehow, let's say, can somehow be important in generating this particularly repetitive behavior. And in particular, we don't know if this upstream cortical region can somehow, let's say, generate the striatum abnormalities that are associated with repetitive behavior. And for example, a lot of studies have shown recently that the prefrontal cortex can play a major role in this model. Actually, the prefrontal cortex is quite important because many patients have shown that a sort of hyperactivity or hypoactivity in a particular region of the prefrontal cortex that is called the orbitofrontal cortex. And in particular, the hyperactivity has been associated with symptoms provocation, or has been associated with a sort of correlation with the severity of obsessions. Moreover, the persistence of this sort of maladaptive patterns of inflexible thoughts or inflexible behavior can indicate a, let's say, a lack of or a dysfunction in cognitive flexibility. The cognitive flexibility actually is a cognitive process that is particularly associated with the prefrontal cortex. Again, here there are a lot of preclinical studies in mice model that have confirmed the possible role of prefrontal cortex in the OCD, and in particular, this study that has been published in Science paper in the Science have shown that optogenetic stimulation of the pathway from orbitofrontal to the striatum is sufficient to generate the OCD-like behavior. So in terms of the neuromodulators that are involved, there are a lot of studies on serotoninergic pathway, just because the serotonin uptake inhibitors seems to work very well in at least a part of patients. But actually, it has been shown that about 30% of these patients actually are not, doesn't answer, let's say, to this to the serotonin reuptake, and actually it seems that antipsychotic that are working in the dopaminergic, let's say, pathway are can, let's say, be beneficial in these OCD patients. So we can say that that actually, even despite this information about the role, the possible role of prefrontal cortex and the possible role of dopamine, whether the prefrontal cortex dopaminergic dysfunction are associated in the pathophysiology of OCD is still unknown. And actually, we were particularly intrigued by this lack of information, because a few years ago, we found that the astrocytes located in the frontal part of the cortex, and in particular in, as I say, including, let's say, in the prefrontal cortex, have a sort of particular unique features of dopaminergic glial cells. This what does it mean? It means that these astrocytes are responsible for regulating dopamine homeostasis in these brain regions. So now I'm going to present some data about this, and because it is important to understand why we thought thought, let's say, that this model could be relevant for the OCT. So at that time, we were curious to understand, or let's say, yeah, to decipher whether the astrocytes were able to, let's say, to play a role in the dopamine homeostasis. And actually, we focused on the prefrontal cortex because we don't, in the literature, we don't have a lot of information about the mechanism, the cellular mechanism that are able to, let's say, to regulate this dopamine homeostasis. So what we did, we started this project by doing a FACS sorting in astrocytes. So we isolated astrocytes from a GFP CFP mice that you can see here. And this, in these mice, the astrocytes are expressed in CFP under the promoter of GFP. So we isolated the cells, and then we performed the RT-PCR analysis. And actually, we were interested in checking the presence of bona fide, let's say, genes involved in the synthesis, uptake, storage, and the degradation of dopamine. So here you can see that we found the OCT3, which is a plasma membrane transporter. We found the VMAT2, which is a vesicular transporter located in the cytoplasm. We found the MAO-B, which is enzyme involved in the degradation, but we couldn't find any expression, mRNA level of TH, which is a tyrosine hydroxylase, and it is the enzymes involved in the production of dopamine. We also found, then we checked the presence of the protein by immunohistochemistry, and actually here we can see the OCT3 that is expressed mainly in the soma of the GS positive astrocytes. Here we can see the high expression of a MAO-B with the mitochondrial protein, but again, we couldn't find any signal of the TH in the astrocyte. So TH is only in axonal, in axons. Basically, these results were suggesting that astrocytes have plasma membrane transporter, they have the enzyme able to degrade dopamine, but they are not able to produce dopamine. So then we focus on the VMAT2 because these vesicular transporters in neuron is expressed in vesicles, in synaptic vesicles, and of course can regulate the homeostasis not only of dopamine but of all monoamines. Here we can see the signal of VMAT2. VMAT2 was expressed very well in the cell body, but also in the big processes and in the small processes, both in mouse and in rat. But what was particularly interesting is that the VMAT2 signal was expressed only in the astrocytes located in the frontal cortex, including, as I said, the prefrontal. And actually in other dopaminergic areas, such as, for instance, in the striatum or in the VTA, the signal of VMAT2 in the astrocyte was weak. As you can see here, we have a little bit of yellow of colocalization, but very little, or completely absent. So in the VTA, here we can see the VMAT2 in the cell body of neurons located in the VTA, but if we check the green astrocytes, we couldn't find any signal. So for us, the VTA was a sort of control area in our studies. So then we wanted to, of course, we were interested in defining whether the physiological role of, let's say, of astrocytic VMAT2, and actually we used a loss of function strategy to, let's say, to study the role of deficit in VMAT2 so let's say the impact of deficit of VMAT2 in the brain. So we use a Krelok system, and we crossbreed the human GFP-3-ERT2 with the VMAT2 flux mice, and then to induce the recombination, we treated the mice with the tamoxifen for 8 days from P20 to P28. Here we have some data just to tell you how we check that the deletion was correct. So we isolated astrocytes from control and our mutant mice, and here we can see that we couldn't find any mRNA level. We also check the VMAT2 with immunohistochemistry. Here is the normal situation where we can see the presence of VMAT2 in the astrocyte, but here in our mouse, we couldn't find any VMAT2 in the GS positive cells, but we still have some axons, of course, dopaminergic axon in this mouse, which is normal, let's say. Then we also check the signal of VMAT2 in the dopaminergic neurons of the VTA. We couldn't find any let's say any difference. And also when we performed the Western blot analysis, we found a decrease, about 30% of decrease in the VMAT2 protein, only in the prefrontal cortex and not the VTA. Then we were interested in understanding the role of this astrocyte VMAT2, and we started to check the competence of astrocytes in maintaining, let's say, the level of monoamine. So we started with tissue homogenates, and this is the HPLC, and actually we found a significant decrease only in dopamine and not in other catecholamines. And this was specific for the prefrontal cortex, as we couldn't find any reduction in the VTA. And actually, when we performed the microdialysis in vivo, we also found a decrease in the extracellular level of dopamine. So we, let's say, we concluded that the VMAT2 in the astrocytes can control at least 30% of the dopamine content and the dopamine, let's say, level in the extracellular space. We spent quite a lot of time, let's say more than a couple of years, try to define the mechanism by which the loss of VMAT2 in the astrocyte could reduce the level of dopamine. But now, I mean, I don't have time to go into much detail. So to keep the story short, at a certain point, we realized that in the prefrontal cortex, we had a decrease, a significant decrease in the dopamine, but also a significant increase in the DOPAC. DOPAC is a metabolite of dopamine. So we thought perhaps dopamine metabolism is involved in this decreased level of dopamine. So what we did a lot of experiments, but what we did in vivo was to inhibit two enzymes that are involved in the metabolism of dopamine during the development. One is the COMT, the catechol-O-methyltransferase. The other one is MAO-B. So we treated the animals with one inhibitor, which is a tolcapone, is inhibitor of COMT, and also with inhibitor of inhibitor of MAO-B, which is deprenyl. Here are the extracellular level that we measure with the microdialysis. As you can see in our mice, so the level are significantly different. But here you can see very well that only deprenyl, so the inhibitor of MAO-B, was able to increase the level of dopamine. And consistent with this data, we also found an increase in the activity of MAO-B. So to keep, as I said, the story short, we concluded that in general way, the metabolism of MAO-B was able to accounts for the low level of dopamine in our mice. Then we spent a lot of time to, let's say, to decipher the mechanism, but this is not important today. So that time we were interested in understanding the real role of VMAT2. So for this reason, we produced a lentivirus specifically targeted for astrocytes, so an astrocyte lentivirus expressing VMAT2. And we injected this lentivirus at P25, and actually then we did the characterization. As you can see, this lentivirus goes specifically into the astrocytes, and there is no expression of this virus in neurons. And then we performed the microdialysis and found that if we overexpress, let's say, VMAT2 into the astrocytes in our mouse, we were able to rescue the extracellular level of dopamine. Fine. So at that time, we were interested in understanding the physiological, let's say, role of VMAT2 in the astrocytes. And so for this, we checked the synaptic transmission in prefrontal cortex. And actually, we started with the extracellular field recordings, where we checked the, let's say, the basal synaptic activity we record, let's say, the basal synaptic activity in layer 5 by stimulating layer 2. As you can see in this input-output curve, here in green, we found that our mice, they displayed, let's say, in an increase in the basal activity. And then when we performed the pair-pulse ratio, we found that the pair-pulse facilitation was decreased in our mice, suggesting that we had a problem in the probability of a release. And actually, this was confirmed by the whole cell patch clamp recordings, where we measure the frequency of and the amplitude of MAPSCs. And actually, we found that in the layer 5 of the prefrontal cortex, our mice display an increase only in the frequency and not in the amplitude. So this means that we had an increased probability of release. So at that time, we set up two rescue protocol, one for checking the role of VMAT2 and the second one for checking the role of L-DOPA. So for checking the role of VMAT2, we injected lenti-VMAT2 at P25 and then we record at P40. And for checking, let's say, the role of the dopamine, we treated chronically our mice from P20 to P40 with L-DOPA. And of course, we control, we have control experiments where we have seen that these two treatments, let's say, were able to increase the level of dopamine in the prefrontal cortex. And basically, this is what we obtained. We obtained a very nice rescue, both with lenti-VMAT2 and with L-DOPA, as we can see here and here, but perhaps we can see much is more evident here with the frequency. So the chronic treatment with L-DOPA and or the infection with the lenti-VMAT2 only in the astrocyte was sufficient to rescue this phenotype. Then we moved in checking the impairment of cognitive function related to the prefrontal cortex. We checked the working memory with the T-maze delayed attention task, and we checked the behavioral flexibility. Actually, with the T-maze, we found, so in the T-maze, the mice has to learn to alternate, and when they reach the criterion, we put here, we close the door, we put a sort of delay. And as you can see here, our mice in green made many more errors when we put a 5-second and 20-second of delay, meaning that our mice had an impairment in the working memory. For behavioral flexibility, we used the two-choice order discriminant task, where the mice have to associate an odor with a reward. So they reach the criterion during the first day, then we repeated the same experiment the second day, and here you can see very well that our mice didn't have any problem in acquire, let's say, this criterion, but when we reversed the contingency, so we reversed the rules, let's say, our mice spent many more time, let's say, in other words, they needed many more trials to reach the criterion, meaning that our mice have a problem in behavioral flexibility. And actually, the same story as before, when we injected the lentivirus with P25 or we treated our mice, we could have a nice, let's say, amelioration of these, let's say, phenotypes. Keep in mind that this is not a real rescue in the sense that we prevent the pathology to occur because we treated at P25 from P20. Okay, so at that point, so to summarize what we obtained in the last work was that we have in the VMAT2 deficient mice, we have an increase in the basal activity, and we have also in the deficit in behavioral flexibility that can be, let's say, can be the phenotype that are reminiscent some physiological and cognitive, let's say, aspects of obsessive compulsive disorders. And we wanted to study at that point the physiological significance of VMAT2 in the OCD relevant behavior. And this is what we obtained. So actually our mice starting at 3 months of age started to develop a facial hair loss. Actually at 3 months is not a lot, but you can see here that they started to lose the hair here very close to the nose. And actually this, let's say, the penetrance of this phenotype increased with the age and affected all the transgenic mice, which develop a strong hair loss, as you can see here. At the age of 10 months, let's say they lost the hair and also the whiskers. And actually, what is also interesting to note is that this loss, this hair loss, were also observed in some control mice when we put the control mice together with these mice, as you can see here, thus suggesting that our mice not only have an excess of let's say auto-grooming, but they also have an excess of allo-grooming. In other words, so not only they have this auto-grooming, especially in the frontal part of the mouth, of the face, but also they are going to groom the other mice. Here is the quantification. You can see very well that they have here in green our mice. They have a more repetitive behavior related to the grooming, not for example for digging. The boats were significantly higher, and also the grooming time. So at that point, as these mice, let's say, show this compulsive-like behavior, we also use an open field and the elevated plasmase to check the anxiety-like behavior. As you can see here in the novel field, our mice, they have a sort of hippo locomotion, so the distance travel was just significant decrease. They also like to stay in the center of the arena, and this is a sign, typically is a sign of anxiety-like behavior. And this sign was then confirmed in the elevated plasmase, where they spent less time in the upper arms, and also where they let's say they have a latency to go into the open arena, so sorry, into the open arms, that is completely disrupted, so it is increased. So at that point, we wanted to determine the significance of VMAT2 in the expression of this OCD-like phenotype. And to do this, again, we used our lentivirus expressing VMAT2. In this kind of experiment, we have 3 groups. We have a control mice with a lenti-GFP, which is a control lentivirus, and then our mice with the lenti-GFP, and the mice with the lenti-VMAT2. These are the results. So first of all, the VMAT2 spent significantly more time in grooming, as you can see here in the green, and let's say meaning that was very similar to the results that I presented before. So meaning that the lenti-GFP was not let's say changing any behavior in this time. But then let's say the single intracranial injection of lenti-VMAT2 on P25 was sufficient to rescue this grooming phenotype. We have a very nice rescue in all of this phenotype. Similarly, consistently, for the VMAT2 deficient mice spent significantly less, let's say, time in the where is it? In the center of the arena, and also less time in the upper arms. And again, we had a very nice rescue of VMAT2. Interestingly, we couldn't find any rescue in the distance travel. So there is a sort of tendency, but it is not significant. So then we also check, we also estimated the effect of L-DOPA. And here you can see here in blue that the treatment with the chronic treatment with the L-DOPA ameliorated this phenotype. And the same was for the anxiety phenotype. Here, for example, is for the elevated plasmase, and here for the center of arena. So here we can conclude, we can have a little conclusion, which is quite important. And actually, we think that the astrocytic VMAT2 and also the proper levels of dopamine in the prefrontal cortex are necessary to have a normal grooming behavior. So at that time, we were interested in understanding the role of the prefrontal cortex, because actually with the VMAT2, we had a deletion everywhere. So we produced an antivirus carrying let's say, carrying the CRE recombinase, and we injected this lenti-CRE, let's say, only in the medial prefrontal cortex. Again, this is the results. These are the results of our antivirus that is expressed only in the astrocytes. We first checked for the phenotype, let's say, the sense for the decrease in extracellular dopamine levels, and actually it is significant. And then we checked for the behavior, and actually, it is quite remarkable that we had an increase in the grooming, and especially in the grooming boats. We had also an increase, let's say, in a decrease in the time spent into the center, the time spent into the open arm, which is let's say, an indication of anxiety-like behavior. So apparently, the injection of CRE lentivirus with the CRE, so by inducing the deletion of VMAT2 in the astrocyte only in the prefrontal cortex was sufficient to, let's say, to cause a sort of OCD-relevant behavioral deficit. Finally, in order to assess the clinical importance of astrocyte VMAT2, we also investigated the expression of bona fide proteins involved in the synthesis, storage, and the degradation of dopamine in human astrocytes. These are human tissue coming from the frontal part of the region of the cortex, sorry, of young, let's say, adult. As you can see, we found a very nice signal for MAO-B that is expressed that colocalized is expressed in GFAP positive astrocyte, and also of COMT, which is another enzyme that involved in the degradation. And here we have the results for VMAT2. We found that at least 80% of astrocytes in the human frontal cortex express VMAT2. And if you go into the high magnification, you can see that VMAT2 is expressed in the soma, and also in the let's say, here are not big, are long, let's say, processes. And actually, we also identified a subclass of astrocytes that are large, typically tortuous, and with a highly branched, that are localized in the layer 5. This astrocyte, one example is here, express quite high level of VMAT2. So in our conclusion, we can say that that dopamine, that astrocytes in the dopaminergic areas, especially in the prefrontal cortex, can play a particular important role in regulating dopamine homeostasis. And we also think that this phenotype can be potentially interesting because it may be related to the etiology of human OCD, spectrum disorder, in particular to trichotillomania, where repetitive air pulling from various sites lead to air loss. So in this case, for example, the patients they have this air pulling from the head. And for this is the last slide. I would like to thank my group, of course, and in particular also some former group members, such as, for example, Francesco Petrelli and Tamara Zender, and also Corrado Quali. And Francesco Petrelli did a lot of experiment in this project, and Tamara also helped, at the time was a PhD student, help in characterizing these mice. I would like also to thank the collaborators, especially Jean-Pierre Mottet and Glenn Dalérac for the electrophysiology in the first part of the project, and then also Linda Simler in the University of Geneva that did a lot of electrophysiological experiments that I didn't present today because I didn't have a lot of time. So thank you very much, and I will take some questions if there are any. Thank you. Ute, we can't hear you. You have to switch on.
Yeah, sorry, then I have to repeat. Thank you again very much for this nice talk and overview over your work. And we have now two options for the questions for the participants. You can either write them in the F&A chat that you can see as a right button on your screen, or it would be nice if you can just turn the video on and ask the questions. Because we record also the questions, and so it would be nice if we can also hear the question. But I can read it if you write it in the F&A. Please let me know if you have any questions. And for a first start, I probably have a question, although I'm from a different background. But if the astrocytes control of the dopaminergic pathway might be a mechanism for the OCD, why is then the dopaminergic pharmacological treatment not efficient? I mean, it is to some extent efficient, but why is that not the regulatory mechanism where we can then really treat it?
Paul, is a complex answer in the sense that the OCD, we don't know, first of all, we don't know exactly which is the cause of the OCD. So I'm not saying that are only astrocytes that are doing this. I'm telling that in some subgroup, let's say, I'm hoping some subgroup of OCD, they will have a problem in the VMAT2 in the astrocyte. But for example, now there are let's say 2 or 3 good work relating to the genes that are involved in this OCD, because actually it is highly irritable. For example, they found the SAPAP that is one of the genes that is involved. But this is only a subpopulation of this of all the OCD patients. Another question is can be the following. So, is there any patient with the VMAT2 mutation or deletion or etc. Actually, the answer is no, but this is because the VMAT2 is highly expressed in neurons, in all monoaminergic neurons and catecholaminergic neurons. So meaning that VMAT2 in neurons can regulate dopamine, serotonin, histamine, etc. So it is really an important gene, and if you delete or if you mutate this gene, then is incompatible with life. Actually, this has been demonstrated in mice. There are only a couple of important papers regarding the VMAT2 mutation. They found a family in Saudi Arabia with the mutation of VMAT2, but this is of course a general mutation, so it's not related to the astrocyte, it's related to VMAT2 everywhere, and this patient have really a strong phenotype. I mean, it's not related. Of course, they also have OCD, but I mean, they are catatonic, they can't move, etc., etc. So my opinion is that it is possible that there are some pathological conditions that for example, some inflammatory condition that can occur during, let's say, just after birth, or some inflammatory condition that can occur during embryonic life, no? That somehow that can perhaps modify the astrocytes that we know that become reactive, no? They change a lot the function and the structure and the genome, etc., the gene, let's say, the gene that are expressing. So perhaps there are some of these conditions that somehow can affect the level of VMAT2 only in the astrocytes, and then can cause this kind of, let's say, of phenotype, let's say. But right now we don't know. So this is the next project. We would like to check if there is any condition that can somehow regulate VMAT2 only into the astrocytes.
I have another question for you, Paola.
Yes.
I will read it to you. Do you think that cognitive impairments in your experiment is related with developmental anomalies or only dopaminergic physiology? You can also see the question if you click on.
I'm thinking about, didn't understand very well. So in the sense that he or she is worried about the role of other monoamines, or she is worried about the role of astrocytes, in the sense that the cognitive, the two cognitive that you check, because we check only working memory and behavioral flexibility, apparently are rescued if you re-express VMAT2 only in the astrocytes, or if you treat the mice with L-DOPA. Of course, when you treat the mice, L-DOPA goes everywhere. So they can increase dopamine everywhere, but I'm pretty sure that is dopamine related, yes.
Yeah,
because apparently astrocytes, and also this, I don't know why, but apparently this VMAT2 in this subpopulation of astrocytes can control only dopamine. So we couldn't find any other, let's say, monoamine that was dysregulated in this mouse. Of course, then we focused on the prefrontal because we found that VMAT2 was particularly, let's say, high in the prefrontal and the frontal part of the brain. But perhaps there are also other areas where there is a little bit of expression of VMAT2 in the astrocyte, and for example, the striatum. As I said when I showed the immunohistochemistry, so the level of VMAT2 in the striatum, in astrocytes in the striatum, is not zero, apparently. We defined weak in the sense that we can see something, but it's not very high. But still, perhaps it can be important, it can have important physiological role that we don't know yet, let's say.
Did that answer your question, Marco? It seems so. I can't see.
Is related to development anomalies. Ah, yes, sorry, I didn't answer these development anomalies. We check, so we did really a lot of experiments to check the developmental anomalies, but actually we couldn't find any gross, let's say, deficit in the prefrontal cortex and in the cortex. What we found is a decrease in the number of spines, and also in the number of dendrites that we didn't publish. But we have the number of excitatory, let's say, dendrites and the spines, but not with the spines is published, but also if you check the preliminary, the supplementary results, we have a lot of information. Also, we did really a lot of control. We also check with electrophysiology and with optogenetic, the function of dopamine neurons in the VTA. because we said perhaps, I don't know why, but this deletion will affect some dopaminergic function of dopaminergic neurons in the VTA, but actually the answer was no. So we couldn't see any differences, let's say, in the dopaminergic neurons.
Thank you very much. That answered his question already. He already said yes, thank you. And since we're already over time, thank you again, Paola, for the nice talk, and thank you
so
all,
much.
and thank you all to your participants for your attention and your participation. And I wish you a very fruitful and interesting remaining conference. Have a nice remaining day wherever you are. Bye. Bye, Paola.
Bye.
Thank you everyone for coming. I'm Adam Steele. I'm a postdoc at Dartmouth College in Hanover, New Hampshire. And I've been told that we have a few moments to just wait for people to trickle in. So I'll use that time to say, everyone in the US, please vote. If you have already made a plan to vote then, and you figured out how you're gonna do that, then call a colleague and figure out how they're gonna vote. And if you can't vote in the US elections, then call a colleague in the US and figure out how they're gonna vote, because this is super important. I can't emphasize that enough.
And don't call the US administration chaotic, because there is beauty and subtle structure in chaos, as we will discuss in this session.
Ronnie, that's a beautiful point. You can call it, well, maybe I shouldn't express my political leanings, but I think dumpster fire. So my apologies for that, everyone. So we have 3 great thought-provoking talks this session about dynamic systems and recurrent neural networks. As a reminder to those in the audience, we have the chat where you can post messages and clarification questions. Just make sure that you have your messages set to panelists and attendees, so that way everyone can see what you're saying. If you'd like to introduce yourself, so that way everyone knows who's here, now's a great time to do that. So just post who you are and where you're coming in from in the chat if you'd like to. We also have the Q&A tab for questions. So you can post questions at any time and make sure to upvote your favorites so that way they can be asked live. If we don't have time for your questions, the panelists will be available in chat or to answer the questions via typing. For those on Twitter, please tweet about this session using the hashtag NMC3. So for our first talk, we've reordered the talks slightly, but our first talk is going to be Rainer Engelken from Columbia University. And his talk is titled "The Effects of Partial Connection Symmetry and Asymmetry on Dynamic Stability, Lyapunov Spectra, and Training of Recurrent Neural Networks." So you have the floor.
Thank you so much. My name is Rainer Engelken. I'm postdoc at the Center for Theoretical Neuroscience with Larry Abbott. I'm studying dynamics and learning in neural networks using a dynamical systems perspective. I would like to share with you today. My talk is entitled "Quantifying Dynamic Stability in Signal Propagation, Lyapunov Spectra of Chaotic Recurrent Neural Network." I guess we all agree that information in the brain is processed by the coordinated activity of large-scale neural circuits. Understanding mechanisms, how this complex dynamics gives rise to functions, such as processing sensory information, performing decisions, or controlling behavior, is a challenge, both for experimentalists and for theoreticians. Today, I want to describe how we can use tools from dynamical systems theory to understand better in rate networks what shapes this complex dynamics and the correlations, and how we can use that to better understand this also from an analytical perspective. So in dynamical systems, we distinguish 2 very different kinds of states. If small perturbations of initial conditions exponentially converge over time, we call a system stable. In this case, we have a negative largest Lyapunov exponent. In contrast, in chaotic systems, infinitesimal perturbations exponentially diverge over time. So we have a positive Lyapunov exponent, and that has drastic effects on the information processing capabilities of such systems. So in a nutshell, if a system is sensitive to initial conditions, this means two nearby states are being pulled apart over time and become distinguishable, even if they are indistinguishable at the beginning. So in other words, we learn about the initial state. Now, if the microscopic state of a system, say of a neural network, only contains noise, then this entropy would be a contribution to noise entropy. In contrast, if this microscopic state contains important signals, then this dynamic entropy rate of a dynamic system measures how fast this information becomes accessible to a microscopic readout. And this concept of dynamic entropy rate was formalized by Komgov and Sinai. And while it's really difficult to measure entropies in high-dimensional systems, we can, under weak mathematical constraints, approximate it or get it from the sum of the positive Lyapunov exponents. Second important concept, if systems are driven by stochastic external input, which is frozen, then there is a subtle link between microscopic stability, meaning then a negative largest Lyapunov exponent, and the global stability. So if the largest Lyapunov exponent is negative in such systems, it's guaranteed that if you wait long enough, arbitrary initial conditions will collapse onto a random sink that is a set of measure 0. And I will use that later to better understand rate network dynamics. Now, such dynamical systems don't fill the whole n-dimensional phase space, but they live on a lower dimensional attractor, which can be a 0-dimensional fixed point, a 1-dimensional periodic orbit, or a strange chaotic attractor with higher and usually non-integer dimensionality. And again, measuring an attractor dimensionality is really intractable if you do it directly on data, but through this Lyapunov exponents, we can get access to such quantities also in very high-dimensional dynamic systems. So to summarize, the sign of the largest Lyapunov exponent give us whether the system is chaotic or not. The sum of the positive Lyapunov exponents give us, under weak mathematical constraints, its dynamic entropy rate. And from the number of Lyapunov exponents, which sum to 0, we can get the attractor dimensionality. The idea here is that if you have a d-dimensional ball, the shrinking directions are being compensated by the growing directions, so that an initial ball is only being deformed but doesn't change its volume. So basically D is the sweet spot, such that the growth in a couple of directions is compensated by shrinking in other directions. So the system I would like to use these concepts for are firing rate networks. The network is given, the dynamics is given by a decay term and a nonlinear interaction term, where the coupling matrix Jij is drawn from a Gaussian with mean 0 and variance g squared over n. G is a global synaptic strength parameter, and the normalization is to make sure that the spectral radius is invariant with system size, and phi is a nonlinear input-output function. In our case, it's a hyperbolic tangent. And so these network types are very useful to learn complex input-output functions. Therefore, there was in the last couple of years a renewed interest in these kinds of chaotic neural networks. However, their collective chaos and dimensionality is not well understood. So I will now use the concepts which I just introduced, entropy rates, dimensionality, to quantify them and see how they are, what shapes them in these kinds of networks. First, we look on the coupling strength, and as expected from theoretical consideration, the largest Lyapunov exponent becomes positive at a critical value of the coupling strength, where the trivial fixed point becomes unstable and aperiodic chaotic dynamics emerges. And now for this network, we can look at the entire Lyapunov spectrum. It's a network of 1,000 units. So there are 1,000 Lyapunov exponents, which are sorted here by size. And for very weak coupling, all Lyapunov exponents are close to the negative inverse characteristic timescale. At the critical value, the largest Lyapunov exponent hits 0. And for larger couplings, there is now a positive fraction of, there's a finite fraction of positive Lyapunov exponents. Note that the entire Lyapunov spectrum is symmetric in these networks, and ask me later if you want to understand why. Now, based on the full Lyapunov spectrum, we can quantify dimensionality and entropy, we found that despite the fact that from a mean field perspective, nearby pairwise correlations are vanishing for large G, the dimensionality is bounded below 10% of the phase space. So there is an intricate, subtle, entangled structure, which is not being seen from the pairwise correlations. At the same time, the dynamic entropy rate first grows with coupling strength, but something which you can't see here is it's also bounded and it decays for very strong coupling. So while coupling intensifies chaos based on the first Lyapunov exponents, both dimensionality and entropy are bounded. Next, we investigated the behavior with system size, and as expected from theoretical considerations, the largest Lyapunov exponent saturates with network size. But now what's new is the shape of the entire Lyapunov spectrum, if you normalize it by network size, is independent of network size. This indicates extensive chaos, so trivially both entropy rate, dimensionality grow linear. That was hypothesized already decades ago, but now we found really direct evidence for that. And next we investigate, so can we better understand this complex chaotic attractor? Here I projected the first two principal components. I projected the dynamics of the first two principal components. More conventionally in neuroscience, people measure dimensionality based on the PCA. So here we compare this attractor dimensionality with PCA-based dimensionalities, and you can see both of them grow as a function of coupling strength once network turns chaotic. But now for the PCA dimensionality, where it saturates and at what rate it saturates really depends on whether you measure the PCA-based dimensionality on the firing rates or on the local fields. So this quantity is not invariant and a diffeomorphism. In contrast, the attractor dimensionality based on the Lyapunov exponents is a topological invariant. And similarly to what I showed you for Lyapunov exponents, both PCA dimensionalities, however, grow linearly also in network size. So these are also extensive quantities. So what happens if you drive a network with time-varying external input? It was shown before in other studies that the largest Lyapunov exponents decay. So there's a suppression of chaos, both in time-discrete networks and in networks with sinusoidal input and in continuous time networks. However, the full Lyapunov spectrum wasn't quantified before. So here we find that both entropy and dimensionality decrease as we drive the system stronger and stronger. So as we crank up the noise strength, and for very strong input, networks arrive at a random sink. So that is a state where the microscopic information cannot travel to the macroscopic state anymore. So generally, it's really difficult to quantify Lyapunov spectra analytically. They're given by a log of the eigenvalue of the oscillatic matrix mathematically, where the oscillatic matrix is built up by the inner product of this long-term Jacobian, which is basically a product of non-commuting matrices, which are hard to evaluate analytically. However, in some limits, Lyapunov spectra are very invariant and a shuffling of these Jacobians. And that is the case when they are uncorrelated. So if G is large, if noise drive is large, or in discrete time networks, or close to the critical transition. So in these cases, we can analytically approximate the full Lyapunov spectrum. Here you can see the numerics in full lines and dotted lines, the analytics, and appreciate that they match pretty well. And that was just one of the examples. These are the other cases where we can calculate them analytically. I think I don't go into the mathematical details, you can ask later. But so we want to use this machinery now to better understand reorganization of state space structure during learning. So say we start with an initial chaotic network, and then using some training algorithm, we can now stabilize these unstable directories. We want to use this machinery to better understand how that happens. And here is an example. I trained a network on an oscillation task with very good frequency. And on the right, you can see the Lyapunov spectra after training using different training algorithms. So the Lyapunov spectra now can also make statements about how stable the results based on different training algorithms are. Just as a quick outlook, we also quantified Lyapunov spectra of more machine learning networks, in this case, a discrete time LSTM network. And as we saturate the forget gate in these networks, we find an accumulation of Lyapunov exponents close to 0, which is consistent with earlier eigenvalue considerations by other people. And so what that means is, in this case, the entropy rate is decreasing, but at the same time, the dimensionality is increasing. That might be useful for expressing very complex input-output functions or complex time-dependent tasks, and also to bridge long time scales. Just one last remark I want to make before I wrap up. There's a subtle link between the forward dynamics of the tangent space as quantified by the Lyapunov spectrum and the backward dynamics during backpropagation through time. So if you do backpropagation through time in a recurrent network, it's done by unrolling the network dynamics in time. And so we have these expressions how one network state depends on its own past. And the mathematical, if you write down the mathematical expression for that, you get a long-term Jacobian, which basically tells you how a small perturbation at one point affects a perturbation of the same state, of the same unit at a later time, or of other units. And the singular values determine whether these gradients in backprop explode or vanish. And so we hope to use Lyapunov spectra to better understand vanishing, exploding gradients. To summarize, we quantified the complete Lyapunov spectra of chaotic random networks. This gives us an estimate of the attractor dimensionality and Conroe-Sinai entropy rate. We find an increasing entropy and dimensionality, and for coupling strength, but they saturate, they're bound. The Lyapunov spectrum is symmetric around the negative inverse characteristic time scale. We find that dimensionality and entropy are reduced by fluctuating input. And while pairwise correlations can be super weak in large networks, there can still be a very low dimensional attractor as shown by the Kaplan-York dimension. And in some limits, we can analytically calculate the full Lyapunov spectrum using random matrix theory. And there is a subtle link between vanishing and exploding gradients when training networks using backprop and the Lyapunov spectrum. And as an outlook, we want to use that to better understand and quantify stabilization of trajectories during learning. So we have a preprint about this work, and later there'll be a talk by Matthew Ding, who will investigate how different network structures shape the network dynamics. With that, I want to acknowledge my previous lab, Fred Wolf, which is led by Fred Wolf, my current postdoc mentor, Larry Abbott, and the team at the Center for Theoretical Neuroscience, the funding sources, and all of you for your attention. Thank you very much.
Great. Thank you, Rainer. This was it was a great talk. Absolutely. Unfortunately, we don't have any time to do questions verbally, but you do have 2 questions in the Q&A from Pierre Orhan, which you can address through typing. So next, we will have our second talk by Manuel Brenner and his colleague from the Central Institute of Mental Health in Mannheim. Manuel, did you have, who was the colleague that you needed to have pulled out of the audience?
He's actually sick, so I'm doing it on my own, so no worries.
Great, okay, excellent. So it'll just be Manuel then. His talk is titled Fast and Scalable Learning of Generative Models for Chaotic Dynamical Systems and Neural Data.
Yeah, thanks for the introduction, Adam. Today I will be talking a bit about a current project I'm carrying out with Leonard Bereska, Po-Chen Kuo from Taiwan, myself, and the research group of Daniel Dustewitz at the Central Institute of Mental Health in Mannheim. We are also part of Heidelberg University. And just to give a short illustration, just to give a short motivation of why we do what we do. So there's this general hypothesis that cognitive functions are implemented in terms of network dynamics in the brain, so that the dynamics are actually really crucial for implementing function and shaping our emotional and cognitive experience. And because we are part of a mental health institution, it's also crucial for us to understand what happens when this cognitive and emotional experience is disturbed in some kind of way by changes in network dynamics. So you have distractibility in ADHD, you have obsessions in obsessive compulsive disorders, hallucinations in schizophrenia. And so the general hypothesis is that these changes in network dynamics can actually be caused by a lot of biophysical and structural causes. So changes in dopamine concentration, in synaptic connectivity, for example. So it's really crucial if you want to build a causal model of what's going on during mental illness and in the brain from a dynamical systems perspective, you need to understand what's going on in terms of the dynamics. What we are doing is we are inferring generative models from data. This data can look many different ways. It can be just simple benchmark dynamical systems data, as we will see later, or it can be experimental data that is in some way pre-processed before we plug it into our model. The next step is to actually infer the model by showing it the data. And after we have inferred the model, we can just completely throw away the data in principle and generate completely new samples, as we will see later. And we can then try to compare these completely new samples with the data distribution and assess the deviation in terms of a KLX measure or as mean squared error, for example, as I will also show in more detail later. The model we are using more concretely is called a piecewise linear recurrent neural network. This is a state space model that's composed of two main parts, the latent model and the observation model. And the latent model is really the heart of what we are trying to learn and achieve, because the latent model is kind of hiding behind the data surface, but this is where the dynamics are actually going on. And in our case, we have just these latent states, which you can also kind of imagine as units like in a neural network, so kind of synapses or neurons that are firing or have a certain kind of activity and are connected to each other with these diagonal and off-diagonal couplings. And what's important here is that we have a piecewise linear structure, so we have a non-linearity in the form of a ReLU activation function, and then we can connect the latent dynamics to an observation, to data through this observation model. This can be a simple Gaussian observation model, as in this case, or it can also be for fMRI data, something like a hemodynamic response function. If you want to take a look, that's already implemented in this paper by Georgia Koppe and also from our research group. So our main question that I will be talking for the rest of this talk about is how can we increase computational capacity of this simple piecewise linear state space model, and by increasing the computational capacity, achieve some kind of dimensionality reduction of latent space while retaining this piecewise linear form. And you can think of it in terms of a neurophysiological analogy, in terms of, for example, dendritic computation. In every single neuron, there's also computation going on in the dendrites, and there's, if you increase the complexity of the synapses and of the neurons, you can achieve some kind of diversity and more computational capacity. And we achieve this by introducing this basis expansion. So we replace the simple ReLU activation function that just gives us a maximum of 0 and the latent activation by this base expansion, which introduces this bias vector and a scaling factor alpha. So we can pick the number of basis states here. It's a hyperparameter that we can choose, and this introduces more parameters into the model while retaining the latent dimensionality. And so makes the model more expressive and colorful. The method we are using to actually learn our model is called variational inference. That's pretty popular right now in a lot of machine learning environments. So the basic idea is always the same. We have this variational lower bound that we are trying to optimize by introducing this approximate posterior distribution over latent states, which is this Q that we are not computing explicitly, but we are approximating from the data. So in our case, we are also doing a mean field approximation. So for every density at time step t, we are just estimating it straight from the data at time point t by parameterizing a Gaussian distribution with a multi-layer perceptron, so a neural network. And just as a general note, we can also, in principle, use different algorithms to learn these piecewise linear recurrent neural networks, like expectation maximization, for example. But the advantage of this method is that it scales really well computationally, and we can have a high number of latent states while having a really fast and amortized inference of our models, which is especially helpful for if we take a look at real neural data like EEG recordings that have a high number of input states, and therefore also in potentially a high number of latent states. So first of all, we tried this out on benchmark dynamical systems like the Lorentz attractor with this famous butterfly shape, and also the Lorentz 96 system. The Lorentz 96 system is, it doesn't have a fixed dimensionality as the Lorentz does with 3D, but the Lorentz 96 is recursively defined, so you can in principle also have, in our case, we trained on 10-dimensional Lorentz systems, but you can also have 20 dimensions, 50 dimensions, which makes it really useful to understand. And both of them are chaotic dynamical systems, so they have these typical chaotic properties that we already heard about in the first talk. What we are using to evaluate how well our reconstructions actually are, that we learned from the data, we are using both global and local metrics. The first one is a Kullback-Leibler divergence that compares the distributions in state space and in observation space of our trajectories. So in our case, you can imagine just a Lorentz system that is the underlying true system, and then we learn a completely generative model and just generate a completely new trajectory based on our model, and we can compare the two. And for chaotic dynamical systems, this is really crucial because mean squared error predictions quickly diverge because you have small changes in initial states that can blow up quickly, and then you are really not matching the underlying dynamics, the underlying data well, while you still have captured the underlying system properly. So we tried this out on the Lorentz system and could actually show that having this base expansion, so this number of parameters of bases, really improves pretty dramatically the reconstruction. So for the KLX, and both in state space and in observation space, and the mean squared error predictions 1, 5, and 25 time steps ahead. So you can see here that the number of latent states usually improves reconstruction, but by introducing the spaces, we can achieve an effective dimensionality reduction, because if you have if you have 10 bases or 5 bases, you really achieve these better KL results and better mean squared error results much faster, and thereby you don't need 12 latent states, for example, to learn the Lorentz system, but you can achieve the same result with 8 latent states. And effectively, for 12 latent states, you still have a substantial improvement in the quality of your reconstruction. And we could achieve the same thing for the Lorentz 96 system. So if we just have 20 latent states and 1 basis, we tend to find this, be able to generate these trajectories that kind of seem to capture the right timescales that are present in the data, but only provide these simpler oscillatory patterns. So these are contour plots where the color just gives you the value of the trajectory. And as we can see in the case with 20 base pairs, we really achieve this kind of chaotic behavior. And if you look more closely here, we really have, especially in the beginning, we closely trace the system, but then at some point it diverges, which is not surprising because it's a chaotic dynamical system. But we have, in terms of both the KLC measure and the 25 steps ahead prediction mean squared error, we have really good results. So how to read this plot? From left to right, we can see the number of base pairs that we introduced, and this is a number of latent states. So just as you can see, for 15 latent states, we weren't able to really properly learn the system, but starting from 20, 25, and 30 latent states, you can see that we both really managed to reconstruct the system, and that introducing these base pairs substantially increased the quality of the reconstruction and made reconstruction much more consistent. So with 50 base pairs, every single one of the reconstructions has a very small KLZ value, which means that the reconstruction is really close to the underlying data distribution, and the mean squared error 25 steps is also much better than just what you would expect from just randomly guessing the system. We are now also moving towards experimental results and experimental data sets. This is an example where we took a look at intracranial EEG recordings, so from the human brain, that were doing a visual spatial working memory task. And there are some problems that we face with real data that we usually don't face with these benchmark dynamical systems, for example, we don't really know the underlying attractor dimensionality, and we also don't, there's potentially noise, and we don't really know how high dimensional the system that's generating this data actually is. Because in the case of the Lorentz, it's only 3 dimensions. In the Lorentz 96, it was 10 dimensions, but for EEG, it's we really don't know. And considering that, we could also, with the help of the base expansion, achieve some at least qualitative reconstructions of these trajectories. And now we are also taking a look at multiple single unit data from a rat brain. And just to wrap this up, we introduced this method to our PLRNN model that's called base expansion. We could show that it actively improves inference, and it encourages, in the case of the Lorentz 96, the learning of more interesting chaotic dynamics and the reconstruction of these dynamics. And it also allows us to effectively reduce the dimensionality of the latent space, which can help us with interpretability and just computational scaling, and also reduces parameters we need for the model. Just as acknowledgements, we were funded by the German Science Foundation and by the Excellence Cluster Structures at Heidelberg University. So thanks for your attention.
Great. Thank you, Manuel. That was a really interesting talk and super clear. So I really appreciate that.
Thank you.
We've got several questions in the Q&A. Jules Brichard asks, after being fitted to a data from a complex system, are your networks chaotic systems themselves?
Yeah, you could understand it that way, because we are learning this piecewise linear recurrent neural network. And if we have an initial state, we can generate dynamics with the system, because we have this recursive map that shows us when we have a C0 state, we can move to C1, C2, and then generate a completely new time series. And that time series in itself is then a chaotic dynamical system. So yes.
Great. So Pierre Orhan asks, what is the exact definition for KL divergence of the model and simulated trajectories here?
So what we are doing is basically we are binning, in this case, the space, and just compare the density of the points, so the probability of the model to be in that region of the space with the probability of the simulated trajectory. So we just take a trajectory that's like 10,000 time points long, and then we generate one completely freely from the model that's also 10,000 time points long, and then we just compare the probabilities of them being in every bin of this point of this space, and then that gives us a value that can be, if it's close to 0, that means we have a strong match, and if it's large, that means we basically don't have any overlap.
Makes sense there. If Pierre, if you have any more technical questions, you can post them in the chat. And then we have one more question from Ranek. He says, thank you for, they say, thank you for the talk, Manuel. How similar or dissimilar is this method compared to David Cicillo's LFAD's algorithm? And then this needs to be a short answer because then we have to move on to Matthew.
Unfortunately, I don't know that algorithm in any details, so I can't answer that, sorry.
Okay. So you can pick that up in the chat. Also, there's a request for paper references in the chat too.
Oh, yeah.
So thank you again, Manuel. That was a great talk.
Thank you.
And we'll move on to our final talk of the session from Matthew Ding, our research assistant in Larry Abbott's lab at Columbia University. He will be presenting work that builds on earlier work presented by Rainer Engelken, titled Quantifying Dynamic Stability and Signal Propagation, Lyapunov Spectra of Chaotic Recurrent Neural Networks. Just make sure to unmute yourself, Matthew.
Oh, sorry about that. Thank you very much for the introduction. So yeah, I'll be presenting the effects of partial connection symmetry on stability and Lyapunov spectra of recurrent neural networks. And much of this has been explained prior, but I'll go over it again, just in the context of my research, to provide some more clarity, hopefully. How can I... Here. So I'll start with the motivation behind our research. There's recently been a lot more connectomic data both on a scale of individual neurons and on a scale of brain regions. And from this arises the question of how does connectivity shape the dynamics of biological neural networks? And to study this rather complicated question, we'll consider connectivity in a common model of neurodynamics, which are recurrent neural networks. In particular, we are interested in the effect of symmetry on the autocorrelation timescales and dimensionality of the dynamics, as well as the dynamic stability, namely, how does the symmetry of the network affect the Lyapunov spectra and the stability of trajectories. Finally, we consider how partial symmetry in the initial network state affects its behavior during training and its ability to learn to generate periodic signals without input. Now, I'm going to elaborate more on what symmetry means in this context. This is a standard recurrent neural network with n-rate units and a 10-inch nonlinearity with a network-wide gain parameter G, which uniformly scales all of the synapse strengths inside the network. We can think of the symmetry parameterized by eta between -1 and 1 as a sort of correlation coefficient between reciprocal synapses in the recurrent neural network. As an example, an eta value of 1 would indicate total symmetry, in that if neuron A is connected to neuron B with certain strength, then the reverse connection has exactly the same strength as well. And the case of eta equals -1 is perfect antisymmetry, in which case it would have the opposite sign. Otherwise, the variance of all the entries of J, the connectivity matrix, are normalized to 1 over the square root over the network size to ensure that the spectral gap of the connectivity matrix is within a reasonable bound, varying with size. An important property to know for this network is that for a vanilla, so-called eta equals 0 network, above G equals 1, the network is chaotic. And the typical training initialization is to set a G between 1 and 1.5. We consider two cases in this following research: the strong case, in which we set G to equal 10, and the weak coupling case, in which we set G equals 1.5. And there are a few notable differences between the two cases, as I will go into. This is just a sort of review on the what the Lyapunov exponents and the Lyapunov spectra are. This has been explained before, but I'll go through it again. Initially, nearby conditions separate at an exponential rate, and the largest Lyapunov exponent quantifies that exponential rate of separation. If the largest Lyapunov exponent is positive, then the network is chaotic. Otherwise, it is non-chaotic. And it is also possible to define an entire Lyapunov spectrum, which is a list of the Lyapunov exponents the same length as the dimensionality of the system, which describes the transformation by the evolution of a chaotic system on a infinitesimal ball of initial points around a reference trajectory. And as a sort of illustration, I've put the visualization of such the transformation on a ball of points of a Lorentz attractor. And from the full Lyapunov spectrum, it's possible to calculate a measure of dimensionality called the Kaplan-York dimensionality, which is an upper bound on the more familiar box counting dimensionality of the attractor, which indicates what fraction of phase space that the network dynamics occupy. And we can also calculate the Kolmogorov-Sinai entropy rate as before, which quantifies the rate of growth of uncertainty due to chaotic separation of initial conditions. And just from the plots of the trajectories as a function of different eta, we can see that relative to the vanilla network, the more symmetric networks have fluctuations that are on slower timescales. And to quantify that further, we see that the autocorrelation functions of more symmetric networks decay slower relative to the vanilla networks. And in the right plot, we see that in a sort of analogous trend, the autocorrelation functions of partially antisymmetric networks decay faster than the vanilla networks. These results are also seen for networks in which the variance of the activities is held constant, meaning that even if the autocorrelation functions all start from the same initial value at 0 time lag, the trend of symmetric networks decaying slower and antisymmetric networks decaying faster will still hold. Additionally, we examine the PCA dimensionality, and to quantify this, we use a quantity called the participation ratio, which is incapable of interpolating between two extremes The first of which is in that all the variance is one dimension, in which case the participation ratio inverse will be 1. And the other extreme being the variance is spread equally, in which case the dimensionality will be n. And values in between 1 and n will indicate more or less extreme concentration of the variance in the first few dimensions. And we see that the trend in PCA dimensionality differs in the weak and strong coupling regime. In the strong, the PCA dimensionality decreases pretty monotonically as a function of eta around the initial eta equals 0 point, barring a few edge cases at the extremes. And in the weak coupling case of G equals 1.5, the PCA dimensionality peaks at an intermediate value of eta. As for the Lyapunov spectra, we see that we see a pretty clean trend in that more symmetric networks tend to have more curved Lyapunov spectra, indicating that more symmetric networks have both fewer positive Lyapunov exponents, and the magnitudes of those positive Lyapunov exponents are smaller. And in the anti-symmetric network case, we see a similar trend in that for up to an intermediate value of minus eta, the network, more anti-symmetric networks have less curved Lyapunov spectra, leading to more positive Lyapunov exponents and Lyapunov exponents with greater magnitude as well. And as a result of this, we see that in the strong coupling regime, the Kaplan-York dimensionality and entropy rate also monotonically decrease as a function of eta. And the maximum Lyapunov exponent starts to decrease as a function of eta around the vanilla case, and really goes down as in the symmetric case. And taking our results to the weak coupling case of G equals 1.5, we see the similar trend for symmetric networks. And up to a certain extent, up to eta equals minus 0.3, similar trend for the anti-symmetric networks here as for the strong coupling case. Eventually, due to the shape of the eigenvalue spectra of the weight matrix, networks in the anti-symmetric case in the weak coupling regime fail to be chaotic after a certain eta, or below a certain eta threshold, after which the maximum Lyapunov exponents falls to below 0, and we see a sort of decay in the trend. A future study, I guess, would aim to control the chaoticity of the networks to see if this trend holds even in that regime. And as a result of this, the Kaplan-York dimensionality and entropy rate peak at an intermediate value of eta as well. And the maximum Lyapunov exponents in the subcritical regime is linear in the symmetry parameter and peaks at the similar value as the dimensionality and entropy rate. Finally, we'll consider the training of periodic target signals. Here we use backpropagation through time, and we unroll the network for the length of one period of the target signal times a small overlap factor to ensure that the final training trajectory is non-chaotic and also periodic. As a measure of how successful the training is, we examine the convergence times, and we see that, as one might expect, more anti-symmetric networks converge faster and are generally more successful at training both all of sawtooth, square, and a superposition of forward frequencies than vanilla networks or symmetric networks. Although a notable trend to indicate that is that the most anti-symmetric networks are converge slowly, pretty robustly, than the eta equals minus 0.8 networks. And from here, we quantify training in a different way by setting an arbitrary success threshold. The threshold being the mean squared error below which it's the threshold of the mean squared error. And if the test error falls below that threshold before 2000 epochs, then we consider the training successful, otherwise not. And we see here also that the more anti-symmetric networks also have a higher success rate than the vanilla networks and the symmetric networks. And in conclusion, we see that with both strong coupling and weak coupling, the symmetry increasing has a pretty uniform effect of increasing the autocorrelation timescale. And likewise for anti-symmetry, autocorrelation timescales decrease. For Kaplan-York dimensionality, in the strong coupling case, symmetry decreases the Kaplan-York dimensionality, whereas in the weak coupling case, there's local maximum of the dimension at an intermediate value of eta, similar for the entropy rate, and with the maximally abundant exponent as well. In terms of training, most of the time, backpropagation through time as a training algorithm will not suppress the chaos of a recurrent neural network. And so we only consider the weak coupling case of G equals 1.1. And in these networks, we have a greater success rate and a faster convergence time for RNNs that are anti-symmetric rather than symmetric or completely random. And a future direction in which I thought of to take this work is to not only refine the training results earlier, but also to look at further motifs that people have considered and measured in local circuits in V1 and other brain areas that incorporate multiple neurons in convergent, divergent, and chain motifs. And these sort of measured statistics may also have a pretty large effect on the stability, trainability of recurrent neural network models. And that's all. I'd like to thank Rainer Engelken for plenty of great mentorship, Larry Abbott and Laura Lee Nijiako for helping refine and discuss this project. And we're also supported by the Gatsby Foundation, National Science Foundation, NeuroNext, and the Source Foundation. And that's all.
Great. Thank you, Matthew. That was an excellent talk. You can see Reiner's great mentorship coming out for sure. I had a question. So there's time for maybe one or two quick questions. I'm going to ask a question. If you can go back to your the data figure that you showed, the last data figure that you showed about the success rates. Here you go.
Yeah.
So it looks like in each of these cases, you've got a like a peak in the success rate, albeit a small peak, that's situated like right around 0.5 for eta. Do you have an intuition for why that might be?
Well, the cause of this peak is that the training algorithm sort of fits an initial transient around the initial condition of the hidden layer state to the target signal. However, if one allows the network to run after that, we do not observe a limit cycle. We only a fixed point in the dynamics. And
okay. But why does that? Why would that cause specifically a peak in success rate there, as opposed to like kind of having a base, some sort of base success rate? Or were you about to get to that point? I'm sorry.
Well, my explanation is that because the timescales differ for different values eta, the sort of transient length that the training algorithm has to work with may differ. And it could be the case that there's a balance between the appropriate timescale of dynamics necessary for fitting a target signal and the appropriate transient length available to backpropagation that causes it to be most successful around eta equals 0.5.
I see.
But to sort of solidify that intuition, I would have to do more experiments.
I see. Mm-hmm. Great. Well, I think that that's all the time that we have for the moment. So I just want to thank again our three speakers. These were great and very clear talks, and I hope everyone enjoyed them. And we'll see you at future sessions of NeuroMatch. Thanks again, everyone.
Thanks for having us.
Thank you.
Thank you so much. Thanks, Manuel. Cool work. Let's chat more about
an actual colleague. So I'm announcing the talk by Ismail Abdus-Sabor, who is one of my colleagues at UPenn. He's in the biology department, just a stone's throw away from where I work. And I'm very much looking forward to his talk, which will be about a touch circuit in the skin for social and sexual behavior. Ishmael, very much looking forward to your talk.
Thanks for that introduction. And it's great to be here with you all today in this virtual community. So today, so my lab opened here at Penn 2 years ago. And here's one of the first projects we got started with. It started as a side project, but I think it's morphing into something we care much more about these days. So let me get started. So just to give credit where credit's due at the outset, this work was led by two really talented Penn neuroscience PhD students, Leah Middleton and Melanie Schaffler. Most of what I'll present today is Leah's studies. All right, so gentle stroking of the skin is rewarding to mammals, and I think this is something that we all easily appreciate. This is important for normal social bonds and developing relationships, important for sexual behavior and relations. And you can see, and again, what we can appreciate is that when you're touched across your skin surface by a relative or friend, this feeling of euphoria or reward is nearly instantaneous. And it's almost as if we have neurons in our skin that are tuned to sense this type of rewarding gentle stroke and signal that information to the brain so that we can mount the appropriate response. So it turns out there are such neurons like these in the skin. They're unmyelinated C low threshold mechanoreceptors, or CLTMRs. So these neurons were first identified in cats actually in the late 1930s, where scientists could do experiments where you would stick an electrode in a cat and you could find neurons that seemed to only fire to touch or tickling, if you would, but not to pain. These neurons were identified in people in the late 1980s by doing these microneurography techniques combined with psychophysics, where you can stick an electrode in a person's arm and you can find single unit recordings, neurons that fire to the stroking across the skin, where people said this feels really good and soothing. There are neurons that seem to correspond to that sensation. Okay. Here's a more recent cartoon of these neurons, a review from Victoria Abrera and David Ginty. And so here these CLTMRs are shown here in red. You can see they wrap around hair follicles, or sometimes they just terminate in the skin as these free nerve terminal endings. So the idea being that in the skin, as you stroke across the surface of the hairy skin, you would generate a sensory percept. The person would say, this feels good or gentle. Now, I believe this field may have been broken open by these two studies here from David Anderson's lab at Caltech. I'll just share a little bit of this data and then I'll start to get into our data for the rest of the talk. But these two papers were important because the Anderson lab identified a molecular class of neurons in the mouse that express this GPCR, and this class seems to correspond to these C low threshold mechanoreceptors, these CT afferents, these gentle touch neurons. Let me just show you a little bit of this work from the Anderson lab. So this GPCR called MRGPRB4, it's only expressed in these skin sensory neurons that are thought to convey gentle touch, nowhere else in the brain or non-neuronal cells. Here's their morphology in the skin. They made a mouse line with this alkaline phosphatase so they could just visualize these terminals. The point here is that these terminals are quite patchy in the skin. This is like air skin and this is back skin. Here's a single sensory neuron. You can see it's highly arborized, but non-uniform in the skin. And the logic to this anatomy is such that you can imagine if you just indent one of these afferents, you may not get a sensory percept, but you need the sweeping, like stroking movement stimuli to turn on a sensory percept as gentle stroke, for example. The second paper from the Anderson group, here they did a number of really cool studies. So here they used the genetically encoded calcium indicator Cmap into these MRGPRB4 neurons and recorded calcium transients in the spinal cord. And what you can see here is that when they gently stroked the flank of a mouse, they saw firing of these neurons. However, that wasn't the case when they gave a painful stimulus. Okay. Likewise, they did this condition-place preference assay with an activating dread approach. So the idea being here is that you do some training over the course of several days. One chamber, you give the inert ligand CNO, which will turn on the activating dread to activate all these neurons versus saline, the negative control. And then on the final day, you just ask the animal where you prefer to spend your time. And they do prefer to spend their time in the chamber where these neurons were activated. So all this is consistent with, based off the anatomy, the firing, and this condition-place preference with these neurons being putative gentle stroke neurons. Now, I will say there's been some maybe controversy, if you would, or the jury's still out on the true nature of these neurons, because there are only a handful of papers really studying these neurons, and now they date back 7 years. Likewise, this particular experiment with this condition place preference, these neurons are everywhere there's hairy skin. So when you're turning on these neurons, what does the animal perceive this as? Maybe the animal feels like they're being touched everywhere at once. And is that really physiologically relevant? So sparse data with these neurons in terms of publications, and these neurons have never been implicated in any natural, ethologically relevant social behavior. All right. And this is what we specifically sought out to accomplish, and our as an entry point into this project. And our rationale being, what if we use light to turn on these neurons focally to do transdermal optogenetics? Unlike cannulating an animal in the brain, but with these peripheral sensory neurons, because they tile the surface of the skin and they're very superficial, we could just shine light directly to the skin to activate them. And if we did that, could we identify a more ethologically relevant behavior? Okay. So here we got our hands on that Cree, and we crossed it to AI32 mice, a Cree-dependent channel-rhodopsin. This channel-rhodopsin, blue light sensitive ion channel, also has a green fluorescent tag, so we can visualize these neurons. So this is just showing you our genetic targeting strategy works in these mice, and this pattern looks as similar to what's published. We don't see any overlap with the CGRP nociceptive population, some overlap with IB4, no overlap with these large diameter LTMR neurons. One thing now, just make a subtle point maybe for there's some context or aficionados in the somatosensory field, is that these neurons are reminiscent to pain neurons in terms of their anatomy and their wiring, but they're atypical, if you would. They're still C fibers, but the perception that they generate may not be painful. All right, and here are just the terminals in the spinal cord. This is consistent with known expression patterns. And as I mentioned before, sometimes these neurons innervate or affiliate with hairy skin, hair follicles, which you can see here. Okay, just another slide, a little bit in the weeds, just for definition purposes. So these are lineage neurons. All right. So this is this RNA in situ hybridization with RNA scope, and the take home here is that with this targeting strategy, we're hitting 100% of these B4 neurons, but we also hit a few of their related family members, these MRG-PRC11, MRGD, and MRG-A3. I won't show you all the data, but we've done related experiments with MRGD and A3, and we don't see the same behaviors that I'll show you today. So we think the things that we're showing you are really driven by this B4 population. We don't see any overlap with this TRPV1 nociceptive population. All right, so how does the behavior look? We stimulated these neurons in different areas, but we focus on the back skin because we reason that the back skin is an area that's accessible from one mouse to another and may be important for social behavior. So these are high-speed video recordings and also black and white, but this is blue light that I'll be pulsing. So here you can see I'm pulsing blue light. This animal sees that we're there, but he doesn't really care, doesn't really respond. But look at the experimental animal. This animal is responding like it's kind of being pushed down on its back. We think this is definitely a touch behavior. I won't show you other data, but if we do the same experiment with a TRPV1 channel rhodopsin line, which is a pain line, the animals run away from the light. They try to get away from it. Or if we do this with an itch line, the MRG-A3 line, the animals scratch where we shine the light. So we think this is a touch behavior. Okay. So this is how it looks. The animal is just kind of laying flat as we shine the light there in the back. Here's just some quantification. Okay, we see it's hot. If we just measure how much they lower to this light and lay flat, a nice statistical significant difference comparing our experimental to control animals. So we next asked the question, well, we don't think this is aversive based off our data with some more known aversion lines, but is this a neutral posture or behavior from the animal, or could it be even rewarding? So to do this, we adopted this an optogenetic condition place preference paradigm. Okay, so the idea being, whenever an animal is in this one chamber, it'll get blue laser light to turn on those neurons versus green light as a negative control. We also add some other cues into these cages so that the animals can learn to make the association. Okay, but these cues have a baseline; they're neutral. Okay, so the way we do this, the first 3 days of this experiment is this a baseline. We're just making sure that without the laser light, there's no preference for one chamber or the other. For example, animals don't prefer coconut over almond. They're equally, the mice like them equally. And then we do this for 3 days. We do this conditioning. And then on day 7, we just ask the animal which chamber they prefer to spend time in. And we can see that they do prefer to spend time in the chamber where these neurons were turned on. Okay, so this is consistent with activation of these neurons in this particular paradigm through the backskin is a rewarding, reinforcing behavior. Okay, so with that in mind, so we have this posture and we have some implication that the animal may be perceiving this as rewarding, but what the hell is this, right? And we spend a lot of time thinking about this. You know, is this a natural behavior? And I'll tell you about 2 phenotypes that we think are linked to this, or try to convince you of that. So one thing we did, and I'll say these are all females. All the data I'm showing you today are females. And if people have questions about why we focus on females over males, we can get into that in the Q&A, for example. But anyway, one thing we did here is just look at 2 animals, 2 cage mates, and we studied their behavior, and we're looking for any natural behaviors that may look like this, what we're doing, inducing with optogenetics. And lo and behold, we do find times where I'm going to anthropomorphize a little bit here, but where one mouse will get on the back of another and like press and almost massage. And this recipient mouse kind of just like lays flat. Okay, looks eerily reminiscent to what we're inducing with the optogenetics. We're calling this a conspecific crawl, the same-sex conspecific crawling posture. And we believe that this may be this natural behavior. And I'll try to convince you of that today. Another thing this looked like to us is this lordosis, this female sexual receptive posture. So this circuit, this lordosis behavior has been well studied in the literature, but mainly more so in the context of like olfactory cues and visual cues. We do know there's a touch component. As a male is going to mount the female, he is like pushing down on her back to get her to lay flat for mounting. And we thought maybe, you know, what if, in addition to this sort of behavior, what if also when we turn these light onto the backs of the females, they're perceiving this as maybe a male attempting to mount and they're adopting like this posture. Okay, so I'll try to convince you that some of this may be true. All right, so let me show you the social interaction paradigm. Okay, so we have cage mates, but then we separate them for about 30 minutes. And then we just reunite them in their home cage. And then with the idea being after being separated and coming back together, this will increase the likelihood that they'll want to engage and socially interact back in their home cage. And then we record their behavior for these 20 minutes. This is where we first saw that thing we're calling conspecific crawl. I'll just show you examples of this. And on top, these are our optogenetically induced postures. And I really want to drive home the point that we think these natural behaviors, which are shown at the bottom, that we are mimicking them when we turn on these neurons in the back with light, with optogenetics. Okay. Now, if this is true, can we prove this? So to prove this, we reason that if we genetically ablated those neurons and then did these assays, and then we'll just look in this recipient mouse. Does she respond normally when her friend gets on her back to massage her, okay? or touch her back in a socially relevant manner? So to do that, we genetically ablated these animals, and to do that, we return to this Cree mouse line. It has a Cree tomato or M-cherry TD tomato reporter, so we can visualize these neurons. And here we crossed it to a Cree-dependent diphtheria toxin, or DTA, to kill these neurons. And this is just shown here. So here is a wild type or a control animal. Here are the neurons labeled in red, this other population in green. This is completely black here because we've killed these neurons, and we've left this other population intact. So this is a specific genetic ablation of these neurons. We're ablating these neurons in the first week of life around postnatal day 5 when this Cree turns on. So one of the things I'll show you, we had to really characterize their behavior because we're not doing the behavior until adulthood. So we wanted to make sure that there were no other primary deficits in these animals such that whatever phenotype we may see, we could easily interpret it correctly. Okay. All right, so we noticed that developmental milestones were intact in these animals when we ablate these neurons. They grow normally, their weight is fine. Their sensory and proprioceptive reflexes are all intact, so this looks good. Another behavior seen in pups, this ultrasonic vocalization, where if you separate a mom from their pup, the pups are going to cry for mom to come back and localize them and find them. This behavior is completely intact when we ablate these neurons, no deficit there. Their locomotion and motor behavior is completely intact. If we just look at the animals in an open field arena, they walk around normally. They don't spend time in one compartment of the open field, for example. We look at a rotorod test, which is just a test of their motor function and ability. No separation away from their wild type littermate controls. This test was useful. This social paradigm, which is another commonly used assay, where we give the animal a choice between engaging with a live mouse versus a toy inanimate object, a toy lion in this case. Normally, if there's no social deficits, a mouse prefers to spend time with a live mouse versus a toy. And that's the case for both our controls and our ablated guys. Okay, they prefer live mice over this toy. So they don't have a generic deficit in social behaviors. And this makes sense too, because this phenotype is driven by visual and olfactory cues, which should be completely intact in our animals. Then the last bit of data I'll show you, this us really thoroughly phenotyping these animals. We ran a gambit of depression and anxiety-like behaviors, because you can imagine that if an animal grows up without this touch population in early development, they may grow up to develop some of these anxiety or depression-like behaviors. So we tested this, and the upshot I'll just tell you now is that we don't see any phenotype. Here's this one test that people in the field like, this novelty suppressed feeding, where you put an animal, a hungry mouse, in a novel environment and look to see how fast they go to eat the food. If animals are anxious or depressed, their latency to eat will be much reduced, but we don't see a phenotype here. This sucrose preference, animals like things that are sweet, but if they're in a state of anhedonia, things that are rewarding may not be as rewarding anymore, but we don't see any deficit in their preference for sucrose. The splash test, mice like to have a clean coat, so if you muddy their coat with sucrose, for example, they really want to rigorously groom it off. Animals that are anxious or depressed, let themselves go, if you would. They don't care about their coat. No deficit there. And then finally, this really canonical test, the forced swim, where animals swim around, but animals that have depression or anxiety-like behaviors, this kind of lay there and don't move into and have a high % time immobile. No phenotype there. All right, so now let me get back to this assay. Now that we can rule out a lot of other trivial explanations, these mice by and large seem quite hardy and fully intact. Okay, so again, the experiment is that we're looking at animals engage in these with their cage mate, and we're scoring for how they respond when their cage mate gets on their back to kind of rub and touch their back. And lo and behold, we do see a deficit that's right at statistical significance, where when we ablate these neurons, these animals have less of that posture, that back lowering posture, to being touched by their cage mate. Now, you could look at this data and say, well, the controls do this behavior more just because they have more opportunities. Maybe they're touched more, so they display this more. So we plotted this data in a different way, where we looked at the opportunity or the rate in which this behavior could occur. So we're looking at the number of back lowerings divided by back touches. And when we plot the data like this, it's even more striking. Okay, these animals do not respond normally to being engaged, touched on their back by their cage mate. Okay, so at this point, we can say that these B4 neurons are both sufficient and necessary for this ethologically relevant social touch behavior. All right, just more sort of negative controls to show you that this is really specific to this social touch. So if we look at self-grooming or allo-grooming, so them grooming themselves or them grooming their neighbor, no deficit in this. Nest making behaviors are intact. And even just them initiating these touchings to their friend, their cage mate is intact. So really, this deficit is specific to this social touch on the back, not for generic social interaction. All right, so hopefully I've convinced you that these neurons appear to be sufficient and necessary for this what we're calling a conspecific crawl. But what about sex in this lordosis posture? All right, so one of the first things we did, this engrossing ourselves in this lordosis literature, a place where we're not lordosis experts, but one thing about this posture is that it's well known that it can be modulated by the estrous cycle. So when females are in their estrous stage, that this posture is more responsive. So we just said if we do this optogenetic activation across the estrous cycle, how will this look? And it looks quite flat. Okay, no matter if animals are in estrus or not, we're able to induce that back-lowering posture through the back. And moreover, we did this experiment where we overreactomized the animals. So we removed their source of estrogen surgically. And maybe you can just focus here. When we remove estrogen surgically, we do not lose the ability of animals to do that back-lowering phenotype. So these data together show that this posture is not dependent upon ovarian hormones, okay? We didn't stop there because, maybe these neurons are still involved in this sexual behavior, but just not these neurons are not regulated by ovarian hormones. So the real tests that people use in the field are these lordosis quotient assays. And when doing these mating assays, they're a little painstaking. You can't just put a male and female together and say, will you mate? But you need to control this in a much more robust and rigorous fashion. And the way to do that is the experimenter, we control the animal's estrous cycle, okay? So to do this, you need to, this is standard in this field, overreactomize the animal. So you remove their estrogen, allow 2 weeks for them to recover from the surgery, and then we exogenously provide their estrogen and progesterone. So we determine when they're going to be sexually receptive. So this is why you can really study this in a well-controlled manner. Wait a week, and then they get these 3 lordosis quotient trials. And the way this works, you need to do this in the dark cycle. This is when the male will mount. So the lights go off at 7, so we need to come in at 8 or 9 p.m. to do these experiments. And then we pair these animals and to a stud male, and we're looking for 20 mounts or 20 minutes, whichever comes first. And then we're looking at the number of receptive female responses over male mounts. This is called a lordosis quotient, or sexual receptivity, just the amount of time that the female lays receptive to the male mounting. Okay. So these are the standard assays to measure sexual receptivity in rodents. And one other thing I'll say before I show you the data, we do these 3 lordosis quotient trials. So the idea being, you test the animals 1 week and their sexual receptivity is at a certain point, but then the animals learn what sex is and it's rewarding and they get used to the movement. And then, so by the 2nd and 3rd trial, you see an upward trend. The females are getting better. They're getting more used to performing this sexual receptivity to the male mounts, okay? All right, so I'll show you the wild type and then the ablated guys. So this is what we see. So when we look in the first week with wild type females, their lordosis quotient or sexual receptivity to the male mounts is around 40%. But the 2nd and 3rd week, these things trend upwards. And this is well documented in the literature. We see the exact opposite trend when in our animals when we ablate those neurons. They start around 50%, but then by the 2nd and 3rd week, their sexual receptivity is much lower. It's greatly diminished. What we think is that this first trial This is the first time this animal is being mounted sexually by a male. They don't quite know what's going on, but those neurons are not there, so that reward signal is not there. So then the female may have no reason to believe that this is a useful behavior, and it may actually be aversive to her because there's a male on top of her mounting, but maybe that reward signal is not being sent to the brain, and now this is why the receptivity is much lower across time. She's learned that I actually don't like this. This is not rewarding. Okay. This is how we're interpreting these results. All right, so just to wrap up what I've talked about today. So these MRGPRB4 skin-specific sensory neurons appear to be both necessary and sufficient for these social touch behaviors, this conspecific crawling phenotype, and maybe this lordosis sexual posture. Work that's been really driven by Melanie in the lab. I didn't have time to get into it today. Maybe we can chat offline if people are interested. It appears that these neurons are necessary for resilience to stress, okay? But that's a different story. It's too much to put in here. And this lastly, what we're doing now is we're currently testing the hypothesis that turning on these neurons in the skin is engaging oxytocin circuitry in the brain. It's well known that oxytocin is a neuropeptide that's involved with social behaviors, including conspecific touch and sexual behavior. It's possible that when we turn on these B4 neurons, we're also activating oxytocin release in the brain. Or when we ablate these neurons, we're not engaging oxytocin as much, and that's the reason for some of the phenotypes. We're currently testing that by combining our optogenetic B4 line with fiber photometry imaging in the brain to also record oxytocin at the same time we do these experiments, and these are ongoing. So with that, I'll stop. I just want to thank, again, we opened the lab 2 years ago, so I just want to thank these brave souls who came to join a new PI. I didn't have time to really talk about some of our other collaborative work with our friends here. Thankful for our early funding sources, and thank you all out there for your attention.
Yeah, wonderful talk, great. And I will be clapping because everyone else is sitting in front of the screen and can't. This was wonderful. I have a few questions. So the first question that I want to ask, because you kind of asked for that question, was why females?
Yeah.
Like arguably cuddling isn't exclusively a female thing.
Yeah, no, wonderful question. We chose to focus on females over males because male-to-male social interaction has the confound that a lot of male interactions are driven by aggression, at least in males. Male mice, there's like this hierarchy in the cage about who's dominant and who's subordinate, and we didn't want that as a confounder in these experiments. We thought females would be more willing to be to bond with one another versus fight one another, and there's definitely precedent for that for sure.
Great. So a slightly related question, maybe. What about child rearing? It's common for a lot of mammals to, in a way, bond through touch with their family. Do you see any effect in that domain?
No, it's a wonderful question that we keep asking ourselves. We haven't tested that specifically just as of yet. What we need to do is, we breed these animals and let them grow up and do these tests, but we need to take these animals where we ablated those neurons and give them the chance to be mothers and rear their litters and actually study that intensely. We haven't done that, but that's on our long list of to-do items. Yeah, you could imagine that without having this ability to sense at least this form of touch generated from these neurons, that those animals may not be the greatest moms for sure. Yeah. And related to that, because we see a phenotype with like the sexual mounting and that they don't respond as much to the sexual mounts, we don't even know if they would give if they would have litters as often as wild type controls, if they'll even be receptive enough to be for us to do that experiment. We'll know the answer to that soon, but
oh,
yeah.
that is very interesting. Yeah, it's right. I mean, like there must be an evolutionary pressure for having these fibers. No, like why else would the animals have it?
Yeah.
So I very much like thinking in terms of what any system is useful for, and like here with procreation, it's very clear that there is one line of that.
Yeah, yeah. But for this con-specific crawl, like what's the evolutionary, like where does evolution fit in with that response? Maybe unclear. We also study pain in the lab, and one thing that we've been seeing through the years anecdotally, and Jeff Mogul's lab in Canada has reported on this. When females over males, actually, when female mice are in pain, if there's one mouse that's in more pain than others, they'll kind of cuddle around that mouse and like rub it and stroke it and really like engage with that animal. Females do that behavior a lot more than males. Males kind of, your buddy's in pain, they kind of don't care and walk right past it. So maybe if these neurons are like wired for this form of touch, and maybe you want to have extra receptivity in times of pain or depression, where you're going to respond to your friend on top of you and turn on reward circuitry. Another related question, you didn't ask this, but I'll just chime in, that we're quite interested in, is that this social touch should be, you should be able to change the valence, right? Just imagine like touch from a friend versus touch from a stranger. The same neurons may be activated, but it's all context dependent, right? If you were startled from a stranger touching you from behind in the back, you're gonna respond not in a good manner versus if your wife had done the same touch and you were expecting it. So that should be the case. And if that's true, like how does the nervous system figure that out? You would imagine that the sensory neurons in the spinal cord may be agnostic to the form of touch, but somewhere in the brain, it's making meaning of like what that touch is and how you should respond. That's a question that I think, we want to pursue further. It'll take time, but.
So you also, oh, hold on, wait, here we have a question. So we have a question by Farousan Farahani, who asked, I'm sorry, maybe I missed it during the presentation. Are these fibers located only at the back? Since for most animals, sexual mounting happens at this position, I guess they should be only located in the back.
No, it's a wonderful question. So these neurons are everywhere in the body. There's hairy skin. So if we shine the light, for example, to the ears, the animals like respond like they're being touched on the ear. Wherever we shine the light, the animals give us like an indication that they feel the touch. But we just thought this back would be like really relevant to these social behaviors. A related question that we're thinking about now is that it's possible that these neurons, because we see like this deficit in sexual mounting, we're attributing that to the neurons in the back skin, but it's possible that these neurons also innervate the vaginal area. And if there's some deficit there, maybe the females aren't responding. It's the back and also the lack of these neurons in the vaginal area. We need to test for that. That's another thing on our to-do list.
Oh, that's very interesting. Like maybe you could find a way of inactivating, say, only the front part of the front 2 thirds of the rodent.
Yeah, that would be really cool. We need to figure out a cool intersectional strategy or a viral strategy to do that. That would be really cool.
Yeah, I mean, like couldn't you somehow only illuminate the front 2 thirds or something with something that blocks activation?
Yeah, we've talked about that, or putting some sort of mask on or coat on the animal where the light only hits one part of the body and not others. And a related question, I'll keep throwing all these thought experiments out that I don't know if we'll get to them. One could imagine that depending on like where you turn these neurons on, you may get different activity patterns in the brain. If you turn them on in the back and it's a socially relevant like circuit, maybe you hit one circuit in the brain, but if you turn them on somewhere else where the animal isn't used to like being touched there, then maybe it's like aversive, or it doesn't tap into that social reward, and you may see a different signature in the brain depending upon where you focally activate these same neurons across the body. That's something we should get around to trying.
I mean, another area where you'd expect a strong response would be the front when it comes to children. No? Like baby mice will probably try and get at the milk somehow, and
exactly.
And like this should be a prime candidate for triggering that set of reflexes.
I agree, and then that totally taps into oxytocin circuitry if we can make that connection. Yeah.
Oh yeah, this is wonderful. So there's one more question, also related to what you mentioned, which is resilience to stress. Now, like we assume that this kind of like pro-social human-human interaction is a big component to the human stress response. What can you tell us about the rodent stress response there?
Yeah. It's a wonderful question, and there are lots of labs who just specifically study the stress response. We stumbled into this a stress behavior, which I alluded to but didn't show, because we threw the kitchen sink of tests, behavioral tests at these animals. I showed you some of it, not all of it, and we couldn't really find much of a phenotype. These mice are like quite resilient. It could be developmental compensation because we killed these neurons so early. It could be that there's such a small population is why we didn't see a phenotype. So then we just decided to give these animals some common stressors that people use in the field, then go back and do these tests, and now we see like this massive separation. So that just tells us that you do need these neurons early in life for animals to respond, to be resilient against stress in adulthood. Why that's the case, we don't know. Maybe, again, I keep talking about reward circuitry, dopamine perhaps, or even oxytocin. Maybe, not having that signaling early in life or from these neurons makes you less susceptible to later stressors in life. We don't know the answer to that as of yet.
Hold on, it makes you
makes you more susceptible to stress.
Okay, great.
Sorry. Thanks for that correction.
I was just making sure that I remember the sign right of that research.
Yeah.
It's interesting. When my kids were little, they had this book that introduced evolution. It's beautiful. It's called Grandmother Fish, and it takes the ability to cuddle as the defining criterion of mammals. It basically says at first everything was a bit like a fish, and then later on we learned how to cuddle, and that's when we became mammals. And it's just a beautiful thing, and it's nice how your research in a way directly ties into this simple evolution story for little kids.
Yeah, I should tie that into the next intro to talk.
I should see if I can still find it and find a copy for you. In any case, let's thank Ishmael again for this amazing talk. And
thanks.
Let's thank the whole audience for joining us here. This was a wonderful talk and very enlightening. I like how it's like, in a way, it's systems neuroscience, but it's in a domain where not everyone has been doing it for decades. So this is just wonderful.
Yes. That's true.
Okay, great. Thanks so much.
All right.
Thanks, everyone.
Talk to you. Bye-bye.
Bye-bye.
Always try to, you can be as encouraging as possible. And last note is please spread the word through Twitter using the hashtag NMC3. All right. Without further ado, first up, we have Brian Barry from University of California, San Diego, who will be talking about power law decay and eigenvalue spectra of neural population data. Take it away, Brian.
Awesome, thank you. So hi everyone, I'm Brian. I'm from Voitech Lab at UC San Diego, and I'll be presenting on this talk relating the power law decay of power and eigenvalue spectra in neural population data. So in this talk, I'm going to first introduce the context of power laws, and then I'll dive into our research question and how we analyzed both neural data and simulated data to investigate it. So you may be familiar with how various kinds of electrophysiological data exhibit power law statistics. For example, the power spectrum of LFP activity is power law. So the power spectrum here, which shows the powers and frequencies in the signal, display this power law shape, meaning power spectral scales as a fraction of the frequency. When plotted in logarithmic axes, this is exhibited as the linear decrease. When a line is fitted to this log-log spectrum, as the slope is the exponent of the power law. So this shape raises the question, is the brain poised at criticality? So originating from physics, criticality is a characteristic of certain high-dimensional systems consisting of interacting units or particles, where the pairwise correlation of two units is a function of the inverse of the distance or the time elapsed between those two units. In other words, temporal and spatial correlations are scale-free. It's best to illustrate criticality with an example. Canonical system is the abelian sand pile. So in this model, sand is stacked vertically on a grid, and wherever sand is stacked more than 3 units high, the next time step, 1 grain is distributed to its 4 nearest neighbors. So the evolution of this model kind of looks like this, when 1,000 or so grains are stacked in the center. So critical spatial and temporal dynamics are reflected in these events called avalanches, which are clusters or bursts of threshold events. This animation here shows another 2-dimensional critical system, the Ising model, where the avalanches are sets of connected units, like these black islands here. Zooming in displays how these are distributed without any spatial scale. In other words, it is fractal or scale-free. If we measure the sizes and durations of these avalanches, as in these figures here, we find this power law shape. And as you can see, they are related. So neural activity also undergoes avalanche-like activity. Local field potentials, for example, when exceeding 3 standard deviations or some other threshold, have very similar distributions for their sizes and durations as these figures above. Power laws continue to appear in neural data. I discussed the power spectrum earlier, but this other measure, the eigenvalue spectrum, is also power law shape, as found in Stringer et al. 2019. The eigenvalue spectrum, or eigenspectrum, represents the distribution of population codes, each of which is made of contributions from certain neurons. And each code is orthogonal to the next. So the eigenspectrum is obtained from principal components analysis, dimensionality reduction technique, which is the eigenvalue decomposition of the covariance matrix over time. Intuitively, this represents a balance between, this power law shape represents a balance between efficient and robust encoding. So the similarities between these two spectra leads to a question, are the power law exponents of these two spectra related? And if so, does their relationship depend on population size? The latter question builds on the scale-free theme to see if a small sample of neurons would represent the same critical dynamics as the whole. So the reason why we're interested in these two spectra is to see if the eigenvalue spectrum, which is a kind of spatial statistic, is related to any temporal statistics, as in those found from the power spectrum, which are also signatures of population encoding. Also, PCA considers pairwise correlations, unlike other measures like avalanche analysis. So if these two spectra are related, we can potentially construct more accurate measures of population encoding. So to investigate our question, we computed the correlation between the power spectra and eigenvalue spectral exponents in some neural data. We hypothesized that interspectral correlation would begin to appear at a certain subset size. So we looked at population data from neuropixels, which are probes that pick up population spiking. And our data set consisted of 10 regions on 3 different mice from Stringer et al. 2019. So this is kind of what our data looks like. So for 1,000 or so neurons, we have firing rate on the y-axis, time on the x-axis. And so the general pipeline for each mouse region pair is we take increasing subsets of random neurons And for each subset of selected neurons, we decompose the subset using PCA and the Fourier transform to yield the spectra of interest. For the Fourier transform, we first sum the signals to yield a population vector. And these two figures show the spectra for one mouse region with subset size increasing from blue to magenta. Once we have our spectra, we use a spectral parametrization tool to fit exponents to each spectra. And we do this fitting and decomposition for many iterations, and then we compute the correlation between the power spectrum and eigenspectrum exponents. So here's some results for the first mouse in the hippocampal formation. This first set of figures shows the average exponent for each spectrum. You can see how the exponents seem to converge monotonically as subset size increases. These figures show the goodness of fit for both spectra, and you can see how the fits get better as more neurons are subsampled. And finally, we have the interspectral correlation as subset size increases. So this particular mouse region, it would appear that the correlation between the two spectra begins to appear at a certain subset size. So in general, the first two figures are representative of the general exponent patterns we saw in the rest of the regions. Overall, however, we find that the space and time decompositions were correlated only for some brain regions and in some mice. So this plot here is the average interspectral correlation between the two spectra. And you can see how correlation only occurs for around half or so of the mice regions, and statistical significance is sparse as well. We also found that there wasn't a specific threshold subset size at which any interspectral correlations began to appear. For example, in these three figures, we see the correlation as a fraction of, as a function of the percent of neurons sampled. And in a lot of regions, we see that correlation actually tapers off towards zero as subset size sampling increases. So in order to test the null hypothesis that a non-critical system will not yield power laws in the eigenvalue spectrum, we simulated independent colored noise time series where the ground truth value are the exponents of the power spectrum. So we're simulating signals where we already know what the power spectral exponent is. So for each exponent in the range of exponents we used, we simulated around 100 time series and followed a condensed version of the pipeline that we used for the neuropixels data. So once again, we're computing PCA on the set of signals to yield the eigenspectrum. Here's the eigenvalue spectrum for each exponent, where the exponent is increasing from blue to magenta. And then we compare the spectral exponents for both spectra. So as you could see, the eigenspectra actually do obey a power law, even though the time series are independent and thus certainly not a critical system. When comparing the two exponents, the eigenspectrum exponent in this figure is on this axis, x-axis, and the power spectrum exponent is on the y-axis. We see that these two exponents are highly correlated to one another. So the takeaway here is that more robust measures of criticality should be investigated besides just power laws, because the power laws in the eigenvalue spectrum and the interspectral correlations seem to be necessary but not sufficient measures of criticality. Another possible implication here is that the neural manifolds that we obtain from our data may be from non-critical or even unrelated activity. That's the end of my talk. Thank you for listening. And I'm ready for any questions you may have.
Great talk, Brian. So that's the applause that you cannot hear from the attendees, and giving in terms on behalf of the attendees. So we have a question right now from Jason Samaha. Thanks for the great talk. Could you unpack a bit what a negative or positive interspectral correlation means in terms of neural dynamics, example, in terms of spiking or LFP dynamics?
Right. So at this point, I don't think we're actually too sure how to interpret that. But that is a great question.
Got it. So as we're waiting for more questions, I had a question. So the eigenspectra is that, I mean, I have a few questions. So first is the eigenspectra, is that a measure of the spatial information, right? So does that mean as you go further away, you have fewer correlations? Is that what it's trying to get at?
Right. So the principal components in the eigenvalue spectrum, each principal component is a neural code or like a neural pattern. And so each principal component is responsible for example here, a certain amount of variance of the data. So right, so like the first principal components are going to be responsible for the most variance in terms of the patterns in the neural population activity. And as you go up in the principal component dimensions, they'll be accounting for less of the activity, if that makes sense.
Okay, got it. Okay, cool. And so we have one more question from Maxwell Shin. Are there any types of analytical relationships you can derive between the two spectra in addition to the empirical results you showed?
Sorry, can you repeat that? Also, is there a way for me to see the questions? Right
Yeah,
here?
you should be able to click the Q&A at the bottom. If you can go to the Zoom. Or I can read it again slowly. So the basic question is like, what you have shown are empirical results, but can you derive some analytical relationships from what you know about these two types of spectra, like some sort of like theorems?
Oh, right. So this is another question where we're not too sure because there's potentially some mathematical rabbit holes that can be followed here, and usually stemming from criticality. But it would be definitely interesting to see other kinds of analytical relationships we can find. But for now, we really focus mostly just on correlation.
Okay, cool, nice. If you don't have any more questions, and thanks again for the presentation. And so we'll move on to our next speaker. And let me make sure I get the order right. Yes, next up we have Cecilia Gallejo Caracedo from Spanish National Research Council. She'll be talking about the relation between LFP and population dynamics. Cecilia, the floor is yours.
Great. Can you listen to me? Okay, so thank you very much for the presentation, and hello everyone. I'm going to talk about the relationship between the local field potentials and the neural population dynamics. So first, the local field potentials are thought to represent the synaptic currents within a neural population. They are usually filtered in several frequency bands, and the important information about these frequency bands is actually the power varying with time. So from that same neural population, we can also record the firing rates of individual neurons. And from previous studies, we know that firing rate can actually be represented in a multidimensional space in which each axis represents the firing rate of an individual neuron. The collective activity between these neurons is actually a trajectory in this multidimensional space. And interestingly, this trajectory does not really span the whole space, but it is restricted to a low-dimensional hyperplane called the neural manifold. So we can actually translate the neural population activity from the single activation of the neurons to the time varying activation in this neural manifold, which are called the latent dynamics. The question we are addressing in this project is actually how these local free potentials from the neural population are related with the latent dynamics that ostensibly drive them. So to address that question, we use neural recordings from a monkey performing an instructed delay central task, in which the monkey had to wait in a center target and one of the possible 8 targets light up, but still the monkey had to wait to a go queue to start the movement. And we recorded from 3 different brain areas. For each area, we focused on the main function. That is, for motor cortex, we actually look at the moments on the task in which the monkey was actually moving, because the main function of the motor cortex is movement control. Likewise, for premotor cortex, which main function is preparation of the movement, we look at the moments before the go cue, because it's when the monkey was preparing the ongoing movement. And finally, we also look at somatosensory cortex. And for this area, we look at the feedback processing of the task. That is, a little bit afterwards, the movement was happening, and it indicated the position of the limb. So we simultaneously recorded the firing rate of the individual neurons and also the local field potentials. From the firing rate of the individual neurons, we extracted the latent dynamics, as previously explained. And in here, for example, we have 8 different latent dynamics because we had an 8-dimensional manifold. From the local field potentials simultaneously recorded, we filtered them in several frequency bands indicated in here. And we also extracted the local motor potential, which is nothing more than the moving average of the broadband signal. So the way we addressed the correlation between these 2 sets of signal was by means of the canonical correlation analysis. That is, specifically, we look for a linear combination of the latent dynamics that maximally correlated each of the local field potentials individually. That means we look at a linear combination of the latent dynamics that maximally correlate this yellow line, another one that maximally correlates this orange one. And so we have a different alignment of latent dynamics depending on the frequency. If we compare these latent dynamics with the true local field potentials that we were recording, we actually obtained a correlation coefficient indicating how similar they were. It is important to notice that the local field potentials are unique for each channel. And since we are recording from multi-channel electrodes, we're actually going to have several correlation coefficients per frequency band. And so we are going to have a distribution of correlation coefficients per frequency band. So moving to the results, we first analyzed the movement execution in motor cortex. And performing this canonical correlation analysis, we obtain a distribution of the correlation coefficients, which is shown here in these clear points. And also the dark point and the arrows just show the median and the standard deviation of this distribution. So we can easily see that depending on the frequency band we are looking, the correlation between latent dynamics and local field potentials varies a lot. Additionally, to give a little bit of significance to these results, we generated a surrogate data of neural population dynamics based on a method called tensor maximum entropy that generates this surrogate data, taking into account the original data and preserving the covariance of the neurons across them. So these surrogate data results are shown here in these black distributions. And the interesting thing is that there was not significant difference across frequencies, which means that the true signals, which are frequency dependent, cannot be found by chance. If we look at the other monkeys that we recorded from this same area, we can see that all of them follow this similar trend regarding the correlation between the latent dynamics and the local field potentials, which is that from the middle frequencies, the correlation was very low. As we look at higher or lower frequencies, this canonical correlation between the latent dynamics and the local field potentials increased. Moving to the premotor cortex, we repeated the same analysis, and we see again that the frequency that there was a frequency-dependent relationship. So this correlation changes with frequency. Interestingly, we also found the same trend of frequencies in both monkeys. We look in this area, and additionally, we see some differences with respect to the motor cortex. correlation, especially in the band 12-25, where we find this sort of peak consistent in all the monkeys we look. Finally, we also look for somatosensory cortex during movement, during feedback processing of the movement. And again, we find this frequency-dependent relationship that was kind of similar in both monkeys we looked at, and it was different from previous area. So just as a summary figure, here I saw the distributions of all the data sets we have from each area separated in frequency bands. And we can see clearly that there are some main differences between the areas, especially in the band 12-25. But not only that, if we look at higher frequencies, the correlation between the latent dynamics and the local free potentials in the somatosensory cortex tend to be higher. And happens the same with low frequencies and the correlation in motor cortex. But are these differences that we are looking due to looking at different brain regions, or are they caused because we are looking at different aspects of the behavior, that is movement execution or movement preparation? And to address that concern, we repeated the analysis from the same brain area. We looked at the canonical correlation between the latent dynamics and the local free potentials in execution, but also in the movement preparation. And we see that the correlation matches exactly, which means that it doesn't really matter the aspect of behavior we are studying. Additionally, we also look at the intertrial period in which the monkey was not engaged in any task. And we can see that when the monkey was not engaged in the task, the canonical correlation decreased. We repeated the analysis for the premotor cortex and see again that the canonical correlation during execution and preparation was exactly the same and decreased a little bit during the intertrial period. And finally, for somatosensory cortex, we see that the intertrial or resting period decreased enormously. So to see this analysis in a little bit more of detail, here we plot the canonical correlation execution, also the canonical correlation analysis during execution and during preparation. In this case, each dot represents a monkey, a different date, and also a different frequency band. And we can see that for both motor cortex and premotor cortex, the canonical correlation during execution and preparation was almost the same, independently of which monkey, date, or frequency band we are looking at. And we repeated this analysis during canonical correlation during execution and during rest, or the intertrial period previously mentioned. And we can see that for almost all of the cases, the canonical correlation during executions were higher than the same during the intertrial or resting period. But do we really need a neural population point of view to see these relationships, or does they also appear in a single neural level? To address that question, what we did is to find the correlation between the local free potentials and the firing rates of the neurons in the same channel, and also the local free potential in one channel with the firing rate of a random channel. And we can see that indeed, in most of the frequency bands, when looking at the correlation between the local free potentials and the firing rates within the same electrode and at a random electrode, the correlation was very low. And with just some examples, some exceptions for the high frequencies in which the correlation between the local free potential and the firing rate just in the same channel was a little bit higher. This is an example for a brain area and a specific monkey, but it is important to say that these results were quite consistent across monkeys and also across areas. And just to summarize this result, we see that the correlation with the correlation with the firing rates and the correlation with the latent dynamics. And we see that with the exception of those high frequencies, in general, for all the dates and monkeys and also brain areas, the correlation with the neural firing rate was very low, and the correlation with the latent dynamics was spread in a very wide range. So we actually do need a neural population point of view to see this relationship between latent dynamics and the neural population activity. And just to summarize, we found the relationship between the latent dynamics and the local free potentials that is actually frequency dependent, and this frequency dependent is constant across monkeys. However, it changes depending on the brain area that one is studying. And finally, and the most interesting thing is that it is independent of the behavioral aspect as long as the monkey is engaged in the task. So thank you very much for your attention, especially thanks to my co-authors for their work, and also thanks to NeuroMatch for giving me the opportunity of this talk. And finally, I'll address any question you have.
Thanks for the wonderful talk, Cecilia. You are right on time, so we have a few minutes for questions. So as we are waiting for, so there is first question from Emily Stephen. Can you speculate about the reason for the canonical correlation peak at 12 to 25 Hertz?
Yes, so we don't really know by SIR, but our intuition is that there has been reported decrease in the beta band, so 12 to 25 Hertz, during movement execution in motor cortex. So our idea is that this peak appears in somatosensory cortex and also in prefrontal cortex, but it doesn't really appear in motor cortex because this decrease in the activity. But we cannot be sure.
Okay. We have a question from Sergei Stavisky. Interesting results. Thank you for the very nice talk. Are the lower frequency LFPs phase aligned across these three cortical areas? Otherwise, presumably it would be hard to align to latent factors which span multiple areas, unlike individual neurons.
Can you repeat that?
So the question is, the lower frequency LFPs, are these phase aligned across the three cortical areas? And if not, it would be hard for the latent factors to align across these multiple areas, right?
Yeah. So I'm not sure how common or are these lower frequencies across areas, but for sure we have seen some differences in the correlation from different areas. For example, in somatosensory cortex, the correlation in lower frequencies was quite low, with the exception of the local motor potential. So I'm not sure if you can say that these local field potentials are shared across these cortex areas.
Okay, so in that case, so do you ever correlate the latent factors from one area versus the LFP from another area?
We actually didn't do that. It's a great idea, and we would certainly try because it sounds really interesting.
Okay, cool. And one question we have is, could you expand a bit more on why the correlation is much higher in the lower frequencies for latent factors than for single units?
Well, we actually can't speculate about that for sure. We can only say that the higher correlation that we found in the higher frequencies are probably because these frequencies are similar to the frequency of firing rate of the neurons. And so the other frequencies did not show this correlation in general lines because it's not at which the neurons are actually firing.
Okay, but there was one figure where you showed that the frequency, the correlation was higher even for the lower. Yeah, this one.
Yeah. So like the correlation within the firing rate, that is what is related to the frequency of the firing rate, is actually low for every frequencies except for the higher frequencies. And our hypothesis is that this is happening because the higher frequencies are much more similar than with the firing rate of the neurons, because the neurons fire at really high frequencies. But for the low frequencies, they are not similar at all, and that's why we are having this low correlation.
Okay, all right. So we don't have time for the last question, but I think Cecilia can probably look at the Q&A and try to answer it offline. We'd like to move on and bring our next speaker, Hamid Reza Abbaspour from University of Southern California. And he'll be talking about neural dynamics underlying naturalistic reach and grasp movements. The floor is yours, Hamid Reza. We cannot hear you.
Sorry, I was muted. Hello, everyone. Happy to be here. In this talk, I will be talking about the multi-scale low-dimensional dynamics during naturalistic ridge and grass movements. There have been significant advances on our understanding of motor cortical dynamics and how low-dimensional dynamics during neural population activity explain movement. In this talk, we would like to extend prior dynamical models in two directions. First of all, prior dynamical models have mainly analyzed spiking population activity to extract low-dimensional dynamics. However, we know that behavior is encoded across multiple spatiotemporal scales of brain activity, ranging from small-scale processes represented in spiking of neurons to larger-scale brain networks reflected in field signals such as local field potentials, LFPs. Therefore, we want to build neural dynamical models that are multi-scale and extract low-dimensional dynamics from combined spiking and LFP activity and compare them. Also, while some prior works have looked at decoding accuracy during naturalistic ridge and grass movements, the low-dimensional dynamics of population activity are relatively underexplored compared to some other conventional tasks. Therefore, we want to also understand and investigate the low-dimensional dynamics during naturalistic ridge and grass movements. Extracting low-dimensional dynamics from a combined spiking and LFP activity is challenging because these signals have different statistical profiles and timescales. Local field potentials are continuous and they have slower timescales compared to spikes, which are discrete, and we model them with binary spike events given their fast timescale and their biophysiological properties. We solve this challenge by building a multi-scale state space model in which the state evolves in time with linear state equations, and we model field signals and binary spikes given their statistical profiles. For example, if you look at the equations here, the first two equations give you the famous linear state space model, but the challenge is how do we also add the spikings that are related with the same latent state, and we add the third equation. We can then relate the behavior by a linear projections of these latent states, which are low-dimensional representation of the combined population activity. So the parameters of this model need to be learned with a machine learning method. We developed this multi-scale expectation maximization algorithm, which identifies all the model parameters in the presence of the latent state. I'm not going to go through the details of the algorithm. You can find the math in our prior work in 2019. So after having this multi-scale EM, we can now learn low-dimensional dynamics with spiking population activity, local field potential network activity, and also the combined version of them. And we can investigate the dynamical characteristics of the low-dimensional dynamics. But how do we investigate the dynamical characteristics? To do that, we take a close look at the state transition matrix in the state space equation. The eigenvalues of the state transition matrix directly and uniquely quantify two dynamical characteristics, the time decay and the oscillation frequency. The time decay is how fast the latent state decay in time given the response to an impulse response. And the time decay directly depends on the radius of the eigenvalue on the unit circle. Also, the oscillation frequency is how fast the latent state oscillates in time given an impulse response. Also, the frequency depends on the angle of eigenvalue on the unit circle. So since the state here is latent, we don't know what the state dimension is, and we don't know which eigenvalues in the state space are important. We have to have a way to distinguish the important eigenvalue of network dynamics from the ones that are not very important. Therefore, what we do and what we argue is that the eigenvalues that are important in network dynamics should appear persistently regardless of what state dimension the latent states were identified from. For example, we extract the eigenvalues from latent state space models from different dimensions. We put them all on top of each other, and the eigenvalues that appear persistently regardless of the state dimensions are the important eigenvalues of the network dynamics. For example, in this plot, the vertical clusters mean the eigenvalues that are persistently present in the state space models regardless of what state dimension we identified the model with. We call this diagram the eigenvalue dimension diagram, and we look for the vertical clusters on the eigenvalue dimension diagram. The vertical clusters are important modes of the system, and we call them principal dynamical modes of the system. And also, what I discussed that we want to understand the low-dimensional dynamics during natural distribution grass movement. What we do, we look at this natural distribution grass movement test performed by our collaborators at Bijan Pesharan Lab at New York University. In this task, there were no specific go cues or hold cues that would isolate any part of the movement. Monkeys naturalistically performed the task to diverse 3D locations in front of them, and the task was continuously performed, and there were no trial structure. And more than 100 channels of spike and LFE were recorded from premotor, prefrontal, and motor areas. And we also tracked the 27 joint angles on the arm and fingers as the behavior during this task. So now that we have these tools, what questions we want to answer? We want to understand how small-scale spiking network activity and larger-scale LFT network activity relate to each other in controlling movement, and how do they explain naturalistic movement. So what we do, we perform the multi-scale state-space modeling on spiking population activity, LFT population activity, and the combined activity of them. And we looked at the eigenvalues or the dynamical modes of the system. First of all, we observed that there existed several dynamical modes in the spiking population activity. As you see in this plot, the vertical cluster represents the dynamical modes that I just discussed. And we can see that the dynamical modes are located very dense around the centroid cluster, meaning they had persistent dynamical characteristics across the state dimension. That means that the dynamical characteristics of the dynamical modes are preserved across state dimensions. Then the question is, by the way, each of these clusters are represented by one color in this diagram. Then the next question is which dynamical mode was most predictive of the behavior? So what we did, we quantified the prediction accuracy of each of these dynamical modes or dynamical latent state modes. We calculated the prediction accuracy. And interestingly, in spiking network activity, one of them was dominantly predictive of behavior. We repeated the same analysis with LFE network activity. Again, we observed several dynamical modes in the LFE network activity. And interestingly, again, one of the modes were dominantly predictive of behavior. So this takes us to this question that now that we get this dominant mode in spiking network activity and LFT network activity, do they have any relationship with each other or not? Or are they separate? So interestingly, even though there were several distinct modes in both population activities, the one mode that predicted behavior dominantly had similar eigenvalue in both scales, and meaning it had similar dynamical characteristics, therefore similar time decay and oscillation frequencies. Therefore, we call this predictive mode that is shared between both of the scales the multi-scale predictive mode. Then the first question we had was, maybe this multi-scale predictive mode is shared between spiking and LFT network activity just because they are simply replicating behavior modes. So what we did, we did the same model analysis on the behavior time series, and we observed that the behavior modes had significantly larger time decays compared to the multi-scale predictive mode, and also they had significantly wider frequencies. So the multi-scale predictive mode was not shared between spiking and LFT network activity just because they simply replicated the behavior modes. Also, we wanted to see, we argued that if the multi-scale predictive mode was actually multi-scale, if we combine spiking network activity and LFT network activity and learn to unify the state-space model, do we identify, if we identify the same mode at the same location, it means it was really shared. So it would identify the same mode with the same dynamical characteristics at the same location. And indeed, when we learned a low-dimensional dynamics from combined spiking and LFT network activity, we observed that the same dynamical mode was identified at the same location. This further validates the fact that the multi-scale predictive mode was actually multi-scale. Also, the multi-scale predictive mode was not only shared between spiking and LFP network activity, it was also shared across animals, meaning even though the animals performed the naturalistic reach and grasp voluntarily and they opted for different strategies to perform the task, the multi-scale predictive mode had similar dynamical characteristics across them. And this again further validates the fact that this multi-scale predictive mode explains naturalistic reach and grasp behavior. The time decay of the multi-scale predictive mode was 1 second, and the frequency of it was around 0.2 hertz. We then questioned whether, because we identified many dynamical modes across experimental sessions on animals with this and scales with the same dynamical characteristics, meaning decay frequency characteristics. We then questioned, are both of these dynamical characteristics important in explaining behavior prediction accuracy? And we first looked at the decay values of the
Hamid Reza,
multi-scale
you have 1 minute left.
We looked at the decay values of the multi-scale predictive mode, and we observed that the multi-scale predictive mode indeed have larger time decays compared to other principal modes. Also, we built a multivariate linear regression model from the decay and frequency characteristics of the multi-scale predictive mode and other principal mode to the prediction accuracy. And indeed, we observed that both of these dynamical characteristics had significant contribution to the prediction accuracy. Therefore, both are important in explaining naturalistic behavior. In summary, we observed a shared mode in spiking and LFP network activity and animals. Therefore, this mode was completely multi-scale and it was predictive of behavior, therefore a multi-scale predictive mode. This mode explained naturalistic behavior, and also we propose that this is due to the integrated action of large-scale brain networks. Both decay and frequency characteristics of the multi-scale predictive mode explain naturalistic behavior. The 1 second time decay indicated that naturalistic behavior relied on integrating dynamics over longer time periods compared to the other modes, and also the 0.2 hertz frequency quantified the rotational frequency of the network dynamics. I would like to thank all my friends and my advisor Mariam at Shawnee Lab, our collaborators, in particular Bijan Pesaran, and all our funding sources. And with that in mind, I would be happy to take any questions. Thank you.
Thanks for the wonderful talk. We have a question open from Julian Block. Is it possible you're getting eigenvalues that are consistent across different dimensions, but correspond to different spatial modes? That is, same frequency and decay, but explaining completely different dynamics.
Can you repeat the question? Because my internet just cut out.
Okay. So the question is it possible you're getting eigenvalues that are consistent across the dimensions, but which correspond to different spatial modes? That is, same frequency and decay, but explaining completely different dynamics across different dimensions.
So if an eigenvalue has same dynamical, it has same decay frequency characteristics, meaning it has a same location on the unit circle, I'm not sure what the question, I'm not sure what they mean by spatial mode, but if the eigenvalue is located at a specific frequency, the dynamical characteristics of the latent state correspond to it is uniquely determined. So they can't have different dynamics given the same eigenvalue. So same eigenvalue would always result in same flow field dynamics, therefore similar dynamics in time. The only difference in dynamical system is the initial condition, but the dynamical characteristics will be similar.
Okay, great. As we're waiting for maybe more questions, I have where are you going to take this result? Like what are the next steps?
So first of all, since we observed that the information in naturalistic behavior is multi-scale, we can take advantage of it for near future neurotechnology. So when we want to build brain-machine interfaces, we could take advantage of local field potentials given the durability compared to spikes, which degrade over time. So one obvious one obvious advantage is we can use local field potential signals in future BCIs. And also it gives us the knowledge of the fact that the information is also there in larger scale brain networks, such as local field potential.
Okay, great. That's really interesting.
Thank you.
So if we have no more questions, I think we can wrap up the session. And I'd like to thank the panelists again for the wonderful talks and for the attendees for engaging with us so far. Thank you.
Welcome, everybody. It's my great pleasure and honor to welcome Beth Stevens to the NeuroMatch conference, 7 p.m. East Coast time. Thank you for everyone who's showing up today. So a little bit about Beth. Beth did her PhD at Maryland and the NIH with Doug Fields, and then did a postdoc with Ben Bars at Stanford. She's now at Harvard Medical and the Broad, where she's the director of the Stanley Center Neuroimmunology Program and also the Levine Family Research Chair. She's also a member of the Howard Hughes Medical Institute and the National the National Institute of Medicine, as well as a MacArthur Fellow. Beth's career, I think probably needs no introduction. She's made major discoveries every step of the way, showing, for example, how complement is involved in synaptic pruning, documenting the heterogeneity of microglia really throughout the lifespan and different states, which is the topic of her talk today. The format here will be Beth will talk for about half an hour, and then we'll have a Q&A session at the end. So please type your questions into the Q&A box, and we'll get to them at the end of the talk. Beth, take it away.
Okay. Thanks so much, Robert, and thanks for all of you for tuning in, wherever you are in the world. This is, I think, really fantastic that this meeting came together, and it's a really great opportunity to be able to share some of the work that we're doing in the lab. So probably, I suspect you haven't had that many talks that relate to the non-neuronal cells of the brain. So I'm excited to share with you some of the work we've been doing. And as long as I can remember, I've been interested in understanding how the other half of the brain contributes to brain wiring and synaptic function and development. And today I'm going to focus on one particular non-neuronal cell in the brain called microglia, which are resident immune cells. And these cells really have, over the last decade or so, really emerged as central players in brain development and function. But compared to other cell types in the brain, I still think we know remarkably little about their function. And I think that just opens up so many new areas and so many new questions. But it's really key that we understand these cells, because more and more evidence points to the fact that these cells are really contributing to a host of neurodevelopmental and neurodegenerative and other brain disorders. So if we're going to understand how they go awry in disease, we need to understand how they normally function. And so what I want to do today is just take you through some of the sort of background, how we got interested in these cells, and some of the work we've been doing to study their normal biology and their normal function in the developing mouse brain, and how that's contributing to new insight in how synapses, the connections between neurons, can become dysfunctional in the context of disease. So the term microglia activation, I put this in quotes because it's a term that's been used for many years to describe the fact that these cells, as our resident immune cells, they make up about 7 to 10% of the cells in our brain, depending upon where you look and what species you look. But these cells can dramatically change when there's some sort of perturbation in the brain environment. So that as their resident immune cells are the only cells not born in the brain. They actually, we now know from fate mapping studies that they derive from the yolk sac, these progenitors and the myeloid cell progenitors that enter the brain very early in development. In fact, so early that it's really, they're the first non-neuronal cell in the brain. They enter about E8, embryonic day 8 in a mouse, and then they colonize the brain over time. And these cells, when there is a perturbation, we've known for many years that they dramatically change morphology and shape, and they can change gene expression as well. And when you see in, for example, a pathological sample or postmortem brain, or in an animal model after some sort of a perturbation, this change in morphology from this process-bearing state to this sort of activated state has been described by many in many different contexts. So we know this happens. And it's microglia activation is really a hallmark of brain damage and disease. But what we don't really know, and this is really what I want to highlight today, we don't know when they've changed. And most importantly, we don't know how these cells contribute to different aspects of disease pathogenesis. And that's really what I want to focus in on today, is understanding their normal roles in brain physiological functions, especially in the context of synapses. And then we want to try to think about how they go awry and may contribute to different aspects of disease pathogenesis, especially relating to cognitive decline and cognitive function. Now, for many years, because of what I just told you, it's been observed by many that these cells become activated. And most people have just assumed that something else happens to the neurons, and then essentially that activates the glia. So they're sort of downstream, they're sort of secondary. Now, while that may be true, what's really kind of been game changing in the context of like how to think about microglia, at least in the context of some diseases, is that emerging human genetic studies, GWAS studies, more and more are starting to implicate these cells, microglia, in Alzheimer's disease and other neurodegenerative and brain disorders. So that means when you look at GWAS data, where most of the time you're thinking about the neuronal cells of the brain, what's really clear, for example, in the context of late onset Alzheimer's disease, is more than half of the common variants, the genetic variants associated with Alzheimer's, late onset, not the familial form. These genes are either expressed or enriched in myeloid cells, microglia. And even ApoE, which has been for many years well-known risk gene, this gene is expressed in microglia and becomes dramatically upregulated in the myeloid cells, both in the human brain and in animal models. So more and more of the genetics, at least in Alzheimer's, is probably the clearest example where the genetics is telling us these are cells we need to pay attention to. They're playing really key roles in disease. But still, how, when, what are they doing? What are these genes doing? So that's where geneticists and biologists and other neuroimmunologists need to start to work together to start to understand what the functional relevance, what the underlying biology is of the emerging genetics in Alzheimer's disease. And I would say the same is true for other disorders and diseases as well. So why can't we just go for the genetics and say, let's look at this gene, let's say CD33 or TREM2, and let's just understand what it does? The problem is that microglia have very diverse roles in development and in the context of disease. And this is work over the last maybe 7 to 10 years is more and more suggesting that these cells have lots of normal functions in the brain from development all the way through until aging. And they're incredibly dynamic cells. They really can play diverse roles, and that they, by the fact that they're immune cells, not surprisingly, are very plastic and dynamic. They have the ability to change states under different contexts. They're particularly sensitive to the brain environment and local signals. So for example, we know from the work of many now in the field that early in development, they play key roles in programmed cell death, not just in clearing up the debris, but also signaling to the neurons and regulating programmed cell death and apoptosis, which is a really important process in brain development. They're critically important as resident phagocytes, not just in clearing up sort of cellular debris, as I mentioned, but actually also clearing synapses, and not just any synapses, but specific synapses that are important for synaptic remodeling and synaptic refinement. And more evidence in the field suggests that they're also playing an important role in synaptic and neuronal plasticity, and even if manipulating microglia in different animal models can actually result in changes in both neuronal, synaptic function, but also behavior. And really, this is just the beginning of understanding what they're doing. But what we also appreciate is when there's a perturbation, whether that be genetic or environmental, these cells really dramatically change state. They can shift from this homeostatic surveying microglia into this inflammatory state, for example. They can, instead of just pruning synapses, which during development is normally a good thing, a normal process that helps to wire the brain, they can also, under certain conditions, become aberrantly phagocytic and start to prune too many or the wrong synapses. And at the same time, they can also help the brain by clearing debris, apoptotic cells, and even toxic proteins like amyloid. So the conundrum is that they play both beneficial and detrimental roles depending on the context. And at the moment, we in the field do not have ways to track these state changes, these markers. We don't have ways to know whether they're beneficial or detrimental. We have a handful of markers that label these cells, but at the moment, we haven't had a way to start to define these different states and relate these states to specific functions. So I'm going to tell you about some of the efforts in the field to be able to do that. And one of the things that's really kind of cracked open this area is the emergence of new technologies and techniques such as single cell sequencing, spatial mapping, that's being used and applied to be able to address some of these questions. So what I want to do in the first part of my talk is focus in on one function that we in the lab have been focused a lot on, which is their role in synaptic remodeling and synaptic pruning. I'm going to tell you about some of the work that we've been doing in the normal visual system of a mouse to try to understand how it is these cells sculpt synaptic circuits, what are the mechanisms by which they recognize and prune specific synapses, and that I'm going to tell you some examples of the same pathways we've identified in development can also become aberrantly regulated or dysregulated, and that can lead to aberrant or excessive synaptic pruning or pathological pruning in the context of disease. In other words, an understanding how they normally prune synapses is providing new insight in how they may go awry in the context of disease. So one of the things I think that's, in many ways that's contributed to our, lack of knowledge of these cells compared to other cells is we've really lacked the tools with which to study these cells compared to other cells in the brain until fairly recently. But thanks to a new reporter lines like the one I'm showing you here, this is a GFP fractalkine receptor mouse that was developed by Stefan Young's lab many years ago. It's been used by many in the field. That's enabled researchers to really start to look into the brain or in a slice of brain with live imaging. And what I hope you can appreciate is that microglia, there's several of them in this field, this is their cell body and these are all their processes, are dynamically surveying the brain's parenchyma all the time. So if we were to put a microscope over your brain right now, your microglia would be looking like this, probably. And if you overlay neurons sparsely labeled, like this one, you can see that they're surveying probably many things, but they're definitely interacting with these synaptic structures, both pre and postsynaptic elements. And so this, of course, got our interest a number of years ago when I started the lab, because we were interested specifically in understanding whether or not they were actively engaged in synaptic pruning or synaptic sculpting, which is a normal developmental process that happens in different critical periods in the brain. It's been really well studied in the visual system. So we decided it's one thing to see the microglia touching synapses in the brain, but to really understand whether they're actually phagocytosing and regulating pruning, we turn to a circuit in a system that's been really well studied in the context of synaptic pruning, and that's the visual system, and more specifically the circuit between the retina and the lateral geniculate nucleus, or the visual thalamus of the mouse. Initially studied in the cat and ferret by Carla Schatz and others, and now it's really beautifully studied in the mouse, where we have transgenic and other tools to manipulate the system. So on the right-hand side, I'm showing you a really oversimplified version of what this synapse, this circuit might look like if you were to zoom in on a postsynaptic cell in the visual thalamus, and if you were to label the presynaptic elements by anterograde tracers of two different colors, like which we can do with cholera toxin of red and blue, for example. So initially, and this is well established in the field, you can look at the postsynaptic cell and you can see that early in development, this postsynaptic cell is innervated by the inputs or the axons from the left and the right eye. But during this critical period, you see a refinement where some of the inputs get pruned away, the blue ones, while others get strengthened and maintained. This idea of use it or lose it, it's been well described in many systems, really well studied in the visual system. And the reason why we got excited about this is because we know this process is regulated by neuronal activity. And we also know that the less active inputs tend to be the ones that get pruned. If you overlay the microglia onto the circuit, we observed, I should say, Doris B. Schaefer in my lab when she was in the postdoc, right when we started the lab about 10 years ago, observed that microglia were intermingling between the inputs of the left and the right eye. So we were really well poised to ask, do they engulf specific synapses? If so, is this activity-dependent process? And if so, what are the mechanisms? And so what she did is use the transgenic mouse, looked at the microglia, indeed observed using high resolution 3D reconstructions that almost every microglia we surveyed during this pruning period were engulfing presynaptic elements. We could even see this by EM. And most excitingly, and I think this is really the key, is that when we manipulated activity in the two eyes, drove competition with either tetrodotoxin in one eye, blocking activity, or driving activity in the other, microglia were preferentially engulfing the less active input. So this was an important, I think, initial observation, because it told us that while the microglia were engulfing inputs, they were somehow receiving activity-dependent cues. It wasn't just a random cleanup crew, but they were receiving instructive signals or instructive molecules must be telling them how or which synapse to engulf. And that's really been the subject of many projects in the lab over the years. I'm going to summarize a couple, but I wanted to give you this background so that I could both describe the model system and then tell you what we've done in terms of trying to understand what the molecular mechanisms are. And I'll say mechanisms because there are actually several, it's not just one. But we began with a mechanism that actually made a lot of sense at the time, because when I was a postdoc in Ben Barris's lab, we unexpectedly uncovered a role for a group of innate immune molecules called complement in the synaptic pruning process. We weren't thinking at the moment about microglia so much, but through an unbiased screen and a number of interesting studies, we uncovered a role for a group of molecules in the developing brain that are traditionally associated with the innate immune system. And what these molecules do in the immune system, in your blood or in your immune system outside of the brain, is that if there was an apoptotic cell, a pathogen, or something you want to clear, these proteins called complement were as our first line of defense. Essentially, these are secreted molecules and they bind to or opsonize, and then that leads to sort of an eat me signal that macrophages in the periphery would then recognize and clear. Now, what's interesting about this is in the brain, microglia are the only cells to express complement receptors. And we showed over the years that these complement proteins like C1q or C3 actually do bind to subsets of synapses, which we can see with high resolution imaging. And what we went on to show is that if we genetically block C1q or C3 or any of these complement molecules or the receptor on microglia, we actually showed that there were sustained defects in pruning and synaptic connectivity. So this was one of the many mechanisms that regulate pruning, but it really to us kind of identified, microglia are doing this, and here's a molecule that's instructing them in how they go about recognizing synaptic inputs during development. But of course, it's never that simple in biology because it's never one molecule, at least in my experience. There's usually many other things involved. And when we started to think about, how is there specificity? Because synaptic pruning is a highly specific process, right? It's not all synapses that get pruned. And going back to that question of like neuronal activity, remember I told you that the less active synapses tend to be the ones that get pruned away. So we started to think about the following working model. And we do have evidence to support this model, but we still have quite a bit more to do. If you imagine two competing inputs, one more active or several more active and a few that are less active, competing for synaptic territory, you might imagine that microglia, because of the fact that they're surveying the brain environment, they're highly dynamic cells, they express an array of receptors that could recognize different molecules. One way this might work is if they're surveying the environment, they might recognize these eat me signals like complement, and then they could be specifically pruning the complement molecules tagged synapses. But we also appreciated that not all synapses get pruned. In fact, the whole axon doesn't get pruned away and the cell body doesn't get pruned away. So what's preventing microglia from just munching the entire axon? So we started thinking about, in addition to the eat me signals like complement, there might be other molecules that are telling the microglia don't prune. And indeed, there's a group of molecules in the immune system called don't eat me signals. One of them is called CD47. And the idea there is if a synapse, or in this case, or a cell has these don't eat me signals, even if complement was all over it, it wouldn't get engulfed. It's sort of stopping the phagocytosis, or sort of a don't eat me signal cue. So one way we envision this might work is that microglia, through their receptors, basically can read out the combination of cues on axons or synapses, and it's that combination, in other words, the complement tagged synapses that don't have the don't eat me signal, they get preferentially pruned away. Now, that's still a working model. We have some evidence to support that. We've published several papers on the topic, but we still have a lot of unanswered questions that we're actively pursuing. And this is really going to be relevant for disease in a moment when I'll tell you that we want to try to understand what stops and how to prevent aberrant synapse loss. We want to better understand how this is normally working. So one of the questions is, what's complement binding to at synapses? These are secreted molecules. They're secreted and expressed by glial cells in the brain, including microglia. They land on synapses. What's recruiting them to specific synapses? There must be some binding protein or receptor that's leading them to land on a synapse. What are those molecules? I'm going to tell you about some data on that in a moment. We want to better understand the role of activity in recruiting complement and microglia to synapses. We want to understand what's upstream in the neurons that's leading to this signaling pathway. And ultimately, we want to understand if this could be relevant to disease. Now, we have been, and I should say Nicole Scott Hewitt in my lab, has been doing a lot of IP mass spec experiments to do proteomic analysis of synapses to try to better understand what are the binding proteins for C1q and C3 and complement, to try to understand and identify candidates that might be expressed at synapses. And I'm not going to tell you about that work today, but there's been a lot of really interesting data that's emerging from that, that ongoing project. But we started to step back and think more generally, because a lot of our insight over the last decade has come from immunologists. And I think this is a really important example where if you just go into another field, ask what do these molecules or cells that are like microglia do in the immune system, I think it can provide a lot of new insight in how this might be regulating brain development and function, because there's a lot of shared biology, shared genes, and shared molecules, complement and microglia especially. So we went into the immune system and we started thinking, like, how is it that some of these molecules would get recruited? And so that led us to think about a very sort of fundamental mechanism, and that is that phosphatidylserine, which is externalized, is an abundant anionic lipid that's normally on the inner leaflet of a healthy cell in the body. But when there's programmed cells, when there's an insult or apoptosis or other signals, you can start to see a flipping of phosphatidylserine from the inside of the membrane to the outside. So you see the flipping. And the exposure of phosphatidylserine under these conditions serves as, in a way, its own eat me signal. It's basically sensing to the environment or to immune cells that there's something wrong here. It needs to be cleared. Now, this has been well studied in the body, in the immune system. And of course, if you damage and you actually cause apoptosis, it's been well described in the brain as well with neurons. But one of the questions that Nicole asked is, could this be happening in a non-apoptotic way? Could this actually be locally regulating synaptic pruning, not in the whole cell, not in an apoptotic way like it's been described, but actually in the context of a small structure like a synapse? Now, there's lots of molecules on the macrophage receptors that recognize phosphatidylserine, complement being one of them, but there's many others. So I thought, well, that's a really interesting thing, because macrophages and microglia have a lot of the same receptors. And indeed, even in the visual system, in the retina, it's been shown that there is evidence of a local removal of a structure, right? So that kind of led to the hypothesis, and this is Nicole's hypothesis, that basically in the healthy brain, she asked, do local externalization of phosphatidylserine on membranes of presynaptic axons or inputs, could they be flipping to the outside? And could that be recruiting molecules like complement or other eat me signals, or for that matter, microglia, to certain synaptic structures? Could this be one of the ways that it's regulated on the neuronal side of things? And so I'm going to just share very briefly, this is recently published work, but I want to tell you about it because we're quite excited about some of this data. And so to do these experiments, Nicole took advantage of a probe that you can inject into the brain. It's not yet BBB permeant, so you can't get it across the brain without injecting it. But it has been shown that this PSVU, it's called, is an annexin 5 mimic. It's very small. It's got very fast binding kinetics. It's calcium independent. And it is very specific for phosphatidylserine that's been exposed. And so she wondered, could she use this probe, not in the context of injury like it's been showed in the field, but can she use this probe to study normal physiological synaptic flipping of phosphatidylserine? Because it really hadn't been observed in the healthy brain before. So she injected this probe into a mouse brain over development during the critical period using ICV injections into the left ventricle. She used a control, fluorophore only, and then she looked on the contralateral side of the brain in the LGN and the hippocampus and other areas of the brain, but in particular, we're looking in the visual system after different time points, 24 hours later. And what she found is, one, there is really synaptic punctate labeling of PSVU at subsets of synapses. This was published just a few months ago. We wrote this paper during the pandemic. It came out in EMBO just very recently. So I'm just going to highlight a couple of the key figures. But what we observed was that PSVU, or phosphatidylserine, seems to be exposed at subsets of synaptic structures, which can be labeled with pre and postsynaptic markers. This is VGLUT2, which labels those retinogeniculate synapses in the LGN, and even subsets of those synapses co-localized with C1q, for example. And so she went on to then ask, do microglia engulf PSVU labeled material? And so for this, she did the same kind of eye injections, then quantified engulfment and showed indeed that they do engulf material that's labeled with phosphatidylserine. And moreover, when she looked in C1q knockout mice, there was less engulfment of PSVU. And so many questions now still left to address. We want to better understand how this is being regulated. Is this activity dependent? How could this regulate the flipping? We're very interested in understanding that, and Nicole's developing new probes to study this and image this. But we also appreciate that C1q in complement is just one of many molecules that could be regulating in this process. And so we started expanding into the literature, thinking about other interesting receptors and molecules that might be regulating this recognition and pruning. And one of them is super interesting. It's called TREM2. And TREM2 is relevant because it's also an AD risk gene. It's been well studied in the Alzheimer's field, and it's only expressed in microglia. And recent work by Michele Mattioli's lab a number of years ago showed that TREM2 is really important in normal synaptic pruning. And we teamed up with Michele in this EMBO paper and showed that not only is complement regulating phosphatidylserine mediated engulfment of synapses, but so is TREM2. And probably there's going to be other molecules that regulate this process as well. So we think this is a fundamental way that the neurons could be kind of exposing a signal that's bringing in these sort of molecules that could regulate engulfment. We think it's probably going to be highly activity dependent, context dependent, and it's a dynamic process. So we're now in the process of doing a lot of time-lapse imaging, using new reporters and tools to be able to try to study this process under normal physiological conditions. So now the question is, what about disease? Everything I've told you about has been development. But over the last many years, in parallel to our developmental work, we've also started studying this in the context of aberrant synaptic pruning in the context of disease. And synapse loss is a hallmark of many neurodegenerative and neurological disorders, and work that we and others in the field have done have suggested that some of the same pathways that regulate synaptic pruning by microglia, including complement, can become dysregulated in the context of disease. And so that leads that leads to this idea that maybe some of the same pathways could become sort of dysregulated to contribute to synapse loss. And several papers suggest that, at least in animal models. This is work by So-Yeon Hong in my lab, who's got her own lab now at UCL, who showed that almost a very similar mechanisms happening in the hippocampus early in Alzheimer's disease models. Work by Morgan Sheng's lab just showed a similar process in Alzheimer's models of tau. And others. So this is example of one mechanism, pruning, that's been studied now by several in the field, and we've identified mechanisms that we think may be relevant to disease. But I'm now telling you that pruning, we think, is probably just the tip of the iceberg in terms of understanding how microglia contribute to Alzheimer's and other diseases. And this is now where we're kind of zooming back out again and saying, well, what are the genetics telling us about biology and function? And I told you about one pathway, complement, one mechanism, or one function, synaptic pruning, but we're also realizing that these cells do so many other things. How do we start to put this together? How do we go from variant gene all the way to function and try to understand the mechanisms in between? And that's really where single cell sequencing, as I mentioned, has become, I think, a really important tool to start to bridge the genetics with the biology. And the first paper that was published a number of years ago now by Ito and Mitzlab was the first to identify in both Alzheimer's mouse models as well as in human brain, that when you use single cell sequencing to purify and sequence microglia in the brain, identification of disease-associated microglia populations were emerged. We call these DAM, disease-associated microglia. It's certainly by no means telling us that this is the only population, but it's an interesting one because it keeps coming up in all of our data sets. So the more single cells that's been happening, the more we see this disease-associated signature. So the question now is, what do you do with this transcriptomic data? How do you link this to function? And we and others have started to really do a deep dive by combining single cell sequencing in different contexts, both animal models, disease and injury models. But we also realized we better just understand their normal heterogeneity under just the normal lifespan of a mouse and just sort of try to collect as many microglia as we can, optimize the methods, try to understand how diverse these cells are. And once we do that, then go back to the disease models and see if we can sort of understand better how to bridge the transcriptomics data to the functional data. And so a couple of years ago, actually last year, we published a paper in Immunity that really brought together a lot of data that we collected. And this is Tim Hammond in collaboration with Steve McCarroll and others, where we sequenced almost 80,000 microglia across the lifespan of a normal healthy mouse to just ask, you know, how diverse are they? How heterogeneous are they? And what can we learn about these different states? This is now a large database that you can probe if you go online. We've also identified and developed protocols to make sure that these aren't artifacts. And this is a methods paper that Sam Marsh is about to put on bioRxiv, which is really important because if you're not careful, you can artificially activate microglia, which can really cloud the data interpretation. So we're going to be publishing this paper and sharing a lot of these methods to make sure that you know that a state you identify in microglia is biologically relevant and not technically an artifact of the dissociation. But in a nutshell, what we found is if you basically profile all those microglia over time, there is diversity. A lot of the diversity is over development. All of these different colored in the t-SNE plot clusters represent different subpopulations or states. And what we found is that there's a lot of really interesting data to really dig into to try to understand function. I'm just going to give you one super fast example because I'm kind of running out of time here. But this cluster 2 really sort of jumped out at us because what we found is that cluster, actually now it's cluster 4 in this figure, that it turned out this cluster, when we actually looked at what the genes were in cluster 4, it was telling us something about their function. And for example, if you looked at the top 10 to 15 genes, a lot of those genes that were in cluster 4 were the very same genes that Ito, Amit, and others have shown in disease-associated or DAM genes. They are suggesting immune recognition, lysosomal activity, phagocytosis, remodeling. We found that this population emerged just during development. And when Tim and Connor did spatial mapping, quite interestingly, most of what we found is that these cells were in the white matter during this developmental period. So we're now in a position to use the genes and the spatial mapping data to start to develop new tools to start to interrogate the function, not of all microglia, but cluster 4 microglia. So now we can knock out genes of interest. We can develop reporters for fate mapping. We can do imaging using reporters like that. And we're doing it in multiple species, so mouse, zebrafish, and even starting to do this in IPS microglia. So I think it really is going to take a combination of approaches, but this is the exact same approach we're taking to try to understand how these cells are changing in the context of disease like Alzheimer's, injury, as well as development. What's clearly emerging from now many, many data sets is there's convergence. So certain of these disease-associated signatures are conserved across all of these conditions, but others are going to be specific for the different context. So now we're in a really good position, I think, to start to go back, zoom back out again, and ask, how do we link the genetics with these specific states to specific functions? And I think this is going to ultimately give us new paths to therapeutics, because really, if we could find the detrimental state, the detrimental phagocytic state or inflammatory state, use single cell and other techniques to identify ways to label and manipulate them, that will give us new tools to start to identify and track microglia, and then ultimately develop new biomarkers and new therapeutics. And I think that's ultimately where we're headed, but it's going to take a village. It's going to take a large collaborative effort across multiple labs, multiple disciplines. And ultimately, it's going to really require the field to start sharing their data, sharing techniques and tools long before it's ready for publication, so that we can start to make some headway here. But although I focus on Alzheimer's, I would say what I told you today is relevant to many other disorders as well. So again, I think we're in an exciting time in the field, but we need to understand normal function before we can understand dysfunction. So I'll end by thanking the human microglia in my lab. This is just a sampling of them. This is a goofy picture, but it ended up on the cover of Immunity for the 50th anniversary edition, with many other labs that submitted their pictures. Lots of amazing collaborators, generous support. So yeah, so that's it. Thank you so much.
Perfect. Thank you, Beth. That was brilliant. So much like really interesting biology there. Okay, I'll remind you, those of you watching on Zoom, please type your questions into the Q&A. Those of you watching the YouTube simulcast, please put them in chat and we'll get them. Is there any known regional diversity of microglia in the transcriptome, for example, between different brain regions?
Yes, so great question. So I think there's emerging work from several labs and unpublished data from our own lab that if you now can purify microglia from different brain regions, hippocampus, striatum, cerebellum, there are differences, both at the epigenetic level. This is really beautiful work by Ann Schaefer's lab at NYU, and at the transcriptional level. So what I told you today is when you just basically take the cortex or the brain and purify all the microglia from a particular brain, not thinking about region. This is sort of the approach that the field started with. And that is in part because microglia represent a small percentage of the brain. So you need to get enough microglia where you can really get the power to start to untangle and look at different states. But now that we know what we're doing, I think now we're in a position to start to look in vulnerable versus less vulnerable brain regions, or even different circuits. And I think what we're going to find is that there are region-specific differences that are going to potentially be relevant to understanding disease vulnerability. So stay tuned. We're not quite there yet, but the field's definitely heading in that direction.
So what do you think about the differences between species, humans and mice in particular? Are there different classes of microglia in humans that you wouldn't find in mice?
Yes, so we and others are really starting to compare mouse and human and non-human primate microglia and just cells in general. This is definitely an area of huge interest. And thanks to some new tools, computational tools, for example, Evan McCosco, who's a collaborator of ours at the Broad, has developed a tool or an algorithm called Liger. Was published in Cell about a year, maybe a little over a year ago. These types of tools enable you to start to align data across different conditions and species, and to try to deal with things like batch effects and other things that can really throw off the analysis. By doing and applying tools like this to the data, human, mouse, non-human primate, and even iPS cells, we're finding actually a lot of conservation across species. If you don't use those tools, it's going to look like totally different data. So the take home there is the computational tools really matter. and also the depth and the number of cells that you actually sequence, and the number of other technical issues are going to also really matter. So if you're not careful, either if you're not powered, if you're not thinking about these different aspects, and if you just compare two data sets, mouse and human, even in the same brain region, it can look like they're different, but it's really not. So I think much more needs to be done in this. There are going to be some species-specific differences. There's already data to suggest that, but there's a lot of conservation, both of genes and of some of these states I've described, including this disease-associated state, which I think is quite exciting because it means learning in the mouse, which is easy and more tractable, can then be applied to looking at human tissue, right? If you know what to look for, you'll know how to do it, or you can start to bring the data sets together. So we and others are starting to do this now. And I think ultimately this data, if it's shared and accessible to the field, is going to allow the field to start to mine and look at this data in a very sort of holistic way.
Related to disease states, can you talk a little bit about dysregulation of microglia in Parkinson's, maybe other neurological conditions?
Yes. So as I mentioned, I think there's evidence now of microglia changes in almost every neurodegenerative disease model or brain that's been looked at. But what's been less clear about is sort of the chicken or the egg, right? Like, is they just responding to the brain just being sick and neurons dying and neurodegeneration, or are they actually contributing in a more specific way? For example, inflammation is a term, neuroinflammation even more specifically, that's used by many, but there's good and bad inflammation, right? So understanding whether and how microglia contribute to these diseases has been really hard. Now that Alzheimer's disease is kind of paving the way because the genetics are clearly pointing to microglia, it's now enabling us to look across different diseases and start to ask whether some of the same things we see in one disease is relevant to another. Parkinson's is a good example, where some of the genetics are also starting to point to microglia, like LRRK2 and other genes that are expressed or enriched in microglia are becoming implicated. But I think comparing, again, transcriptomic data sets across these diseases could be also very helpful. So less is done in other diseases in terms of the mechanistic work, but I suspect that there's going to be a lot of common converging biology going on across many different disorders.
The externalization of PTS is a super interesting mechanism. Is that sort of actively encouraged? Is that just a passive process of membrane breakdown? How do you think that works?
Yeah, so we don't think it's passive. And I think that's the next study I think that we're working on now is going to be more interesting, because what we're missing in this first paper was a snapshot. Like, we basically saw what was happening at that moment in terms of exposure. But what we were missing was how dynamic is this process? So what Nicole is doing now, since we have the tools to study this in slice, in vitro, as well as in vivo, we think, we can start to develop ways to be able to stimulate neurons, look in activity-dependent manipulations, and then ask how dynamic is this flipping? And at least preliminarily, it looks like this is quite a dynamic process. It's not a static process, and it's not happening in this all or nothing way. So there may be a very normal physiological function of phosphatidylserine that we've just overlooked because we didn't have the tools. So I think it's not going to only be about pruning. I think this phosphatidylserine could be having other functions in the context of synaptic development and synaptic function that we just haven't uncovered yet.
The questions keep rolling in. Two potentially related questions. Maybe you can talk about similarities and differences between what microglia and astrocytes are doing, as well as similarities and differences between developmental and adult pruning and roles for microglia.
Yeah, great. And I almost feel sad that I blew off the astrocyte for my entire talk, in part because I try to stay focused and on time. But astrocytes and other glial cells are, actively signaling to microglia, and there's a dynamic crosstalk going on between, especially the astrocytes and the microglia. So we are very interested, and so is the field, in trying to better understand how those two cells are talking to each other. So in some ways, you can imagine if the insult, let's say in the case of Alzheimer's, where the genetics is pointing to the microglia being dysfunctional, that if those microglia cells are not functioning properly, that could influence astrocytes at a very early stage and in a very sort of specific way. And if you look back to what's been done in the field on astrocytes and synapses. There's so many roles of astrocytes and synapses, from synaptic development, synaptogenesis, synaptic plasticity. So many are starting to study this. So you can imagine if the microglia are misbehaving, that could alter astrocytes' normal function at the synapse. They're no longer regulating synaptic homeostasis, synaptic plasticity, their signaling is off. So you can imagine when one goes awry, the other goes awry. And you could flip the whole thing around and say if the astrocytes in other conditions are dysfunctional, that can also influence the microglia. So one of the things that we'd like to be able to do more directly now that we know what molecules and tools to study the two cells together is start to perturb one signaling pathway in one cell and ask how it affects the other. And I think this is the approach that the field's been taking in general. But again, I think the single cell data is going to be irrelevant, because if you look at nuke-seq data where you can profile all the cells together, you can start to ask about potential interactions between cell types and receptor ligand interactions to identify candidates that can then be studied in more reduced systems.
So how are you thinking about sensing relative less activity, for example, in terms of pruning during computation between the two eyes? Who's making that computation over what kind of spatial scale and time scale?
Yeah, so if you think about it, I mean, at least the way we're thinking about it is that if we think that the neuron really starts, like they're kind of driving this, which isn't going to surprise most people that are more neurocentric in their thinking. But I would say what's exciting about this idea of signaling is that if you think about activity dependent competition, there's something upstream, whether that be a calcium dependent change that's ultimately leading to the exposure of molecules on the surface of certain synapses, in this case, the less active. Now, phosphatidylserine might be one example, but there's probably others. So then the binding, the membrane is different on the weak versus the strong. And that's going to then recruit molecules and microglia to those inputs, to those signals. So again, I think the idea of doing more of a deep dive on the proteomics on weak versus strong synapses in different manipulations. So we're doing this in the context of like purifying pre and post-synaptic elements through synaptosome preps in different circuits, coming up with other clever ways to barcode and actually sequence. There's a lot of new technology I think we can apply to this idea of activity-dependent competition. So the visual system, I keep coming back to it because it's such an elegant system. Like we know so much about the circuit, we know when and where it happens, we know how to manipulate it. So we're going to keep going to the visual system as our model system. And then based on that information can like kind of zoom out and ask, well, how does this impact hippocampus or prefrontal cortex? There could be some conserved biology there.
Yeah, wow. The proteomics can be really interesting.
Yeah, totally.
Okay, thank you so much. This was fantastic.
Thanks for having me, and thanks for inviting me.
And thanks everyone for asking questions. And with that, we'll close the session. Yeah. Thank you.
Take care. Bye. All right.
Didn't correspond, so a non-congruent prior, or we gave them no information whatsoever. And then we replayed the speech, so the speech signal that they heard on the first presentation, noise vocoded or sine wave speech. And we again asked them to give a clarity rating on that. And if they had received some prior information, we asked them to judge whether or not it was congruent with the auditory signal. So here's an example of noise vocoded speech. So if you're playing along at home, you can sort of listen to this, try and understand the meaning of it and give a clarity rating 1 to 4. So hopefully you could hear that, even if you couldn't understand it. Here's a prior. The scientific community received the news with enthusiasm. And now I'll replay that stimulus. And hopefully then you find that actually, if you couldn't understand it on the first exposure, that it becomes a lot more easy to grasp the meaning of that stimulus on the repeat exposure after having the sentence presented to you in visual form. Now here's an example of the sine wave speech just for comparison. And
Andrew, I don't think we can hear it.
It's not coming
This might
through.
be an excellent example for top-down processing here. So if you don't get it to work, we can use our expectations to fill it in.
Yeah, I'm not sure what the trick will be. So it's playing on my PowerPoint. Do you have any idea how I can broadcast that?
So one option would be when you share your screen, just make sure the two boxes are checked. So if you unshare and then reshare, you might have, there are two boxes at the bottom that says share computer sound.
Yep, that's got it, I think. Yep. Great. So I'll just quickly replay those, just so at least you've got an intuition. So this is the noise vocoded speech. And here's the sine wave speech. Okay, and so what we did was we had 19 subjects and we recorded EEG, and we also recorded pupillometry, although I won't be presenting that today. So just a word about the stimuli that we use. So here are the spectrograms for the clear stimuli before being degraded. You can see most of the spectral activity is kind of occurring in this lower frequency range, but also there are some fluctuations up in the higher ranges as well. When we use a noise vocoder to manipulate that signal, what happens is we basically inject a whole bunch of noise throughout the whole range of the frequency bandwidth. So we're adding a lot of adding noise and sort of disrupting the fine-grained spectrotemporal information. But we're preserving the sort of slower temporal modulations of the amplitude envelope. For sine wave speech, on the other hand, we're introducing sine waves in place of these high resonance formants. So instead of introducing noise throughout a broad band, we're basically reducing the information or reducing the complexity of that stimulus. And in both cases, we preserve the envelope of the original stimulus pretty well. There's a little bit of deviance here, particularly for the noise vocoding. So let's move on to the results. So I'll just present the clarity ratings first of all, and then I'll move on to the spectral analysis, and then finally stimulus reconstruction. So in perceptual clarity, those ratings from 1 to 4, so 1 was that you didn't understand anything, 4 was that you understand most or all of the signal. We don't see any difference between conditions on the first presentation because the priors can't have an influence on the first presentation. They can only influence the second presentation. So we see no differences we'd expect, but we do see a difference between stimulus types. So in general, people found the noise vocoding was harder to interpret. On the second presentation, if you don't receive a prior, there's a small increase in the clarity rating, and the same on the incongruent prior. But if we give people the congruent prior, what we see is a dramatic improvement in people's clarity ratings. So that just confirms that we're seeing the effect that we're expecting to see in terms of that perceptual filling in. If we move on to spectral analysis, so I'm just going to present data from the theta band and the alpha band. We see a small decrease in theta power for the sine wave speech following a congruent prior. We don't see much change when there's no prior information or incongruent information. And for noise vocoding, we see a similar pattern, but in fact, we see a greater decrease following the congruent prior. So the difference between the first and the second presentation there is significant on post hoc analysis. And we see that also in a cluster-based permutation analysis, where most of the effect is occurring in the frontal left region of the scalp. And we see a difference in the positive or the congruent prior versus the negative prior, and between the no prior and the positive prior or the congruent prior. So those effects aren't coming through so strongly for SWS as they are through NVS. So that's the three-way interaction that we see on those models. So what we think might be happening here is that we know that theta power is associated with the retrieval and the integration of lexical units during incremental sentence processing. So we propose that in the presence of a congruent prior, particularly in the case of noise vocoding, where the original speech is very degraded and people are really having a hard time sort of extracting any meaningful content out of those signals, we think that by giving that congruent prior, people are much more able to map the correct content of the sentence onto what they're hearing. And so they're able to resolve that sentence much earlier than they're able to resolve sentences in the other two conditions. So we see kind of a continuation of theta power activity we predict, or we interpret from the other two conditions, because people are having to sort of engage in further processing. They're having to test sort of a higher number of potential hypothetical ways of resolving that sentence as they would compared to the positive condition. On the alpha band, we see a similar kind of overall pattern of results in terms of a decrease in activity for both positive or both congruent priors compared to the first presentation. We also see a significant decrease in the no prior condition for sine wave speech. And we relate these findings sort of broadly to kind of domain general functions of alpha band filtering, where we think that alpha band activity is involved in trying to filter out noisy interference. And we think that there's an additional need to try and filter out noise or separate signal from noise in the presence of noise vocoded speech when there is no congruent prior, so in the negative prior and the no prior condition, and also the same for the sine wave speech when there's an incongruent prior. So potentially a kind of interference effect. If I give you the wrong information, there might be some more interference that's kind of provoking some further alpha activity to try and filter out that sort of distracting noise and try and hone in on the meaningful content in the sentence. However, that interpretation is a little bit tenuous, because we're not seeing significant effects on those two congruent priors. There is a decrease, but it's not reaching significance on the post hoc analysis. So I'll move on now to the final set of results that we have here, which is the stimulus reconstruction results.
You have 2 minutes to do that, and that won't allow for questions.
I'll be quick then.
I was trying to signal.
Yeah, was completely missing that. So I'll rush through this. Basically, what we did with stimulus reconstruction is you try and produce a backward decoding model where you map the neural responses onto the stimulus. And the idea is that we're going to try and correlate the reconstructed stimulus onto the original stimulus that people were exposed to in degraded form during the experiment. And basically, the bottom line of these analyses are that we find a significant improvement in stimulus reconstruction for the congruent prior versus the incongruent prior. And we find the same effect under noise vocoded speech. And when we decompose those presentations into 3 segments for the 3 sentences, we find a significant effect contrasting the congruent prior with the incongruent prior for both stimulus types on the first exposure, but we don't get it on the second exposure or the third exposure. And finally, when we correlate the decoding performance against the clarity rating, we see a positive correlation in the case of sine wave speech. So it's suggesting here that we have a better chance of reconstructing that original signal envelope when people are able to track the meaning of the sentence more accurately. We don't get that with the noise vocoding, but we sort of caveat that by saying that we see less variation in the clarity ratings anyway, so it might be harder for correlation to manifest. So I'll just wrap up. Although sine wave speech was more intelligible on average, we found that providing congruent priors consistently evoked perceptual filling in both stimulus conditions. The spectral analysis and the stimulus reconstruction results, they afforded complementary information about electrophysiological responses to prior information. And importantly for our research question, the congruent priors listed EEG responses that resulted in improved stimulus reconstruction, which does suggest that the top-down processes that we instantiated do augment or can augment encoding of low-level auditory features. And just very, very briefly on the end there, I touched upon the fact that stimulus reconstruction comported well with the behavioral data. So we had more success at recovering sine wave speech, especially when those instances of speech were more clearly perceived. So I might just end it there, given that I think I'm out of time. And thanks to my colleagues, and thanks to you guys.
Thank you so much. Maybe we'll hold questions to the end in the interest of time. If people have burning questions, please put it in the chat and Andrew can engage, and then we might have a few minutes at the very end. I don't want to get too much into our next speaker's time. So if you want to pull up your slides. So Leo Tavares is from Penn State University, and he's going to dovetail off of Andrew's presentation here and share some exciting work that takes a novel approach to classifying and segmenting birdsong.
All right, great. Thanks, Kalina. And thanks to the organizers. This has been great so far. So my name is Leonardo, and I'm a grad student in the physics department at Penn State. And what I'm going to present to you today is a brief summary of our attempts to develop a brain-inspired system for recognizing auditory objects. Okay. All right, so let me start off with some motivations for this. As you might have gotten from Andrew's presentation, humans have a remarkable ability to understand the speech, and we usually take that for granted, right? I mean, we have been trying to build machines to recognize speech for quite a long time now, and we very often see that it falls short from our abilities. And they're ubiquitous in the modern gadgets, but still they don't work quite as well. So there are a few challenges in automatic speech recognition that we should pay attention to. For instance, here I'm showing the performance that is usually reported for a speech recognition system is more or less on the human level, but that's on very specific data sets. And if you look closely, these data sets have hundreds of hours of training data, okay? And then if you look at the performances of these models on mismatched data, you see that they completely fail. Okay, so there's some secret sauce missing from this kind of system, and we're trying to tackle this problem. Now, speech is a little bit of a difficult problem, so we're going to switch to a simpler one, which shares some common features with speech, but that is of birdsong syllable recognition. Okay, so here I'm showing the song of Bengalese finch, data from Sakata Lab and at MacU. And now our task is to go from this to this. So an annotated version of the spectrogram where we have the start of each syllable and also the class of each syllable marked. All right, so that's our goal. Now, we're gonna do this with some constraints from the biological side. And our main motivation comes from works such as this one from Schneider and Woolley in 2013, where they recorded some units in the higher auditory cortical area from the zebra finch. And they found that some units responded very precisely and very robustly to particular auditory features in the song. Okay, these are conspecific songs. And even more remarkable is that in the presence of a background song, these units still fire. Okay, so this is a very sparse code that is responding to specific auditory stimuli. Okay, so let me start off with what our ideas of this problem are. Here I'm showing a spectrogram that we calculate from when the song comes in. And this is a particular syllable from the Bengalese finch. And what we're gonna do is we're gonna window the song. We're gonna calculate many short time windows from the song, and we're gonna represent them in a very high dimensional space. So here I'm showing 3 dimensions, but you should really think of this as really high dimensional, and each feature here corresponds to a single point. All right, now that's one exemplar. We can do this for many different exemplars, and here I'm showing the same syllable, but different exemplars, so they're slightly different. But I'm taking more or less the same spectrotemporal feature for each one of them, and presumably they lie close together in this feature space. Now, other features might lie a little bit farther away, but this gives us an idea that we can maybe cluster together or train a decision boundary to capture the similar features. Okay, so that's what we're gonna do. We're gonna train these decision boundaries and combine similar features together. Okay, now what we do with this. Here's where I am Suppose now that there's a song coming in. Song is represented here in the spectrogram. And now what I'm going to do is I'm going to take a slice of the spectrogram, a short time window, and I'm going to slide it on the song. Okay, this corresponds to a trajectory in this feature space. And note here that I made the trajectory go inside of the decision boundary that I just trained on purpose. And if you calculate the distance from this trajectory to the decision boundary, what you get is something like this. There's a baseline, and then it shoots up. Okay? And in fact, it shoots up above this threshold, the green threshold that I represented here, and which I defined. And that indicates to us that this particular decision boundary is capturing this feature inside the song. Okay, so it's capturing a tiny spectrotemporal feature inside of the song. So once we've done that, then we can trace back and find the onset and offset of that detection. Okay, so that's fine. We can do that for an entire vocalization and essentially represent it as a series of decision boundaries in the feature space. Okay, and in fact, we can encode entire syllables as sequences of onsets and offsets. All right, we can do this, can carry this idea even further and construct a template bank of these onsets and offset sequences. All right, that's the training part. Now let me quickly switch to the decoding part, how we do decoding for the system. So imagine there's the same bird and it sings, and now we have a set of syllables that continuous syllables that we want to decode. What we do is we take those decision boundaries that we trained and we encode it as a set of onsets and offsets again. And now we're going to use the templates that we just trained to decode this representation. So how this is done is the following. This is just representing, again, the same set of onsets and offsets. And I'm going to take the templates. I'm going to first match the onset sequences, right? So this allows me to find the onsets in the input. Then I'm going to match the offset sequences. And that allows me to find the entire region where each syllable spans. Okay, that gives me a score function, which in fact gives me the precise start and end of each syllable. Now you may be asking, why do this? Why do the onsets and then the offsets? And the reason is really for a generalization, because imagine that we have again the same syllable E here, but now I'm going to stretch it. So the initial burst is the same, but then the harmonic stack is kind of stretched in time, right? And that means that the input onset and offset sequences will be stretched as well. So we have to be able to first capture the onset, then the offsets, and then we're going to be able to capture the entire duration of the syllable. All right, so that's the idea. Then we use the waveform to slightly correct the onsets and offsets. Now this can be a little sensitive to deletions and in the sequences. So we adopt another procedure to complete the onset and offset sequence, and that is we lower the threshold for detection. And you can think of that as kind of expanding or decreasing the receptive field of these neurons. Okay, so we tested this with 5 different Beglins finches, and here I'm showing the word error rate. Word error rate is just comparing the number of misclassifications in the output string in comparison to the ground truth, right? So what this is saying is that for 10 training syllables per syllable type, which is more or less 10 seconds of recording, we get about 1% of word error rate. Right? So that means that this can be quite useful in practice. Here's some examples of this idea in practice, annotating in real life some Beglins finch songs. And just let me conclude really quickly. I just described a new method of recognizing auditory objects with sparse sequences. The method can be useful in practice. There's some potential application for speech recognition. In particular, we're excited about potential application in neuromorphic devices. And we're planning to release this work as an open source software for the community briefly. Okay, so with that, thanks everyone, and thanks to my advisor and my colleagues at Wednesday.
Thank you very much, Leo. That was fascinating. We actually do have a moment for questions. So I'll ask the question that came up here. If others have a question for Andrew, we have about 3 minutes. So Isaac actually asks, how do you choose the appropriate time window, and how does it work with speech?
Yeah, so that's a good question. For the Bengalese finch, it seemed like around 40 milliseconds worked well. But then I tried with song sparrow, and that required me to increase it a little bit. So it might depend on the specific kind of auditory stimuli. It might be a kind of trial and error thing. For speech, I would imagine that it should be a little smaller. The window should be probably smaller.
We have a moment or two if there are other questions, including for Andrew. Whether you did, there was a question about the method, wondering whether you did dimensionality reduction for the spectrogram segments. I think
that's also a good question. Mm-hmm. I played a little bit with some dimensionality reduction methods. In the end, I decided to stick with the simplest case. I'm just using a very high dimension feature space because that actually helps the training in my algorithm. But this is work in progress, so I'm not sure. Just a quick note, I'm using support vector machines, so that using higher dimensions usually works better in this case.
Great, thank you. I do actually have a question following Andrew's talk. I'm a developmental psychologist. I work with human children. I'm wondering whether you have any insights about when these kinds of top-down effects emerge. Do they happen early, as soon as children acquire language? I don't know if you have insights.
Yeah, I probably don't have any insights, but I mean, particularly for the kind of perceptual filling in effects that I was talking about. But I mean, if you treat sort of predictive coding type approaches seriously and believe, you know, the kind of excitement around how important predictive processing is as a kind of domain general mode of cognition, then presumably language acquisition is sort of importantly driven by being able to pick up on regularities and develop those expectations, those priors, even though they might be sort of locking into quite sort of low level simple regularities in the environment, maybe not quite the more sophisticated forms of speech recognition inference that we're trying to tap into with our experiment.
Yeah, absolutely. Okay, great. Thank you both. We're going to move into our next speaker, who is Isaac Moran from the National Autonomous University of Mexico. And he's going to share some novel data that looks at the role of supplementary motor area in auditory categorization. Thank you, Isaac.
Thank you. Well, this talk is neural correlate of auditory categorization in supplementary motor area. And well, we know that the brain builds internal representation of sounds. These internal representations are important to categorize the sounds and then make appropriate behaviors. This process is important for humans and for other animals. However, the neural mechanisms associated with auditory categorization are less understood. Well, for this reason, I question how does the brain decide which action to perform based on sounds? For this reason, we create an auditory categorization task in which we train monkeys to arbitrarily distinguish between target and no target stimulus. And well, the monkeys learn the target stimulus because they are rewarded. We use naturalistic stimuli with complex spectrotemporal patterns, and the types of sounds that we use were monkey vocalization, animal vocalization, artificial sounds, and Spanish words. During the task, the monkey was sitting in front of the screen and a speaker and a lever. And the trial began when a gray signal appeared in the screen indicated that the monkey need to press the lever. After this, a sequence of auditory stimulus occurred, and the monkey task to receive reward is hold the lever during the no target stimuli and release the lever after a target stimuli. And it's important to note that we incorporate a delay after the stimuli and green go visual cue. We do this because we wanted to disentangle the auditory and the movement signals. That's all right. There are 3 types of trials, depending on how many sounds occur in the trial, with 1, 2, or 3 sounds. And it's important to know that the target sounds always appear on the last on the trial. Then when the monkey learned the task, we record extracellular activity in supplementary motor cortex, and we choose this area because it's related with integration of sensory information, decision making, and premotor activity. This is the percentage of correct responses in the categorization of target and no target stimuli. And we can see that the recognition is very well, is higher than 80%. And well, when in general, the neural activity in SMEA called the categorical stimuli. And this is an example of a neuron. It's a raster plot, and the firing rate in black lines, and is grouped by the number of stimuli. We can see that this neuron increase its firing rate when the target stimulus appear, decrease its activity during the delay, and then increase again during the period in which the monkey need to release the lever, moving his hand. In contrast, during the no target appearance, the activity of this neuron is changed only a little bit. If we see the same neuron, but this time aligned to the sound start, we can see that, the same profile, but this time depending on which sound is presented. This is all the sound in target and no target categories. And we see that this signal increase with target and is modulated only a little bit in no target sounds. The black line below indicates the moment when this neuron categorize significantly the difference between target and no target sounds. The blue line and the red line indicates the moment when this neuron recognize the individual identity of each sound inner the category. And we can see that this neuron categorize very well, but don't recognize the individual identity of each sound. But it's interesting, no? And there are 3 other examples of neurons, and we can see that the categorization profile is very common in this area. Here, we summarize the population responses in the percentage of neurons that code the category or the identity of no target and target sounds. And we can see that many neurons code the categories of the sounds. Then we also investigate the categorical dynamic of neural activity in the population level. For this, we use principal component analysis as a method for dimensional reduction. In this plot, I show the first principal component, and we can see that activity of this component indicates the moment when the monkey releases the lever, and this makes sense because it's a premotor area. The second component is very interesting because it predicts the appearance of each sound, but its activity increases a lot if the sound is a target sound. Maintain this activity during the delay and decrease when the monkey is going to move his hand. And the third PC indicates the moment of the start of the trial. Well, then we made the mixed PCA, that is a similar method like PCA, to know how is the categorical coding in the population activity. And here is the first DPCE that represents the categorical profile of the population activity. We can see that this categorical profile start at the middle of the sound, is maintained during the delay, and reach a maximum peak when the monkey releases the lever. This is the second and the third DPC, and we can see again the categorical profile, but this time in a transient way because the signal changed their sign in the movement period or in the delay. Well, sorry. And this is important that the three PC together sums 60% of the explained variance of the total activity, neural activity. Then we wanted to know if the auditory and movement processes are dependent or independent one of each other. We use a method developed by El Sayed that calculates the principal component in each period in an orthogonal way. And here I show the variance explained by the first auditory component. This component, explain 50% of the variance during the auditory period. And then during the delay, explain a little bit more variance, but in the movement period, it doesn't explain much of the variance. In contrast, the movement component can explain about 60% of the variance of the population during the movement period, but not a lot in the auditory period. And the result means that the auditory and movement computation are independent or close to orthogonal each other. And well, if we plot the neural trajectory of the auditory dimension versus the motion dimension, we can see that during the sounds appearing in dots, the neural trajectory moves along the auditory subspace. If the target is presented, the trajectory goes to the right in opposite direction of the no target trajectory. And this is very, very interesting because it's like two attractors. And then only on the target appearance, this trajectory travels around the movement subspace to the top, because is when the target appear, the monkey need to release the lever, need to make a movement of his hand. And well, in summary, we found in this premotor cortex that at single neuron and population level, there is a categorical coding. And we found a transition from auditory to movement dimension that is very interesting. And well, thank you for your time. This is the preprint, and this is my mail if you want to contact me. Thank you.
Thank you very much, Isaac. Feel free to also share your papers in the chat for all the attendees so they can have a link if you, in case they can't click on it for if you have a link to your papers or your contact information, Twitter, anything, feel free to share it. Are there any questions from the audience? Great, thank you. There's a question from Mildred Salgado. Are there any results with the control task? How are the neurons modulated during this condition?
Yes, well, we have a passive condition where the monkey only perceive the sound, but doesn't do any behavior. And in this case, the neural activity is flat, isn't modulated, is not modulated. And well, this is, I have a sorry. Yes. In this case, in this passive condition, it's a flat activity. It indicates that the monkey needs to do something to categorize the stimuli to change their activity in this area. And is this. Sorry.
Thank you.
Mm-hmm.
As I was watching this, I was wondering what do you think would happen to the auditory categorization if you deactivated SMA? Like, how would that impact it? Or like, what's the result on the auditory like categorization?
Sorry, can you?
So because you were showing these fascinating results in SMA, right? That they track categorization. If you were to deactivate it somehow, the SMA, what would be the effect on the auditory neurons?
Wow, this is very interesting. Well, I think that it is a good experiment because if we deactivate this area and the monkey can't do the task, maybe it's an important area, but we don't have this experiment, but I think it's very, very, very interesting.
Yeah, it's fascinating. We have one more question from Joseph. Can auditory cues be trained to a specific effector over time with reward? Example, a high tone for the right arm.
Yes,
low tone, like high tone for right arm, low tone for left arm. Can you do?
It is also a good question. I think there is a paper from Robert Shaker. I don't know if you know this researcher. And well, they train monkeys to do something, a different movement depending of the sound. And they found that in premotor areas, there are many neurons that modulate this activity depending of the motor plan. Well, I think it's interesting.
Wow. All right, I think we have a moment or two if anyone has additional questions for any of the speakers. And then I think the organizers have to get ready for the next talk, but if there are any other questions for any of the speakers, we can take one more. All right. Any of you guys have questions for each other? So it's great session, and I'm sure it's recorded and will be posted. So thank you all for this fascinating panel. I definitely learned a lot. So thank you all, and thank you to those of you watching and listening.
Thank you.
Great, thank you.
Have a good night. Thank you.
Bye-bye.